हेलो। टेस्ट। जो लाइव है वो उसको डिलीट कर दो। सुनो तो। हेलो। डायरेक्ट थोड़ी आएगा, थोड़ी देर के बाद आएगा।
So, very good morning to all of you. I would say very good quantum morning to all of you. So, today we are here to celebrate the 100 years of quantum mechanics. So, Honorable uh, Director Professor Hirendranath Ghosh and our esteemed speakers, um, colleagues from NICER, faculties from other colleges, and dear students. Today, the day we are going to have this 100 years of quantum mechanics celebration at NICER, and we had this idea to have this here in Odisha in some form, and due to the generous uh, encouragement and support from our director and also the chairperson, Department of Physical Science, School of Physical Sciences, NICER, Professor Karthik Senapati, we are successful in organizing this event. So today we'll have several talks by experts in the field, and you'll have opportunity to interact with the speakers, and you can also talk to the faculties of NICER, and you can also talk among yourself from the students from different colleges and teachers from different colleges. So it will be a nice gathering to exchange ideas and get exposure about the modern quantum technology, starting from the foundations of quantum mechanics. So without further delay, I would like to invite our director, Professor Hirendranath Ghosh, to formally inaugurate this event.
Good morning, everybody. Welcome to NICER Quantum Mechanics. My background is chemistry, but my work actually basically because of quantum mechanics. I mean, I work on quantum dots. So this is some subject. It is not only the physics people can think it is their subject. Actually, quantum biology, quantum chemistry, there are a lot of discoveries happening. You can see people are getting Nobel Prize. Even quantum dot Nobel Prize got by the chemist, and the physical principle of quantum mechanics starts 100 years back. See, this is like a Darwin moment of physics, right? We cannot think about modern biology without the thought process of or work of Charles Darwin, like that the physical world, whatever science we are doing, based on the quantum principles. And it is so important. It is across the different periphery of the science, not only the physics, chemistry, biology, engineering. You know, you cannot actually avoid quantum mechanics. So I'm so happy to inaugurate. I mean, this all of you came from other places, other institutes, and interacting with our faculty and all students, which will be enriched for all of us. And I have a lot of old friends here. I can see Professor Arun Pati from BRC, he was there earlier days. I can see our Professor Dev, Bhupenda. So it's a very nice moment for getting everybody here. And I'm sure all of you will enjoy. And maybe sometimes later I will also give a talk, what exact what I'm doing. I can tell a little more about that. Till that moment, let's enjoy the other part of the lectures, other lectures. And I suggest all the students, you know, the people who are giving talk, they are all stalwarts. You can check their work, what they did, and I'm sure you will be immensely benefited. So my request to all of you, uh, please interact with them. Thank you very much.
Thank you very much, sir, for your kind words, encouraging words. So now I would like to invite Professor Karthik Senapati to chair the first scientific session of this event.
Good morning to all of you, my teachers, senior colleagues, and colleagues from Niger, as well as students. So we are starting the first session today morning. We have two very interesting talks in this session. The first one is by Professor Lambedar Prasad Singh. So he's a very well-known. I would say the word that comes to my mind is a teacher, because I have been had the privilege of being a student of his class long back. He did his PhD in just a little bit of introduction. He did his PhD in Utkal University only in 1975, and since 1976 he has been teaching batch after batch after batch. Like he had a very long teaching career. I think in Orissa, I will like many people is very well known. He has also his research interest is particle physics and cosmology, but he has also written books in Oriya for physics popularization. So he's very he is known as a popular science popularization figure. And today he will just to start this session, he will start with the very beginning, hopefully, story of the quantum mechanics from the very beginning, probably. So let's welcome Professor Singh, with a big round of applause. Hello.
So, good morning, everyone. I'm very happy to be here as well as tense. My happiness comes from the fact that I'm meeting people whom I had pleasant privilege of meeting them in different occasions of in my journey of life, and I see that they have become experts, and they are also guiding the destiny of the young generation as well as of my country. And I'm tense because I have nothing new to say, because I have experts in front of me, and that also is a privilege, because whenever I make mistakes, I can stand corrected. Let me give just two lines in Odia. ତପନ ସାର୍ ଯେତେବେଳେ ମୋତେ କହିଲେ ଆପଣ ଗୋଟେ ଟକ୍ ଦେବେ, ମୁଁ କହିଲି ମୋତେ କାହିଁ ତା ଭିତରକୁ ଟାଣୁଛ? ନା ଆପଣ 20-25 ବର୍ଷ ତଳେ କ'ଣ ଇଆଡୁ ସିଆଡୁ କହିକି ପଳେଇଥିଲେ? ମୋ ସାଙ୍ଗମାନେ କହିଲେ ତାକୁ ଆଉ ଥରେ ଡାକ ଶୁଣିବା। ମୁଁ କହିଲି ଥରେ ତ ପଳେଇଥିଲି, ଏଥର ବି ପଳେଇବି। Okay, so let me come to quantum mechanics, a bit of the subject that I know. And so as far as I know, you all also know, students here, everybody knows in fact. Modern physics more or less started from, let's say, mid-15th century, when the three laws of planetary motions were written, written by Kepler. Before that, we had some science, but that I would not call as modern science. But we had science. We had science, a lot of science, even in this country of ours. But anyway, it all started, the physics as we know it today, in fact, the journey started from mid-15th century, 16th century. And when the three laws of planetary motion were written, as you all know, they in fact needed a proof, because they were based on observations. Observation, in fact, is an important ingredient of promotion of science, progress of science. Science, as we know today, physics, for example, runs on two rails. One is observation, experiments. Another is mathematics. Because as Galileo had said in the early part of 17th century, the language of physics is actually mathematics. Language of nature, in fact, is mathematics. So that's why you saw just now the director saying that biology, chemistry, physics, the whole of science, in fact, is written in the language of mathematics. So, and the proof of these Kepler laws came through no less a person than Newton towards the end of 17th century in his famous book, magnum opus, Principia Mathematica, Natural Philosophy. And in that he gave the three laws of particle motion as well as the law of gravitation. And then he invented also calculus and then proved the Kepler's laws. And the journey, in fact, has been over 300 years till the end of 19th century. And physics had phenomenal success. We studied, in fact, physicists studied almost all kinds of systems. They studied particles, had laws for them. They studied matter in all its phases, solid phase, liquid phase, gaseous phase, and in fact wrote down various laws governing their motion. They also studied systems which had electric charge in them, giving rise to electric field, magnetic field. Then they also promulgated laws for them, culminating in the four beautiful equations of Maxwell in the 1864-65. And then they also formulated laws for fluids, gases, Charles' law, Boyle's law, Gay-Lussac law, then Navier-Stokes law. All kinds of laws actually were laid down, in fact, to study matter in all its forms. They also studied thermodynamics. They also promulgated three laws. They also developed statistical mechanics, not just to study a system with single particle or two particles, but also study particle system with 10 to the power 23 particles. That also was very successful. So, in fact, so much so that by the end of 19th century, Michelson was the first US physicist to get a Nobel Prize in 1907. He, in fact, is reported to have stated that most of the fundamental laws we have already promulgated, we have found out. So it is very unlikely that future experiments, in fact, would invalidate them or require them to be replaced and renovated by other laws. So most of the fundamental laws are already known. And Lord Kelvin is reported to have stated that in the clear sky of physics, we only see two small clouds. One, he referred to the novel result of Michelson-Morley experiment. He was one of the experimenters. And the other referred to the explanation of the blackbody radiation current. And as we know in our hindsight, that in fact these two small clouds gave rise to the theories of relativity by Einstein and quantum mechanics, which actually revolutionized physics or the way we look at the physical world. So, can I have the next slide, please? Is there a pointer or something? Oh, it. Thank you. So it actually, even though the laws of physics were very successful, towards the end of second decade of 19th century, 1819, 1820, there was a law which all of you know, Dulong-Petit law, which describes the specific heat of solids. So at very high temperature, they are constant, something like around 6 calories per gram atom per degree Kelvin. So, and that could easily be explained using classical thermodynamics. But if you go to low temperatures, then you see that actually there is a deviation, and people, in fact, there was no way of deriving the low temperature variation of specific heat of solid. So that was the question. Then, how do I go to the next one? Okay. Yeah. And then there was this spectral studies, spectrometry. And for example, in case of hydrogen atom, Angstrom had studied the spectrum of hydrogen atom, and then he observed discrete lines. Normally, one would expect that if you are taking a photograph of the radiation, we would probably get a continuous band of spread of light of whatever color. But that was not the case. In fact, in emission spectrum, we got discrete lines. In absorption spectrum also, we got discrete lines. So the presence of discrete lines in the hydrogen spectrum or spectra of other atoms was also a puzzle. We did not know how to explain that. So that was around 1850, 1860 and kind of thing. Angstrom's paper was published in 1855. And then we had also towards the end of 19th century, we had this curve for the blackbody radiation. And the blackbody radiation curve, as you can see there, actually for very low wavelength, the energy density of the blackbody radiation is small. For very high wavelength, energy density of the blackbody radiation is also small. In between, it actually peaks. But we had actually laws to describe this in terms of thermodynamics, Rayleigh-Jeans law and Wien's law. Rayleigh-Jeans law describes this curve for high wavelength side. And then Wien's law actually describes this for low wavelength side. But we never had a law, we could never explain the entire curve by one law, by one equation. So that was also a puzzle. And the last one was the photoelectric effect that was observed by Hertz and Leonard around the turn of 19th century to 20th century. So this actually said that, as you all know, you read in BSc, that the electron which is emitted when you make radiation fall on a metal plate is proportional to the frequency of the radiation, not to the intensity of the radiation. And similarly, the number of electrons are actually proportional to the intensity of the radiation. And not only that, this effect is immediate, instantaneous, more or less. Whereas classical thermodynamics would suggest that it would take some time, but that was not the case. So these four practically were the bulls in the china shop, which was looking so beautiful. As I just told you, many people thought that we have more or less obtained all the fundamental laws of nature. But we were failing to describe these experimental facts. So on 1900 December, Max Planck, in order to explain in fact the previous curve, this one, he was working on it. He proposed his result of investigation in the German Physical Society. And where he in fact made a very revolutionary conjecture that the energy of radiation in case of black body in fact is quantized in terms of a very small amount of energy. You can call it energy quanta, which we now recognize to be some constant, which we call Planck's constant, into the frequency of radiation. And therefore the energy of this black body radiation in fact is integral multiples of h nu. You cannot think of energy less than h nu. So that was his revolutionary concept. And if you use that, then in fact you can actually explain the entire curve. Because you find out for a given frequency of radiation, you find out the number of energy cells that you have. And there you get actually, as you all know, it is 8 pi nu square divided by CQ. And each frequency radiation has energy equal to n times h nu. So you go on, so he basically wanted to find out what is the average energy of radiation for each cell of the cell that I said 8 pi nu square divided by CQ. So these are the number of the cells. So for each cell, you have to find out the average energy of the radiation. And this he did very nicely. So he first found out the, the probability of obtaining the energy to be equal to E. E is equal to NH nu. So this is the probability. Then he calculated the average energy per cell with energy E, and this in fact is just a summation of geometrical series, geometric progression, and you would end up with the result that you already know, h nu divided by e to the power h nu by kt minus 1. If you go to the higher wavelength side, you would recover Rayleigh-Jeans law. If you go to the lower wavelength side, you would recover Wien's law. So that was very nice. And that in fact was the origin of a new era in understanding the physical world. understanding the radiation. Okay, the next result was by Einstein, when he, in fact, got hold of this idea, new idea of Planck, that the energy is quantized at the very basic level. And he said that if, in fact, it is not just black body radiation, it's radiation in any form, anywhere, in fact, it's quantized in terms of h nu. So then he used that and wrote down a very simple equation. H nu, the energy of the ejected electron from the metal plate is equal to h nu, the energy that falls on it, minus a little bit of energy, because after all, electron is attached to the metal plate by a binding energy. So you subtract that, and that the rest will be the kinetic energy of the electron which is ejected. So it's just the kinetic energy of the electron is h nu minus phi. Phi is the work function, as you all know. And this explains the experimental curve very nicely. And so, in fact, what really comes out of it is that radiation travels in some form of the wave, but interacts in the form of a particle when it interacts with the electron or atom or very small objects like that. So that was explained. He, in fact, applied this quantum mechanical ideas to explain the specific heat of solid. He first applied it to condensed matter physics. I think that was the first application of quantum mechanics to condensed matter physics. And he assumed that inside the solid, the atoms are independent and they are vibrating, and that oscillator, in fact, is a quantum oscillator. Once you do that, and they are all oscillating with equal frequency. So once you do that, you would actually come up with a very nice expression. Just a minute. Yes. So you would get, in fact, this result. The specific heat of solid, in fact, is 3R. 3R is actually 6 calories per gram atom per degree Kelvin into this factor. Now, if you take temperature to be, if you take the temperature to be very high, you would in fact see that these other factors would cancel out. They will give you 1. So you recover, in fact, Dulong Petit flow. If you go to very low temperature, then it's actually exponential decrease with the temperature, which did not agree very much with the, excepting perhaps Diamond or something, it did not agree with the experimental result. But there was a decrease. So the temperature dependence for low temperature was in fact explained by his idea. And Debye, as you all know, in fact extended this idea of Einstein to assume that yes, these atoms are vibrating like simple harmonic oscillators, but they are also interacting, and the frequency of their vibration in fact has a maximum value. So therefore, once you make these small corrections to Einstein's ideas, he in fact got that the specific heat would actually go like T3, which we call Debye's TQ law, as T goes to 0. So that was also explained. Now then we go to Niels Bohr. Niels Bohr in 1913, in fact, got hold of the idea of explaining the stability of the atom in the first place and discrete nature of the spectral lines. So he conjectured, just like Max Planck conjectured that the energy of black body radiation is integral times h nu. Similarly, Bohr also conjectured that the angular momentum of the electron inside, let's say, hydrogen atom, that's the simplest atom, should be equal to integral multiple of h cross. H cross has the same dimension as angular momentum. And once you do that, and then in a semi-classical way, by just equating the centrifugal, because the electrons are revolving, so by equating the centrifugal repulsion and the electrostatic attraction, he got the energy for the electron inside the hydrogen atom to be given by some constant divided by n square, that you all know. And that explained very nicely. So he just said that as long as the electron is in a particular orbit, it doesn't radiate. So when it makes a transition from higher energy level to lower energy level, it radiates, and the frequency, you can very well calculate from the energy difference divided by h, you get the frequencies, and that incidentally matched very well with the experimental spectra. So you could see why, for example, we have discrete spectrum for hydrogen atom. Okay, so these are all conjectures that angular momentum is quantized, energy is quantized, etc. etc. Now, as things progressed, in fact, there were two Indians classmates who actually caught hold of this idea in Calcutta, and then they developed their theories, which are now very famous. The first one was Meghnad Saha, and he in 1800, 1920, sorry, 1890, sorry, 1900, 1920, he in fact developed what is known as Saha's theory of ionization. So what he did is, in fact, he thought of the ionization inside the atmosphere of the stars, outside of the atmosphere of the stars, in the outermost domain, the chromospheres, to be a kind of chemical reaction. You have a reactant giving rise to the products. And he thought that this is actually in chemical equilibrium. So once it's a dynamical equilibrium situation. So the number density, the reactants, for example, produce the products, and products also recombine to give you the reactants at the equal rate, and you can find out the number constant or the pressure constant for the chemical reactions, which chemists had done earlier. So he knew all these things. So he in fact calculated, for example, so these numbers you can see, first of all, this is the reaction constant or number constant of the chemical reaction in equilibrium. So that's just the number of reactants. In case of hydrogen atom ionizing, for example, which he in fact applied to, this is the hydrogen atom, this is the ionized hydrogen, for example, this is the electron. So therefore, this ratio in fact is the number constant. And these numbers in fact is proportional to the Boltzmann factor e to the power minus E divided by kT. So he got hold of the, and therefore this number ratio in fact is nothing but the ratio of the partition functions. Because partition functions are defined like that. So therefore he calculated the partition function, for example, all these. Let's say this is ionized hydrogen, this is electron, this is hydrogen atom. You can always take e to the power minus E by kT. E is NH nu, and then in fact E can be calculated. He thought of these things as three kinds of gases confined to a box of volume V, and he in fact solved this by first treating a one-dimensional box, which you can easily generalize to three-dimensional box of volume V. So therefore, this E in fact can be calculated from the particle inside a box, which you do as a first exercise in quantum mechanics, and that's the energy. So you know energy, and you can calculate the partition functions. And this quantity, in fact, this H divided by this is actually called thermal de Broglie wavelength. This is in 1920. So use this for three-dimensional box. So this is the volume, and you get these numbers. You just make the power, raise it to power 3. So the number constant in fact turns out to be this. Okay, and this is the internal partition functions, which in case of, for example, hydrogen atom ionizing to H plus and E minus, they are all 1. Okay, so that's how he finally, so he took this example, which I said, that's the simplest example, hydrogen atom ionizing itself and back. So they are in equilibrium, and then you can calculate the pressure constant, which is just total number divided by pressure into number constant. Number constant is already found out, and this turns out to be the ratio of the partial pressures. And partial pressure is nothing but the number density into kT. So if you use N0 as the initial number of the hydrogen atom present, and X is the degree of ionization, then you can find out NH is this, NE is this. Total pressure turns out to be N0 into 1 plus X into kT. X is actually the degree of ionization. So you calculate the pressure constant, and in fact from here you just take the log to the base 10, you would get this. And delta E in fact is the ionization energy. So that is the Sahaj ionization equation, which involves the pressure, the degree of ionization, and the temperature. So if you apply it to a stellar atmosphere, given, and you know the spectral lines, so from the intensity of the spectral lines and the position of the spectral lines, you know the delta E, you also know the degree of ionization. So you can in fact have a degree of ionization plotted against the temperature, which basically characterizes one star from the another. In fact, so at constant pressure, these are the conclusions. From here, one can easily see constant pressure, ionization increases with the temperature, as it should, because the energy increases. At constant T, ionization decreases with pressure. The pressure is low, obviously ionization is more. And the equation allows to estimate the stellar surface temperature from the degree of ionization, which you get from the intensity of the spectral lines. So at 4000 degree Kelvin, for example, this is much less than 1. And why I have written this 4000 degree Kelvin? Because when the universe actually cooled, we have a model for universe creation, the Big Bang model. So it was actually created with very high temperature. Gradually it cooled, and when it cooled to 4000 degree Kelvin, actually, as you can see from his equation, uh, this, sorry, this ratio is much less than 1, which means actually the ionized hydrogen or the hydrogen ion and the electrons have recombined to give you neutral hydrogen. And from that time onwards, there was practically no charged particle in the early universe, and the universe became transparent, and the radiation, in fact, freely streamlined to the present time, giving us what we call cosmic microwave background radiation of 2.7 degree Kelvin temperature. So that was very nice. And in fact, his equation, in fact, explained also the spectral characterization or classification that we had earlier. This is the spectral. So we have, these are the blue stars, these are red stars, and the temperature, as you can see, the surface temperature for the red stars is very low. For the blue stars, it's very high. And in fact, they are characterized like O, B, A, G, and K and M. So just if you want to remember this, then you can always say that, oh, be a good girl or a guy and kiss me. So that's how you remember it. Okay, so Sah's theory of ionization, in fact, was very effective in understanding the classification of the stars in terms of their colors. So next was S.N. Bose in 1924. See, we had already a very nice explanation for the blackbody radiation curve by just thinking about the average energy of radiation per cell in the phase space. In fact, there is a phase space quantization, but anyway, we have phase space and p square 4 pi p square dp into v, the configuration volume, and divide that by HQ. So here goes the assumption that HQ is the minimal volume associated with one quantum state. So if you have a phase space volume, divide by HQ and get the number of cells in the phase space. And that in fact turns out to be equal to h pi 8 pi nu square divided by CQ. Once you write, your energy is equal to h nu. Okay, so he used that. We knew this expression 8 pi nu square d nu divided by HQ. This is the volume. This is the total number of cells. Now Planck found out the average energy of the radiation per cell. But Bose is saying, I will find out the average number of particles per cell, and once I do that, then I will multiply h nu to it and this factor to that, and I will get the full answer. And that's exactly what he did. And to get the average number of photons per cell, he in fact used combinatorics. And he assumed that the photons are also indistinguishable. That's a new idea which he introduced into the counting. And once you do that, then he got the number of distributions for photons in various energy cells, and that distribution turns out to be this by using combinatorics, and he maximized this to get the most probable distribution of photons in these cells, and subject to the condition that the total number of cell is fixed, total energy fixed, but the number of photons can be n. Now, once you do this by using Stirling's formula and your variation, then you would in fact end up with the number of photons for each cell will turn out to be h nu divided by e to the power h nu by kt minus 1. So, sorry. It would just be equal to 1 divided by e to the power h nu by kt. So, you take 1 divided by h nu, e to the power h nu by kt minus 1 is the average number of photons per cell. Then energy for each photon is h nu, multiply that, and that will in fact will give you the Planck's result. And then multiply to it the number of cells, so you would get the energy density for the radiation, and that exactly matches with the Planck's formula. So this is a new way of doing, finding out the Planck's formula by using basically combinatorics and assuming that the photons are indistinguishable. So he sent the paper to Albert Einstein, saying that please look at it and see if it makes sense. And Albert Einstein in fact saw and quickly recognized that this is a beautiful way of finding the formula, Planck's formula, and he translated to German, as you all know, and sent it for publication, which was duly published. And then he extended both papers to write down the statistics for the all kinds of particles, which we now call bosons, which have integral spins, which are indistinguishable. So that's how we contributed, or people from India contributed, mostly from Calcutta. In fact, they were also the two people who translated the Einstein's paper on relativity to English. In fact, that time Calcutta University was basically guiding the science of the whole country, India. We had both Saha, Raman joined them, and then we had Acharya Praful Chandra Ray in chemistry, and they all built institutions. And we are very proud of those legacies. Okay, so at the same time, Louis de Broglie in France actually wrote down, since he got hold of the idea of Einstein, that if Einstein is saying that waves can have particle nature, then perhaps particles also will have wave nature. And simple equation, since Einstein has written down the equation E square is equal to P square C square plus M0 square C4, the energy equation for relativistic particle, he just said that if M0 is 0, let's take photon into account. If M0 is 0, then you would get that energy is equal to Pc, which must be equal to h nu. And then you just make it 1 or 2 line calculation, you would see that lambda associated with a particle should be equal to h by p. This was clear for photon, but he extended it to all particles. So, and that paper in fact also came to Einstein, because that time his elder brother was actually the president of French Physics Academy or Science Academy. And then when de Broglie sent his paper, he said, why should I look at the paper written by my younger brother? So let me send it to Einstein. So Einstein looked at it and he was very happy. He said that as if the program that I started is now getting completed. So that was also published. And all these people, remember, got Nobel Prizes for their work. Louis de Broglie got Nobel Prize for his work in 1928 or 29. Max Planck got Nobel Prize for his work in 1918. Einstein got the Nobel Prize for his work in 1922 or 23, something like that. So all these people actually got Nobel Prizes. But till now, everything is in a form of a conjecture. There was no mathematical formulation of quantum mechanics as such. 2 minutes, na? Okay. Okay, sorry. So now comes Heisenberg. So Heisenberg was suffering from influenza. It's good that people sometimes suffer. So he was in fact in Helgoland Island in North Sea and trying to recover from the fever. And while doing that, he was also doing his research. And the research was just to explain basically the discrete lines of spectrum of hydrogen atom, basically not using the semi-classical method of Niels Bohr, but using quantum mechanics. So now we know he used matrix mechanics basically. So he took the X and the P as matrices, he expanded them in terms of frequencies, and in doing that, he was actually helped by the correspondence principle of Niels Bohr. Niels Bohr had said that if the quantum numbers associated with these energy levels will be very large, then in fact quantum system would mimic a classical system. So he knew about how a function of t can be sort of spread in the domain of frequencies by using Fourier transform, and this correspondence principle helped him. So he wrote x and p actually in terms of Wmn, which is the frequencies associated with the radiation when the electron makes a transition from mth level to nth level. But if the m and n are very high values, when they take very high values, in fact this Wmn is very small. So the energy levels are very close. So more or less a continuous thing. So therefore he made use of the he made use of this Fourier transform business for xt and pt, and then he differentiated it. And if you take your hydrogen, your Hamiltonian has to be diagonal in this calculation. And if you take care of the indices properly, in fact, the right hand side turns out to be a commutator of h and x or h and p. So that is how he wrote down which we read actually the time development of operators in Heisenberg picture that was actually first developed this way. So you get these results, dx by dt results, etc. And here I have given you, if the Hamiltonian happens to be of very special kind, then you can also get the uncertainty principle, delta x delta p greater than or equal to h plus by 2, which was in fact associated with the non-commutativity a little later on by Kennard in 1927. But anyway, so there was a good mathematical formulation of quantum mechanics. And then we know Schrodinger actually took hold of his idea that if Louis de Broglie is saying that lambda or every particle has a wavelength associated with it, Newton has told us that every particle when it moves we can write down the equation of motion, then this wavelength must somehow be used to write down the equation of motion if every particle has a wave associated with it. And he in fact succeeded in that. So he also used the Fourier transform kind of thing, and he wrote, you associate with any wave a function like this psi xt, and you expand it in terms of Fourier transform, and then define this omega as the energy divided by angular frequency, energy divided by h cross. So energy, what is energy? Energy is basically so p square by 2m plus kinetic energy plus potential energy. And a little of algebra would tell you that in fact IH cross d psi by dt is this, which we now understand as the time dependent Schrodinger equation. And you can also go to time independent Schrodinger equation, which you solve for various kinds of potentials like hydrogen atom, simple harmonic oscillator, etc., etc. And soon after this development of these mechanics by Schrodinger, Schrodinger himself also showed that my mechanics and Heisenberg's mechanics are equivalent. As you all know, you can solve actually simple harmonic oscillator by operator method as well as Schrodinger's equation. So obviously they are equivalent. So that is how we have a development. And then Max Born, who was actually working as head or professor at the Göttingen University that time, with whom in fact Heisenberg was associated. So he came back from the Helgoland island, submitted the paper to Max Born. Max Born looked at it. He immediately understood that this is matrix mechanics, sent it for publication. Then he, Jordan, and his PhD student and Heisenberg wrote 2 more papers the same year. So anyway, this is how the mathematical formulation of quantum mechanics developed. But later on, Dirac and Neumann, they wrote 2 books. Dirac wrote it in 1930, Principles of Quantum Mechanics, and in 1932, John von Neumann actually wrote down his mathematical principles and mathematical foundations of quantum mechanics. And these 2, in fact, would set out what we now call linear vector space formulation of quantum mechanics. So where we take the physical system as a linear vector space, the quantum states as quantum states as the vectors, and the physical observables as operators, and then develop it. You all read it in this. So this is how the mathematical formulation of quantum mechanics was established. But what did we lost in this process? We actually first lost determinism. In classical mechanics, whatever we measure, in principle, everything can be measured to any accuracy. But in quantum mechanics, that is lost. You cannot really measure anything to any desired, any accuracy that you like. In fact, there is a minimum accuracy given by the uncertainty principle. If you, for example, measure position very accurately with infinite accuracy, the measurement of momentum goes away. You learn nothing about it. Similarly, the other way around. So that you lost. You also lost objectivity. So that means even if you are not observing a particular thing, then that particular thing has certain existence with well-defined characteristics. That principle is lost. Here actually comes the fact that to know about a physical system, you have to observe it, you have to measure it. Before measurement, you practically know nothing about the physical system. So this is nothing to do with the observational apparatus or the observer, but this is the intrinsic property of a quantum system. And the third thing that which I don't really very much understand, we have experts here, is the locality. But as far as I understand, anyway, that will be a matter of discussion. As far as I understand, I think there is no violation of locality. What we really see in quantum mechanics is a correlation between states, and that correlation is never lost. Once it is, that is what we call entanglement. So, I mean, I don't have much time. So, but that correlation is something which actually probably leads to a false notion of loss of locality. But anyway, so we have lost determinism, we have lost objective reality of physical system, and I don't know, there's perhaps some loss of locality also in quantum mechanics. So, but we have not lost everything. In fact, all these that we have got in quantum mechanics are also well rooted or well connected to things that we know in classical mechanics. For example, in commutators, we see the presence of kind of Poisson bracket. In the Schrodinger equation, we also see the image of Hamilton-Jacobi equation. In the Bohr's correspondence principle, we also see that how if the quantum numbers associated with the quantum system are large, we also see the classical behavior of that system. So anyway, so this is more or less the story of quantum mechanics that I wanted to tell you. And then it goes to relativistic quantum mechanics, then to quantum field theory, and quantum field theory happens to be the most modern mathematical formulation at our disposal to understand the fundamental interactions of nature. Strong electromagnetic field. Gravitation is still out of our reach of quantum mechanics. Okay, so I think I will stop here. Thank you very much for your attention.
Thank you, sir, for a nice lecture on the foundational aspects of quantum mechanics. In the interest of time, we will take just one or two, maximum two questions. Please, students. So this is one place you can ask questions without thinking about what will happen in the grades. Okay, so please, this is for you. Okay.
You can reserve your questions for later speakers.
Yeah. No, okay, so there is one question.
Yes. Yes, please.
Sir, I just wanted you to expand a little more on your opinion on locality or the violation of locality.
That's what I am very unsound. Locality, I mean, see, normally in relativity we would say that nothing would no information, no signal would move or pass with a velocity greater than the velocity of light and vacuum. If there is a seeming violation of that, if there is an instantaneous interaction, then you would say it's a loss of locality. But here in case of quantum mechanics, for example, you might be doing, when you write the spin zero state as 1 by square root of 2 times, let's say, first particle up spin, second particle down spin, minus first particle down spin, second particle up spin, and you start observing it, then it suddenly collapses either to the first product or to the second product. But so if it collapses to the first product, let us say, of the first particle is down spin, so which means automatically, irrespective of the distance from the observation, the second particle will have up spin or down spin, the opposite. So that people probably call as non-locality, but that is actually not one particle sending a signal to the other particle. It's more of a correlation between the two particles than any information moving from one particle to the other. So therefore, in the very strict sense, there is no violation of any signal moving with a velocity greater than the velocity of light. Instead, it's a correlational property. That's all I understand. Maybe there are experts who would tell you better.
Thank you, sir. Thank you, sir. Okay. So I think in the interest of time, we'll move on.
Okay.
So the organizers, please wait. The organizers have arranged this moment. Okay, so after this foundational lecture, I think the next important principle is superposition and entanglement, of course. So we have a very well-known researcher in the area, Professor Arun Pati. So he has been active in this area for last, I think, 35 years or so. A lot of, he's also very well known, and a lot of awards, among a long list of awards, I'll just name a few. He's a J.C. Bose National Fellow. He's also an elected Fellow of Indian Academy of Sciences, Bangalore, and he's also a Fellow of the National Academy of Sciences, Allahabad, and so on. So let's welcome Professor Pati with a round of applause, please. Thank you.
Is it audible? Okay, so good morning, everyone. So, and thanks to Professor Tapan Mishra for inviting me to this event. And I'm happy to be here, and also a great pleasure to meet many old friends and old colleagues here. And also, you have heard from Professor Singh about historical development of quantum mechanics till 1925, beginning from 1900. So what I'm going to do now is tell you the most important discoveries that have happened between 1925 to 1935. Okay, so that had to do with quantum superposition and quantum entanglement, and which are key resources in latest area of quantum computing, quantum information, and quantum technology. So I don't know if you have heard of those terms, but we will be using these very often once you enter this new area of quantum computing. Okay, so So as you already heard from previous talk, the new quantum theory emerged from from this development of wave mechanics and matrix mechanics by Schrodinger and Heisenberg. But before that, the key concept that was proposed by Louis de Broglie, so-called wave-particle duality, that played very important role, because that is the notion that kind of fuel Schrodinger to ask the question, what exactly every entity is a wave and a particle, then what is the equation of motion that actually governs the wave? That's how we came to this idea of the wave equation. And between 1925-26, Schrodinger and Heisenberg, they developed the matrix mechanics and wave mechanics. And in 1927, Heisenberg also tried to formulate the Heisenberg uncertainty principle and tried to interpret it, as already you have heard from previous talk. That is a notion which tells you a clear demarcation between classical world and quantum world. Okay, and around same time, the Copenhagen interpretation came, because when Schrodinger developed his wave mechanics, it was not clear exactly how to interpret the wave function, that enters in the Schrodinger equation. But Max Born, he came into picture and he gave the probability interpretation, and that's where the probabilities enter into, the quantum theory. And not only that, there is an element of randomness also appeared in quantum description, because when quantum system evolves without any measurement, they obey Schrodinger equation. But once you do a measurement, the state collapses to one of the eigenstate that you're trying to measure, and that happens with some probability. So probability enters at the time of measurement. So these two incompatible description also, appeared, when the theory is being developed, And in 1935, Schrodinger also realized a weird notion, so-called quantum entanglement, and at that time he could see that how this notion makes a complete departure from classical line of thoughts. And that is a strange feature that you don't see in classical world. I will come to, I will come to in more detail about these notions later. I'm not going to use any equation, because Tapan told me that not to use any single equation, only tell the stories. So I'm going to tell only stories. Okay. So the idea of superposition was developed with the birth of quantum mechanics, as you know, in the early 20th century. And Schrodinger's equation played a very key role in trying to give this, notion of superposition. And some of you already might be knowing, Schrodinger was trying to extend the notion of superposition to larger and larger objects, and he came up with the thought experiment where a cat was inside a box, and there is a radioactive element inside the box, and there is a poison. So if radioactive element start decaying, this poison will break and that will kill the cat. But if it's not decayed, you don't know. So if you don't unless you open the box and see it, the cat could be in a superposition of living and dead. Okay. So if you extend the quantum mechanical superposition principle, you could also extend to the macroscopic living objects, and that could lead to a situation where you see that your living object could be in a superposition of living and dead. Okay, so that is kind of weird thing also happening because of quantum superposition. So, and this is still kind of a lot of debate still going on. So, but this is kind of issue is there since the birth of quantum mechanics. So, what exactly is superposition? So, if you are already, students already have learned quantum mechanics, you know what exactly it is. But basically, this tells you that any quantum entity that you think of, whether electron or photon or proton, anything you think of, they can exist in multiple states at any time. Okay, so what it means is that if you identify two or more possible states of a quantum system, the same system can also remain in a superposition of all those possible states. Okay, in a simple way of saying is this is essentially superposition principle. Okay, at the heart of this idea. So if you think of electron spin, you know it has spin up state, spin down state. That is perfectly fine. But then, because of this superposition principle, you could have a state of electron spin which is both up and down. Okay, so you have some amplitude of being up and some amplitude of being down. Okay, that is basically rising due to quantum superposition. But if you try to look at it by doing some measurement, you will see that the superposition will collapse to one of the eigenstates of either up or down. Okay, so that is the very famous, so-called quantum measurement, issue. Okay, so you can. So what I just said is you identify two distinct states of electron spin, spin up, spin down state, and because of quantum superposition, you could have a state which looks like alpha up plus beta down. Okay, this is state which is neither up nor down, but it is both at the same time. Okay, both up and down. Okay, but if you do a measurement, you will see either up and down. Okay, so this is essentially due to quantum measurement. Often it is called collapse of the wave function. Okay. So to really appreciate how quantum superposition is playing very important role, you have to come to so-called quantum interference experiment or the standard double slit experiment. Okay, that already you are familiar, right? So imagine that there is a source that emits particles one at a time. Okay, and in front of the source there is a wall with two narrow slits, and then you put a detection screen. Okay, so behind this screen, behind this slit there is a screen that records where the particle will hit. And what you would expect? If you think in a classical way, you will think that like if you're throwing say bullets one by one, so you will see that some of the bullets will go through one hole and other bullets will go through another hole. And if you wait long time, you will see that two humps or two bright bands, on the screen. Okay, the classical way of thinking about the situation. So this is like spraying paint through two holes in a fence. You will see two stripes on the wall. Okay, so classically, if you do this experiment, you will see two bumps on the screen. Okay, but if you do the same thing with the wave, what do you see? You have the source here, you have a double slit setup here, and you have a screen here. Then what you see is you see not two humps here and here, but you see an interference. Okay, that already you know. Okay. Now the next question is, what will happen to quantum entity if you send electron one by one or photon one by one? Do you see two humps or do you see an interference? Okay, so that was the question raised during that time, and obviously you will imagine that if your entities are both wave and particle, that means you should see an interference, right? Does it really happen? The answer is yes, it does happen. Okay, so what actually happens is if you send particles one by one at a time, after many particles hit the screen, you see an interference pattern. Okay, why? You can say that okay, they are waves, so these waves interfere. So each particle behaves like a wave that goes through both the slit at once, and this is your quantum superposition because each particle at any given time they go through both the slit and hit the screen. Okay, at one point. But the second twist is, if you try to measure which slit this particle has gone through by putting a detector behind the slit, you will not see any interference. Okay, you will see again two humps. Okay, so this tells you that just by observing which path information in the interference setup, your quantum system changes from wave-like to particle-like. So it is like as if this quantum entity knows that if you observe me, I will behave like a particle. If you don't observe me, I will behave like a wave. Okay. So, uh, but if you ask the question how each entity goes through both the slit, we still don't know. That is still a mystery. Okay. And it is not that you send many particles and somehow some particle go through this, some particle go through this, and you see the interference. No, it's not that. People have done actual experiment, okay, and they have ensured that at any given time there is only one particle going through this setup from source to screen. Okay, that already has been done, and at each point of time you see only one particle going through the setup. That means the single particle somehow goes through both the slit. Okay, how it goes, we don't know. Nobody knows. Okay, so you can see this from the famous quotation by Richard Feynman. This interference is a phenomenon which is impossible to explain in any classical way, and which is in the heart of quantum mechanics. In reality, it contains the only mystery of quantum mechanics. So let me pause a few seconds and tell my own journey. I thought of becoming a scientist because of the wave particle duality, because of this quantum interference. Why? Because I thought there is something wrong with the rules of quantum mechanics and I should change it, So that was kind of motivation. And when I first learned in this wave particle duality in BSc, my BSc bestmate, Dr. Arvind Rath is here, so he knows. So, when it was taught in our BSc level, at that time, probably we had hydrogen atom and no Schrodinger equation, nothing. Only wave particle duality was there. Okay, but still, I was so much motivated. I thought something wrong with this. This wave particle duality. That is something deeper than this, and I should explore that. And that's how I thought. No, I should do research in quantum mechanics only, nothing else. And then I pursued my career in in physics and doing quantum mechanics and so on. Okay. So why I sort of telling you this story is because whatever you learn in your textbook, is not the final thing. Okay, there is always something beyond what is written in your textbook. Okay, so let me tell you another example. Okay, so already Professor Singh has mentioned that Heisenberg discovered the uncertainty principle, and little later, just 1 or 2 years later, Schrodinger, Robertson, and Kennard, they also discovered more general form of uncertainty relation. And that's what you learn in your textbook, right? For last 80 years or so, till 2014, we knew only Heisenberg, Schrodinger, Robertson, and Kennard uncertainty relation. Okay, but in 2014, myself and one of my colleagues, my collaborator in Italy, we discovered a stronger version of uncertainty relation which goes beyond Heisenberg relation. Okay, that means there is something more than that. Okay, and that has new features, and and you can show that the Heisenberg relation is a special case of the relation that we discovered. Okay, that means the relation that you read in your textbook is not something final. Okay, you can always look beyond that. Okay, and by the way, when you discovered that in 2014, did not just we did that in 1 year, 2 years. This thought was there in my mind till from days of my MSc days. Are you thinking what exactly can we go beyond this? Can we do something better than this? And then the answer came in 2014. Okay, so you see, I mean, you should feel motivated whenever you read something, something new and something beautiful. Okay. So coming to this wave particle duality, already you know that light behaves like wave, already discovered by Young's double slit setup in 1801. about this wave particle duality for a matter or electron was experimental done by Davidson and Gerber, already you know, and they tested during the experiment with diffraction of electron, and that actually proved the wave nature, and this journey continued. Very recently, people have tried to see this wave particle duality for larger and larger number of quantum systems. Like this group in Vienna, they have carried out experiment where they could see the interference molecule, and this is the largest entity for which you can see the double slit experiment. And each of those entity comprise of 2,000 atoms. You see, this is really a huge system, and you could still see the interference. And the mystery continues. I just said, these quantum entities, are they truly wave or truly particle, or something else? Who knows? We don't know. Okay. So the wave particle duality is still one of the most intriguing feature of quantum theory, and the research, the people working in quantum foundation or quantum mechanics still don't know what exactly these quantum entities are. Okay. And such a duality supposes that quantum particles is any quantum particle is, I should not say particle, every quantum entity is accompanied by wave that is both particle and wave are assumed to exist objectively. Okay. Then few years later, we asked the question: can you really separate wave from particle, or they always exist as a whole? Always. Then we thought of designing an experiment, and a proposal that we came up. Yes, indeed, you can separate the wave and particle. That means you can design an interference setup where you send the quantum entity one by one, and in one path of the interferometer, the wave goes, and in other part of the interferometer, the particle goes, and then we see the interference. That we proposed, and actually people did experiment and verified the idea. So here is a question. You have this entity, and sometimes we have a wave, sometimes we have a particle, but we propose this experiment where you can actually separate these two aspects. Okay. And this was done by one of my visiting student and myself and my collaborator in China. And this group in China, they actually did the experiment, just 2 years back. Okay. And here you see again, I'm not going to details. So this is experimental setup where you send the entities one by one, and this you see the wave in one side and particle in another side. Okay. This is actually possible. Okay. Now I go to quantum entanglement notion. Again, I told you the notion was already there way back in 1935 due to Schrodinger. And in same year, Einstein, Podolsky, and Rosen, they tried to use these entangled states and to argue that quantum theory is an incomplete theory. Why? Why they did that? Because Einstein, even though he played a very major role in development of old quantum theory, but when the new theory was developed, he was not very happy with the interpretation and probabilistic element that entered quantum theory. Okay, he was of the opinion that everything should be local, everything should be determined, and nothing. And as you know, his famous quotation that God doesn't play dice. So he was having very classical world-like view. So he came up with a proposal where you can use these entangled states and argue that quantum theory is not a complete theory. There is something beyond quantum theory. Okay, and these entangled states display very strong correlation, as Professor Singh was mentioning. They display very spooky action at a distance, and that worried Einstein. But now we know that even though they are spooky, they are not that they are not that strange, because you can use the entangled state in quantum computing and quantum communication and many other things. Okay. So here you see Einstein, Podolsky, Rosen here, and these entangled states, as I said, they display strong correlation between space-like separated objects and particles, and we can use them for quantum computing and quantum communication. I will not have time to go through these two areas, in more detail, but I will tell, I will just touch upon these notions. Okay, so here you see a picture where two particles, they are far separated in galaxy and they could still be entangled. Okay. So what exactly it means? It means that when you have two or more particles in an entangled state, they are connected in a strange kind of manner, I'm not going to write any equation, so I will try to be very heuristic, very, intuitive way of telling you these ideas. And basically, if you have an entangled state, individual particles are not independent. And you can always write a global wave function for the joint state, but you cannot write a wave function for the individual state. Okay. In quantum theory, you know that one of the postulates of quantum theory tells you that for any quantum system, any quantum particle or quantum entity, you can associate a wave function. Okay. So when you have entangled state of two particles, the joint state does possess a wave function. You can write a wave function for the joint state, but if you want to write the wave function for this and this, you cannot do that. Okay. So then you say they are intertwined, they are connected, they are correlated in a very strange kind of way, and that is basically your entangled states. Okay. And as I said in the beginning, these kind of states very weird. They display very weirdest feature of quantum world. But now we know that you can use them to do something amazing, something beautiful, which you cannot do with classical world. Okay. So entanglement appears when two more particles become linked. Knowing the state of one particle instantly reveals the state of the other particle, even if they're far apart. So as Professor Singh already mentioned, that think of two spin-up particle. Okay, in an entangled state, like spin up down, say plus or minus down up, and you take one, keep one particle here, take the other to the say moon or Mars, anywhere you like. Okay, so if you find this particle is spin up, immediately you will know that the other particle is spin down, and vice versa. Okay, what only you know. Okay, the other person still doesn't know. So it's not that by knowing you are able to communicate faster than light. No, it's not that. Okay, so the communication, you have to inform the measurement outcome from here to the other person who is at a distant location, and then only he or she will know that his particle or her particle is up or down. Okay, so even though this is a strange correlation, strange thing happening, but there's no communication happening faster than light. Okay, sometimes people get reading news articles, they get miscommunicated or misinformed that entanglement helps you to do strange, communication faster than light, but no, not that. Okay, that never happens. So entangled particles act as a single system, and their properties cannot be disturbed independently. So a classical analogy would be something like this. Imagine a pair of globes. You put one globe in Mumbai and other in London. If you find the right globe in Mumbai, you instantly know the London globe is left. Okay. If you think of quantum entanglement, this analogy is much, much stronger, and that works even across huge distance. And just to tell you how strong these correlations are, that if you try to model this kind of correlation using local realistic description, then you cannot do that. That is the work of John Bell, and that's how the Bell's inequality was discovered. And from 1935 till 1966, thousands of papers being written, trying to resolve this Einstein-Podolsky Rosen paradox. Okay, but those are mostly philosophical discussions or some back and forth comments and so on. But there is no concrete way to prove or disprove Einstein. But John Bell came up with a very simple idea that he assumed that, okay, if you do something here and that doesn't affect the other particle, that is essential locality. And reality means the property of the quantum entity does not depend on the observer, that exists independent of your observation, that is reality. Okay, so if you take these two things into account and tried to derive some correlation between this and this observation. Then he found a new bound, and that bound is violated in quantum mechanics if you use entangled states. That is a Bell violation. Okay. Again, I'm not going to detail about that is another story. So that's how this correlation is very, very strong. And the 2-3 years back, people who did actual experiment in Bell violation, other things, they actually got Nobel Prize for that. Okay, so again, this is just to show how if you have more than 2 or 3 and n number of particles, they could be entangled and correlated in a very strongest possible way. And what can you do with superposition and entanglement? If you ask this question, you can do many things, because superposition allow your quantum computer to perform calculation instantaneously, simultaneously, and you can use the parallelism that gives a power to quantum computer, and that has huge potential, and that gives a speed up for certain tasks compared to classical computer. And entanglement lets your quantum bits set information in a way impossible for ordinary computer. In quantum communication, entanglement, they enable quantum teleportation, quantum key distribution, remote state preparation, and many secure communication protocols. So this is, you may hear a little more about these notions, by Professor Bhanuda's talk, or maybe Professor Bhagande's talk, and many others maybe. But I'm not going to tell too much about these. Just I will touch a little bit. Okay, so just to tell you a glimpse of this emerging area, think of your classical information. So in classical information, you store your information in zeros and ones, and all present-day computer you do store in bits. Okay, and essentially you identify 2 possible state, and you say this is 0 or 1, and then you do various tasks using classical laws of physics. But if you ask to do same thing in the quantum system, what will happen? Okay, this question was raised by Feynman in 1982, and David Deutsch, he took this idea very seriously, and he developed this whole theory of quantum computing in 1985. And the basic idea he used is the quantum superposition. Okay, so that is the clear demarcation going from classical bit to quantum bit. Okay, so he said, okay, you store information in say a single electron, spin up and spin down. Spin, if it is up, you say it is 0. If it is down, you say it is 1. But then we know that this electron can remain in both up and down state. Okay, that means if you translate this into logical language, you have a state which is alpha 0 plus beta 1. Okay, so that is basically your quantum bit. So quantum bit basically is any 2-state system in a superposition of 2 distinct states. Okay. So, a quantum computer simply is a device that performs computation using principles of quantum theory, the ultimate theory of nature. So, as I said, he is regarded as the father of quantum computing. Okay, David Deutsch. And as I said, your classical bit will be only found in 0 or 1, but quantum bit can remain both in 0 and 1. And you can think of quantum bit like spin or proton polarization or 2 atomic level and anything else. Okay. And this inherited parallelism you see here is responsible for new type of computation. That's what we call as quantum computation. Okay, this is emerging area that you hear now. Okay, now if you think of 2 quantum bit, what happens? Classically, you can have 0, 0, 0, 1, 1, 0, 1, 1. Quantum bit, if you think, you can also see that they can remain in 4 logical states, but they can also remain in simultaneously all those 4 logical states. Okay, so if you have n quantum bit, classically, sorry, if you have n bit, at any given time you will find only in one of those possible logical states, but your n quantum bit can remain in all those possible logical states in one go. So if you think of n equal to 300, that is roughly 10 to the 90, then more than number of atoms in the known universe. So you see how vast your quantum computer state space is. So quantum computer state space exploits all those exponential number of logical states in one go and try to do computation. That's how you see the massive parallelism or massive advantage in quantum computer. Okay, so quantum computer takes the advantage of this exponential number of logical states, leading to massive parallelism. Now, quantum information is a big subject, that has emerged over the last 30-35 years. But the larger goal in this area is to ask the question how well you can store, process, and transfer quantum information using principles of quantum mechanics. Okay, and quantum mechanical features like superposition and entanglement are exploited for practical applications and for doing amazing things which are impossible otherwise. And that is the reason understanding superposition and entanglement is the key to next generation technologies, from faster computer to unbreakable codes and better scientific discoveries. And learning these ideas now puts you ahead in the exciting world of quantum research and its countless upcoming applications. Okay. So before I end, I thought I will tell you one of the beautiful applications of quantum entanglement in so-called quantum teleportation. Okay, teleportation is a very fictional thing that you might have seen in Star Trek or maybe in sci-fi movies, that there is some hi-fi device. You enter, a person enters and switches a button, and he disappears from here and appears in another planet. Okay, so teleportation dictionary meaning is destroying an object in one location and recreating the same at a distant location. Okay. Now, if you want to ask this question for quantum entity, can you do that? Before 1993, it was thought that no, you cannot do that. But then, thanks to quantum entanglement, people realized that yes, it is possible to do quantum teleportation. So, the first proposal came due to these six scientists you see here: Charles Bennett, Wouters, Rich Dosa, and Brassard, and a few others here. So they proposed this teleportation idea in 1993 using quantum entanglement, and then 4 years later, this group they did the first experiment in Vienna, in Innsbruck, in 1997, over a tabletop experiment, teleporting a single photon over 1 or 2 meter distance. Okay, and why I thought of showing this picture, because this person you see behind standing there, he is none other than Anton Zeilinger, who got the Nobel Prize in 2022. Okay, and here you see J.W. Pan. He is leading the China's quantum science technology mission. He is one of the leading figures in China. And here you see Dick Buckminster and few others here. And Anton Zeilinger and Ellen Aspect and John Clauser, they got Nobel Prize for their experimental testing this Bell violation with entangled photon and quantum teleportation and many other things. This is not just for single work, but for combined various works. Okay, so I think I am done now. So now I'll try to summarize what I said. Quantum world, as I said, it has strange features. It has many strange features, but you can pinpoint two features which gives rise to all other features. Okay, so that basically superposition and entanglement. Okay, and superposition and entanglement, they give rise to many non-classical features, and they are also backbone of quantum information science because they enable you to design new kind of encryption, faster calculation, and technological feats that could revolutionize physics, chemistry, materials, and beyond. Okay, and not only that, superposition and entanglement also help to rethink foundational questions for exploiting technological revolutions. Okay, so with that, I come to end. So continue to explore unexplored. Okay, so thank you.
Thank you, sir, for a wonderful introduction to superposition and entanglement. We can take 2 questions, maybe. Yes, please.
So this quantum entanglement is understood, it is the non-local correlation between two particles. So it was our experimental also proven.
Yes.
So recent there is a new concept called single particle entanglement in multimodes. So like if you put photon in a beam splitter or something like that, so then there will be two polarization of the same photon, and there will be some thought about how they can be entangled. So can you have a thought about?
Yeah, so entanglement is not just between two or more number of particles, but you could also think of between two or more degrees of freedom of the same particle, or you could also think of entanglement between say polarization and say path, okay, of same single particle. And as long as you can identify two or more distinct degrees of freedom of a quantum system, you can think of quantum entanglement between those degrees of freedom also. Yes. Yeah.
Okay, very well.
So you talked about the experiment relating to separation of the physical states of wave and particle. So in there, what do we exactly mean by the physical separation of those two states, and how can we ensure that one of those separated states won't act like the other at a later stage?
Yeah. So this is slightly, I would not say slightly, this is very technical paper. I did not want to go to detail, but basically what you do is you create a state where you superpose wave aspect and particle aspect. It is going slightly beyond the wave particle duality in some sense, okay, because uh, superposition basically, as I said, was born, and the basic idea was born due to wave particle duality. But now, over the last couple of years, people are trying to propose a scenario where you can have an entity which is the superposition of both wave and particle. So you can think of a state where it is alpha wave plus beta particle, okay, and then sending those kind of particles, and by suitable designing measurement on this two arm of the interferometer, Mach generator interferometer, you can design this setup so that you see the wave amplitude going here and particle amplitude going there, then you see the interference. So, I mean, this is just slightly, and those measurements are something called weak measurement. Another, another technical thing. I didn't want to go into detail.
Sir, sir, what role does the means quantum entanglement play in quantum teleportation and quantum communication?
Sorry, I could not hear. Can you repeat, please?
What role does quantum entanglement play in quantum teleportation and quantum communications?
Yeah. So in quantum teleportation, what happens is we have two-person Alice and Bob. Okay. Your goal is to teleport an qubit or a quantum entity. Say, think of single photon. Right? Teleport a photon from here to here without physically sending this photon. Okay. That means you don't put the photon inside optical fiber or don't put the particle inside box and send it by courier. No, not that. Okay. So what actually happens is this entanglement acts like a channel. So it is a channel. Somehow this information goes from here to here miraculously without physically going through this distance. Okay. So entanglement is an invisible link. You can think of like an invisible link through which information passes through, and that itself is not enough. You have to also send, that is some technical details also. So you have to do measurement here and send the outcome from here to here over classical channel. Classical channel is like your ordinary channel, like telephone or internet, or or you can send a fax or something, or just ordinary channel that you use. And by doing this dual channel, this quantum channel and this classical channel, you can destroy the particle here and create here. Okay, that's how it helps. Okay.
Does it,
Yeah.
sir? Does it violate the Einstein's theory of relativity, which
No, because
which is
because to recreate this, once this disappears from here, once to recreate that this distance, you have to send the classical communication, and that had to obey the speed of light. Okay, you cannot do faster than that. Okay, that is why this is not instantaneous. This had to respect Einstein's special theory of relativity. Yeah.
okay? Thank you, sir.
Okay, thank you, sir. I think we are running a bit too late, so please interact with Professor Pati during the tea time. We are breaking for tea, sir. Okay, so thank you, sir. Let's thank again Professor Pati.
Thank you. Thank you.
A small memento. Thank you.
Thank you. Thank you. Thank you. Mm.
We'll be, so we are breaking for tea. We are breaking for tea. We'll gather back again in 10 minutes. We are running late actually. Please help in this matter. Okay. Please, outside there is tea and snacks. काय घेत आहे?
Come quickly as possible and take the seat. We'll start the session. Already we are running out of time. Yeah. In this session, we have three lectures. The first lecture is by Professor H.N. Ghosh, Director NICER. Let me introduce briefly Professor H.N. Ghosh. Professor H.N. Ghosh did his master's from IIT Kharagpur, and followed by he joined as a scientific officer at DRC Mumbai, where he has held various positions at DRC Mumbai. Then he moved as a director at INST, that is the Institute of Nanoscience and Technology. Then he joined here as a director NICER, and last 3 years, last 2.5 years, 3 years he is in NICER. He has published various research articles, and more than 250 research articles he has published. And he also received various awards and honors. To name few, there are some of the things which is very close to his heart, particularly on recipient of Homi Bhabha Science and Technology Award in 2010, and recipient of DAE SRC Outstanding Investigator Award in 2012, and he is a fellow of all the three National Science Academy, and he is also a recipient of J.C. Bose National Fellowship in 2019 and 2024. CRSI Chemical Research Society of India silver medalist in 2022, and in 2023 he received elected as a fellow of the Indian National Academy of Engineering. And his area of research interests are ultra-fast spectroscopy, perovskite materials, 2D materials, plasmonic materials, and terahertz spectroscopy. Today he will be here. He will hear deliver the lecture on the topic of ultra-fast spectroscopy in the quantum world. I now invite Professor H.N. Ghosh to give a brief lecture for 25 minutes. I request all the speakers to stick to the time of 25 minutes. Then there will be a question and answer session for 5 minutes. Then we will go to the next speaker.
Hello? Okay. I think bring it a little down. Okay. Thank you, Professor Srinivasan. So, quantum science, what physicists and other chemists does, I'm here to in between why ultrafast spectroscopy is very, very important. To make any devices out of these quantum materials, you have to understand the physics behind mechanism, and by theory you can talk many things, but eventually if you don't do experiments, say for any photoexcited material, semiconductors, we talk of the electron hole, if you do not know how fast the relaxation process, transfer process takes place, actually you cannot do much. So ultrafast spectroscopy is extremely important in that matter. and that too in the quantum world. So first I must acknowledge my group of people. I'm not talking anything about whatever I've done in BRC. Last 7-8 years, I was out of BRC and then went back. So I have 2 laboratories I'm working. First is INST Mohali. These are the alumni people. And currently I have a group here. Manvi and Nitika, they're still working in INST Mohali. Okay. So, you know, I think you have already discussed about this International Year for Quantum Science and Technology. I don't want to talk much about it. In my language, I just want to tell what is quantum science. Explores the particles at the atomic and subatomic level. It introduces concepts like energy quantization, uncertainty principle, superposition. There are many things actually. Enable advancements in technology. This is a very important thing actually. As semiconductors, laser, ultra-fast sciences, quantum computing, it is very, very important to know the ultra-fast techniques to study the time scale. So, if you talk about the Eyring equation, the temperature dependent reaction rate, you know, this has done it, and these are the typical equation. You can see that at room temperature, if the delta G is 0, free energy of reaction is 0, and it can very easily cross over and reaction can take place. If you determine the rate, and if you invert it, you get the 160 femtosecond. That's the fastest time scale actually it can observe. But if you talk about the molecular system, bond is like 1 angstrom, and the motion of atom is 1000 millimeter per second. So the bond breaking time is 100 femtosecond. The question is that how to track the ultra-fast processes, the fast processes, okay? So, you know, this is a very nice experiment actually. Long before 1878, first stroboscopic experiment was done. The galloping horse, when they go, I mean, the ultra-fast person who has done that, they might be knowing it. It is available in the internet. When a horse run actually, you know, you cannot make out whether all the 4 legs is on the earth, or sometimes it goes up. So there is a curiosity. It was there, and the May Bridge, 1878 in Stanford. That time it might not be the some of the ranch actually they did the experiment and took 16 cameras. They are Sony F12, 16 cameras in different position, and they took the picture and find out that there is a time when all the 4 legs is up. So just imagine, this is the first time resolved studies, long before, almost 150 years back. So, I mean, evolution of time scale, you can see roadmap of ultra-fast spectroscopy. You can see the chemistry and biology in the line, like humans and kinetics, stop flow, relaxation method, lasers, photochemistry and femtochemistry. This is a different time scale we observe. So, I must tell you that how the roadmap happened. Invention of our first working lasers by MIMEM, based on theoretical work by Charles Stoynes and Arthur Leonard. Is a first patented Gordon code. In 1976, first femtosecond pulses obtained using colloidal pulse mode locking, CPM. And 1981, RL4 and B.I. Green, C.B. Shank. Actually, Nobel Prize for this femtosecond pulses was given to Ahmed Joel. To my knowledge, actually, 2 persons they have ignored. One is C.B. Shank, another is Robin Hochstetler. Robin Hochstetler was the guide of Ahmed Joel. So they actually demonstrated the ring cavity get the shortest pulse, 90 femtosecond, and using that concept, you know, Robin Hochstetler built mid-infrared, and later on, using that concept, this Ahmed Joel, he actually got the Nobel Prize and demonstrated some experiment. So before the chart pulse amplification demonstrated by Stickard and Gerard, and they also got Nobel Prize 2018. And as I was telling you, Ahmed Joel, he got Nobel Prize in 1999, and he actually did wave packet dynamics. That's the first time he demonstrated to the common people. Earlier, the smartest thing what he did, he actually shown to the common people how the wave packet actually move in the potential energy surface. And you know, last year, Nobel Prize in Physics, he got it actually, 1 second pulse. So this is a Joel's experiment. If you take sodium iodide and a photoexcite it, and then it's go to the excited states, and then you monitor the wave packet dynamics, you can see that at excited state, sodium and iodine they break, and you can check the wave packet that it is coming down, and there's the sodium is going up. So very fast time scale they have measured. The breaking time of sodium iodide got 1.25 picosecond. So before coming to that, more talk about the ultrafast today, let me talk a little bit about the confinement system of molecules and materials. I mean, actually, Indian, the people when they make a steel sword, through this process, you can see this. And people say that Alexander did not come to India for gold or silver. He came for this metal, and also this plasmonic gold material. You can see there's a different color. You change the size of the gold, you can find different color of glasses. So quantum dot journey starts, as I was telling, that ancient India. In 1959, Feynman talked about the plenty of room at the bottom, and then the DFT calculation, they discussed something, and then 1980s, Ekimov and Brass, actually, a very interesting experiment they have done. They have done, like Ekimov experiment, I remember, he changed the size of the particles and do the redox, and then find out the energy, conduction band energy is different, and the redox ability of the electron is different and depending on the size, okay? And later on, size quantization effect, Brush actually did it. And 1990, first DFT code is written by Wienert. And early 90s, again, Bawandi synthesized this cadmium sulfide, cadmium selenide material, size dependent. And later on, taking that material, people talk about the many quasi-particle story, exciton and biexciton. And then 1998, ultrafast dynamics of the quantum dot material was first demonstrated by Klimov. Although I have started ultrafast experiment much before 98, 93, but that time we used to do only molecular. But Klimov first demonstrated the quantum dot ultrafast spectroscopy in 98. And you can see that 23, these three gentlemen got the Nobel Prize, Ekimov, Brush, and Bawandi. There are a lot of applications. I'm not going to talk much. Photovoltaic, storage battery, mobile display, LED lights. This everybody talked about this quantum dot solar cell, and this picture people they saw, and the solution people think that perovskite to the tandem silicon tandem solar cell is efficiency is getting like 32%. And remember, all the concept comes from confinement effect. In Chandrayaan, the solar cell, what they have sent it actually, that is also made of quantum dot material. The problem was that in the night it did not work because the solar light was not there. So the next project, atomic energy is pitching in, where they are going to make battery, where even in the dark conditions that will work anyway. So if you see the TV actually, LCD, so many components are there, and the clarity was not there. When come about the LED and QLED, you can see these days, this Samsung already built a QLED, and resolution is much better. So this is very interesting study. You take one material, cadmium selenide, change the size actually. You can see the entire color actually. For this work actually he got the Nobel Prize. Now to study spectroscopy, there are many optical methods. Transient absorption, which is actually in NISER we have recently developed. The upconversion, it is already there, and then microscopy, maybe someday microscopy also will be installed in NISER, and there are many more things can be done. It is very important to build this laboratory. It is you can have a laboratory, and if you do not know how the laser works, actually you cannot handle. So in India, those who does ultrafast spectroscopy, you can tell them that they are half engineer. So today I'll be talking something, one lab which is still working in INST Mohali, and this is NISER Bhubaneswar. So what we do, It's a pump probe experiment. You excite the sample with a pump beam, and the excited species actually can monitor through the probe beam. This is the transient spectra, which is basically talk about the structure. Talk about the structure, and this is the dynamics, and that's the way it can do that. Sorry, I'll come after half an hour. So that's the way actually you can monitor the kinetics and dynamics of a system after photo excitation. So if you talk about this, there is a one line here. You monitor this across this, you get the spectrum, and if you take this way, you can get the kinetics. So both structure and dynamics of a system through a transient spectroscopy can do it. So last 7-8 years actually I'm involved in these activities. 2D material, perovskite, plasmonics, and heterostructure. And here in this slide, I'll take a little more time. So I'll be talking about quasi-particle. I mean, I'm sure you guys are talking about the electron, proton, neutron. I'll be talking quasi-particle. So when you take a semiconductors and you make a device, you photo excite it, you really bother up the electron and hole and charge separation. But other than this charge separation, I mean, the electron and hole, there are many more things are happening which you really did not know. First thing, let me talk about if you take a standard band gap material and excite it, it through thermalization, it comes, the electron comes here, hole comes here, and due to the Coulombic interaction, you make an exciton. And any normal semiconductor, you can do it, get it. There's something called bi-exciton, where if the band gap of the material is a very small, and if the photon energy, say for example, band gap is 1 electron volt, and you are giving like 3 electron volt energy, then the extra energy of the electron actually make impact ionization. So in a system on 1 photon, it can create 2 electron hole pair. That's called bi-exciton. This is something really new. I mean, transient spectroscopy time scale of the formation of trion and polaron. Trion basically 2 electron on 1 hole, or 2 hole 1 electron, and polaron I'll talk. So trion, this is another quasi-particle. This is the time scale how fast a trion can be formed on a decay. I think we are the first group who told about this dynamics. So what happens when you take a 2D material, its confinement takes place in the one direction, and when you photo excite it, first it generates a lot of free carriers. So immediately they do not form exciton. So because in the 2D material, the carriers actually move around, and then the carriers means electron and hole separately, and due to the Coulombic interaction, they form first exciton, and in the system still there will be exciton and free carriers. Now the exciton can interact with the electron or a hole and can form a 3-body species, and then you can make a trion, positive or negative. The another things I'll be talking to the polaron, which is another quasi-particle. So if you take a semiconductor, if the polarity of the material is high and it's a soft materials, then when you excite it, you create electron and hole. Now, as I'm telling you, the polarity of the material is very high, and it's a soft material like a perovskite, then it emits tons of phonon. The phonon actually, they interact with the electron and the hole separately actually, and you can make a positive trion or negative trion. So basically, the electron or hole is jacketed with the tons of phonons, and the mobility of the trions actually basically slows down. So it is very, very important when you make a devices of any of the perovskites. It's very important to know you don't think that you are only creating electron and hole. At the same time, depending on the polarity of the material, you can create trions, which the mobility of the carriers actually slows down. It's very, very important to know. That's why we did this kind of studies. So today, how many minutes I have now? 10 minutes, 15 minutes? 10. Okay, fine. So a few quasi-particle dynamics I'll be talking. Another thing I'll be talking about the plasmonics, 2D material trion and exciton, and also in perovskite polaron. So plasmon dynamics, which I did not speak in the last slide. Those who are working the metal nanoparticle, if you excite the metal, you get a plasmon band, and there are multiple processes. I mean, if you take a gold particle and change the size, you can see the optical spectra changes. It goes to a bigger particle, make a kind of broad absorption, goes to beyond visible in NIR. And if you make a rod, actually, you can get 2 band. Actually, one is longitudinal plasmon band, another transverse plasmon band. And what happened actually when you excite it? First, plasmon resonance created, and first it diffusing time is very, very fast actually, 10 femtosecond. And there are first it will take electron-electron scattering, electron-phonon scattering, and then phonon-phonon scattering. This is the multiple process. So to make this material in the devices, this processes is very, very important to know. Today I'll be talking something different. It is not the metal nanoparticle. I'll be talking about this quasi-particle, not quasi, plasmon of semiconducting plasmon. What is semiconductor? Metal, you excite it, you create a plasmon, and that's fine. But if you take a semiconductor, say for example copper sulfide, what is the valence here? I don't know, physics student, you should know also. Copper is +1 and sulfur is -2. So when you see the formula actually, it is Cu2s, valence. Now what happens when you synthesize it, the copper sulfide, you add less amount of copper. So some copper will be converted to +2. So there will be situation, both +2 and +1 will be there. So in the copper, when there is a +2 formation, then the conduction band, the valence band, actually it will give the electron. So it will create a vacant state. This vacant state, actually the transition can take place. So just imagine you take a plasmonic material, a non-plasmonic material absorbs up to 950 nanometer, but if you can make it by adding less copper, you can get a broad absorption till 2, 3, 4, 5 micron actually. So it's very, very important to know how the relaxation process takes place. So we did like this, like if you excited a normal semiconductor, you get exciton. But when you excite the plasmonic semiconductors, you create photoexcited hole here, not electron, and the relaxation process takes place here. So this is something actually we discussed, which is when you take a normal semiconductors, you get to talk about the interband relaxation, for conduction and valence band recombination relaxation process. But when you take a plasmonic semiconductors, you can see this when you photoexcite it, the photoexcitation takes place with a deep valence band electron and put in the vacant state, and this relaxation process takes place. Very, 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 very fast processes. Now I will be talking about the trion dynamics, which I talked of how the form trion, and also if you want to capture the carriers before the decay, actually you can put a gold particle which you can accept the electron. So here we can see that you can excite it, free carrier which I was talking it. First they form exciton, and then extra electron comes and form the three body particles, which is basically trion, and that trion actually the gold can take all the electron. That's the kinetics we are talking about. So in the transient spectrum, actually A and B, those who are working in 2D, you know what is A exciton, B exciton, and there is a positive band comes here. We are talking about the trions. We did a lot of things, and putting a gold particle, how fast the trion decay takes place, and that's what we have demonstrated. So in addition to that, the 2D material WS2, we talk about the exciton. There is something called high energy exciton. The dynamics of the high energy exciton is not much discussed or demonstrated. So if you take a WS2 material, you find A, B, C, D, and through ultrafast spectroscopy, we can talk about the all relaxation process. You find that C and D recombination process is very low because it pump into this state, where the Pauli blocking the recombination process is slows down. And finally, I'll be talking about the polaron, which I already talked. So if you take a normal semiconductor, you excite it, electron and hole, but then, when the electron goes, suppose the electron goes there, and these are like a ionic species. So cation and anion species is there. So when it moves the electron, it attracts the anion and it deflects the cation. Sorry, attract the cation and deflect the anion. So there is a movement of the ions. During that movement, due to that movement, actually, it emits phonon, and that phonon interact with the electron, the same electron, and eventually form a polaron. That's the idea actually. That's what I've written here. I mean, you can see this thing in Wikipedia. They have described about the mobility of these carriers actually. The trions will be much, much slower. So we did some transient studies and tried to discuss how fast the trion dynamics takes place. So you excite it, you have a phonons here, you form a polaron formation, less than a picosecond it is formed. then it decays in 2 picoseconds. Because once the phonon goes out of the system, and then actually your trion goes. I mean, without phonon, trion cannot be there. So within 2.5 picosecond, generally, or 3 picosecond, the phonon decays, you know, because as a heat, you know, if the sink, it goes, and your electron, your polaron become a normal electron or normal hole. And this is the dynamics actually we have shown it. And you have to take this kind of material, which is basically can high polarity and also it supports polaron formation. We have shown it. And when we do the temperature dependency, it's very important, the temperature dependent study of this kind of materials, because what we observe, if you see that I already talked about this polaron and 300 K actually, you can see the polaron dynamics. But as you decrease the temperature, eventually this polaron is not there. You know, this is a different things happen. I mean, it forms a excitonic states. So this time scale suggests actually that the polaron is decay within 3 to 4 picoseconds. Now, when you take about this kind of material and talk about the relaxation dynamics of charge carriers, so at 300 above temperature, the hot carrier cooling actually dominated by the polaron formation, but at low temperature, which is basically acoustic phonon come to the play at lower temperature, then acoustic phonon actually cannot form polaron. So, you know, it is dominated by the hot carrier cooling. And finally, you know what we did? We make a material which is basically in one case there is a less defect states and a little bigger, little more polar. And we found that in this case, like a cesium lead bromide, you know, dodecahedron, and then this is the nanocube. Nanocube actually normal, which is kind of a defect state. So in that case, we have observed the formation of polaron and decay is a different time scale. In this case, when the size of this is bigger and more polar, you don't see defect states. You can see that very fast the polaron can be formed. You can find this, and then the decay also slow. In this case, where the defect state is there, the bound exciton is formed. In this case, only free exciton. You can see the formation is slow and decays fast. I know we did some transient studies, as I was telling, the photoconductivity and mobility of those quasi-particles, what you generate actually in the system, how fast or slow. You can find it that cube one, which is basically this is nanocube. That is basically is much faster than that dodecahedron. So in this case, why it is slow? Because it's a bigger size, the slow, and also decay. I cannot say much because it's the noisy signal. But one thing is that the mobility is the bigger one is much slow. That's what we have observed. And thank you very much. I think I kept my time. Yes, I would like to have questions, because I think quasi-particle, polaron, trion, not many people have taught you in the classes. Yes.
We have one or two quick questions.
You know, this for 3 particle bound state,
yeah,
there is something called Efimov state, where 2 particles do not bind, but when third particle is present, they bind. Is it possible to see analog of that in case of trions?
Okay, trion, what exactly you want to do?
2 particles do not bind.
2 particles, what are the particles?
You know, it has been shown in nucleus. Efimov actually the nuclear physicist. They have shown it.
Nuclear, I'm not sure, because
they have shown it.
There's a much higher mass actually.
No, here experimentally has been shown cold atoms.
Okay.
I'm asking, is it possible to have a trion analog of that?
I cannot tell you actually. I don't understand how the cold atom is produced and what are the conditions. It is difficult to answer for me.
Physically, 2 atoms or 2 particles do not bind.
Yeah.
The moment you put a third particle, they form a bound state.
Okay. So in this case, purely due to Coulombic interaction. Okay. If you talk about the trion, right? So 2 electrons in 1 hole. So first they have to form the exciton, right? And then after the exciton, because already you are telling they cannot form, but here it is forming already. Now this exciton can polarize any electron in hole because it has both the charge actually. So there is a high chance they can make it. But as you are telling, 2 particles, they don't interact, you put something else. In this case, particles are anyway forming exciton. Okay.
Good morning, sir. Sir, this is Naveen from IIT. Hi, sir. Yes, sir.
Okay. Sorry. Yeah.
Sir, I just want to get some facts on what if we take a 2D material and what if we incorporate some TMD quantum dots into the layers of the stacked 2D materials, and how would it affect the, I mean,
2D, this 2D actually all TMD only.
Okay.
Yeah.
So
it's
like,
a WS2 MOS2 material.
What
It's
if
already
we,
TMD. What do you want to do?
what if I take SNO2 quantum dots?
You put on a quantum dot.
Yeah, incorporate in between the layers of the 2D materials.
Okay.
Then how would it affect the efficiency of the solar system?
No, once the dimensionality decreases, actually, if you, what I have seen it, 2 layers or maximum 3 layers, you can still see some, trion. But once the layer goes up, then in that case, what happens? The carrier, you see, when you have one layer, electron will move around. But when you have another 1 or 2 more layers, then there is a high chance that very fast the exciton formation will take place. And here in this case, there is a long time excitons are moving around actually. In that case, it will not be there. Electron and hole, and in 2 different layers, they can excite, indirect exciton that can form. So trion formation will be not be easy actually. If you have more than 2 layers, or maybe 3 layers, I have seen very, very low signal. 2 layers we have seen the signal is still there, but it has reduced. And the time scale of the formation of trion is also very fast, because it is lost at all. The signal intensity comes down and it decays also fast. Yeah. Sure.
No, the thing is, can I see one of your spectrum?
Which one?
I just wanted to see, yeah, anyone. You are showing different decay times in the same spectrum, right?
Yeah.
So it is like
A temperature dependent decay.
decay. So is it like you are doing one measurement and see all the decay times, or
No. We change the temperature in the cryostat.
No.
Yeah, it's the same sample actually. We keep on changing the cryostat, the temperature, and follow the kinetic.
I'm not talking about this one. The other one before that.
Okay.
Yeah, for instance, that one, E plus E minus, these are different flows, right?
Yeah, no, this is, I'm showing that how it looks like. The trion signal appear in, say, 640 or 50 nanometer. You monitor the kinetics. I just showed it actually. Not here. Yeah. See, this is around this place actually. This is the signal. And you monitor the kinetics there. And that's what you observe actually. This electron. So the phone electron and the tons of phonons will be there. And with time, it's not the trion basically. Phonon it's a heat sink and it goes in the system. It time scale is 3 to 4 picosecond. So 3-4 picosecond, phonon is gone and trion is gone. It will be bare electron or bare hole. Yeah.
Yeah.
Sir.
For qubit realization?
See, you are putting quantum dot maybe one material, and then you want to excite the quantum dot, right? Yeah. It will be a mesh system. Basically, you have a free carriers there, and then you have itself it have a electron and hole. So that electron and hole, whatever you are generating, if it does not form trion, because trion has to be 2D, but at the same time, that exciton, which is form a quantum dot, it can take a electron and hole from the neighboring 2D material and can form a trion. Yes, it is possible. Yeah.
Yeah, we'll stop it here because professor will
Sorry,
be available in the afternoon. You can have a discussion.
Yeah, I
in the
mean,
lunch break.
everybody knows my email address. So anybody wants to know anything can write me directly. Thank you very much.
Before concluding this session, on behalf of the organizing committee, it is my pleasure to hand over a small memento to Professor Athan.
Thank you. I'm sorry.
we'll move on to the next talk. The next speaker is Professor Prashant Kishore Panigrahi. He has been serving as the director of the Center for Quantum Science and Technology that is at SOA University since 2024. Prior that he was there in IISER Kolkata as a senior professor. Currently he is in SOA University. He is the principal investigator in the prestigious first program that is from the DST Government of India. He is a fellow of National Academy of Science to his recognition. With this brief introduction, I request Professor Panigrahi to give a brief presentation for 25 minutes. Professor Panigrahi sir, he is a native speaker. I request him to speak in between some native language so that the students will understand better. Please
Okay,
go
thank
ahead.
you. Thank you so much. And so in fact, my talk is a continuation of Professor Singh and our Arun's talk. So you see this wave particle duality is so fundamental that, whenever I hear about this kind of talk, I get very motivated. So in fact, Arun's talk in earlier conferences and Tabish Qureshi, who is in Delhi, his talk really motivated me to look at this wave particle duality. Then I realized it's really a very fascinating area, and part of it you could have got from Arun's talk. So you see what I'm talking about has a resonance with that. So, here what we found is that there's an exact triality condition. What is this triality condition? Very briefly, that Arun pointed out that in this double slit experiment, there are two slits, and particle or wave passes through it. The moment you know that if it's a particle, namely which slit it has passed through, there is no interference. And if you do not know at all about which slit, then there is good interference. Interference is measured in terms of visibility. It's essentially, this dark and bright fringes, but the difference that it is normalized I max minus I mean by I max plus I mean goes from 0 to 1, visibility. That is interference. Same interference will be one term here. Then which slit? Now you see, people around 1979, I'll tell you the history of it, people started thinking if the slit is slightly bigger or slightly smaller, what will happen? So then they found you can actually quantitatively make this mathematically, make this slit bigger and smaller. So this which slit, there is some ambiguity there. So that will be another entity which will come into my triality condition. You can actually precisely find out which slit and critically formulate it. So that is one term in this triality. And third thing that, for example, when in the past when you are going to a screen, so you put a detector, try to find out from which path it is coming. Typically like Feynman kind of thing. And so you can put a detector. Nowadays, they have these funny detectors where the whole thing may not collapse. You can actually, thanks to Aronov, Google person who is now I think 96 or something, still coming up with brilliant ideas, you can do something like weak measurement, partial collapse. So you can put detectors, which detectors are sensitive, but will not collapse the function completely. So you get partial information. So what you find is that there is an entanglement comes in this process. This particle and detector gets entangled. So essentially, you will find out in this very simple double slit, triple slit experiment, this mysterious entanglement, which is basically what was asked in Arun's talk about entanglement of 2 degrees of freedom of one particle. Same thing comes here. What you find is that path and solar light, wave nature or particle nature get entangled. More precise you will see. So essentially 3 things: which path, which slit, that is one information for path predictability, then standard interference, which is visibility, and entanglement. And all these things are hidden there in that simple interference experiment where you take 2 waves, for example, psi 1, psi 2, take psi 1 plus psi 2 mod square. What you find it out is psi 1 mod square, psi 2 mod square, then psi 1 star psi 2 plus psi 2 star psi 1. In the same expression, these 3 terms are hidden, and you find a precise identity, which came during playing around with it in our COVID period, where the good students were there having work. We also were free. You could play around with this kind of thing. That is a very beautiful triality relationship which came. and Kabis, for example, was also co-author, you will see. And then we sent it out. And finally, with some debate, came out in physical wave. Very recently in this 2025, in the month of February, so there was an experiment done by some groups. So that sort of showed exactly that this duality condition holds. And very interestingly, this kind of physics manifests in many places. And if you go to, there is another parallel conference going on, and Sudhamna Patra is giving a talk in neutrino physics, this kind of thing also turns up. So now I'll go quickly. You don't have to worry much about mathematics. Don't worry, because it has been told that mathematics you also not to use too much of it. So basically, you see this, three things: visibility, standard visibility, what you see in our quantum mechanics book. Now, which way? Basically, you put a detector to see which way it is coming to. Namely, path can you distinguish? As I told you, partial distinction you can create through this local width measurement that helps in formulating this concept. This path predictability is a slit. Can you make it slightly bigger and smaller? All these things can be quantified, and that's a precise relationship. That's what I was talking about. Okay. So same double slit which Arun showed, and plane wave comes. So let's not worry too much about that. Standard Young double slit. I'll show you that this standard expression what we learned in quantum mechanics first chapter, this term has hidden in it both coherence and entanglement. You will see how it will evolve. Okay. And so basically, what you do is you try to formulate it through this density matrix approach, which is nothing but outer product, and gives you a little bit more freedom. You can actually put the coherence, all those things. So standard quantum mechanics can be either be done with wave function or with so-called density matrix, which allows you more freedom. You can, for example, light, if you take fully polarized light, the moment you describe, it will be described by the state, the electric field. The moment you talk about partially polarized light, you have to expand it in terms of this Jones matrix, right? Identity and Pauli matrices. So you can imagine this is actually like Jones matrix. So you are allowing the freedom to have, coherence partially being lost. So you need this kind of density matrix approach. So this object expansion coefficient, as I told you, has the information about quanta. For example, normalization condition is trace rho is equal to 1, like psi star is equal to 1 in general. Trace rho is equal to 1. And it said, Hermitian object because you should be able to measure it. So for example, our 2-qubit term, which is basically Jones matrix, you see identity sigma z, sigma x, sigma y, which people knew earlier. Optics people knew most of it before quantum mechanics came. Partially polarized light is what I am talking about. So now, okay, so again optics, this is standard description of Jones matrix. This is pure, upper part is pure polarized light, in between describes partially polarized light. Origin is completely depolarized light. So these things are known. So visibility, standard thing. So what happened, people started, particularly after this Einstein-Bohr debate, wave particle business was stopped for a while because EPR paradox took over. So the whole 40s, 50s, people are busy with EPR paradox, nobody looked at it very carefully. And then once EPR paradox was quantified due to Bell, people started looking at it. So these two gentlemen, they are still alive, kicking and contributing to quantum information, profound people. And, they started looking at it in 1979. And they formulated mathematically that you can actually do it mathematically and very clearly do some experiment, partially motivated by Bell's work, where he quantified what is non-locality or what is locality. Then Greenberg and Racine, and very interestingly, it was done during the period around 88-89, when I was around in City College. We used to always make fun of Greenberger, big hair, foundation, all talking about quantum, and so we used to make fun of him. But you see how his name, Greenberger, Horn, Zeilinger, all these phonograms, what he was doing at that time. So this was, 1979, and then when he work came, this is the same Englert, for example, particle physics people. So he also started looking at it and added something more. So all this thing you can study. Basically, they were dealing with three quantities. One was the visibility was common everywhere, that is wave nature. One is this path predictability. Okay, so that is essentially slit width can be changed, like Greenberger pointed out. So this portion, for example, Englert was more worried about which path it is doing. So he put a detector. So So this D and P was common here, and they all found D square plus V square is less than equal to 1. D square plus V square is less than equal to 1. So this distinguishes by putting a path. Can you fully distinguish it, or can you partially? But then you realize what is beyond this bar, less than equal to 1. Is it possible to have it 1? So that is waited for some time. So there is a very beautiful experiment. Again, Tavis talk motivated me to look at this very carefully. 2001 experiment. They did an atomic physics kind of experiment, and what they found is actually the three slit. In three slit, they talk about this, this fringe, contrast, which path, very remarkable paper, 2001, and this published in 2001. And they found that if you take this hard slit, in front of it create some disturbance, namely decoherence, visibility increases. So, anybody who hears about it will be really amazed that how can we increase visibility? Now, believe it or not, people are using it for better sensing. You can actually increase the sensitivity or visibility by creating obstacle in third path. So this sort of attracted me. I looked at it very carefully. Namely, decoherence can increase visibility. Namely, decoherence is supposed to be very bad, but in the multipath scenario, it can help. So never understood that paper very carefully. So it comes during COVID period. These were our own student, I saw Kolkata student, and Nitish was also. He is now finishing his PhD in Australia. This fellow is in USA. Not much to do, so we were looking around it. Then we looked at it from the perspective of near field optics, namely free polarization. You know that in near far field we have orthogonal polarization. Near field optics, both the three fields could be present. So we were doing in that context. So we sort of found this identity in that context, communicated to a journal, was heavily criticized. One of the referees said that if you can correct this, put this, clarify this, I will allow. But then it was there in the archive, so which then suggested that we look at it carefully. So his student is Neha. So then we started looking at it primarily. These was Avinash and Tavis were the main players here, and I was an onlooker. So they actually found out that indeed this whole thing arcs up a very nice one. My contribution was that while you look at this one, that row object is a trace row is equal to 1, it's a Hermitian matrix. Where from that additional thing and what does it mean? There what we found is that additional thing actually is actually entanglement. I'll tell you about that. So that entanglement method, to our good luck, me and my student had earlier found out, we exactly fitted that. So here was the experiment in February 2025 of this year, and when somebody sent me this paper, then I found out they have verified one paper, and that paper is ours, 28, 28. So that gave me a big kick. So I started looking at it carefully and more, and then found out that it can have many other applications. So very fun to play around, and essentially that row of the row is a Hermitian matrix. In 3 by 3 Hermitian matrix is Gell-Mann matrix. Our particle physics colleague deal with this kind of thing left and right. So it's a Hermitian matrix. So every dimension we know its behavior, and visibility is defined like that. So you can actually then start formulating things, taking into account that trace row is equal to 1. Probability is conserved. So sort of interference term, that psi star psi mod square term, you suitably arranged because square comes from there. Purely off diagonal elements is interference. So that you write suitably called Hilbert-Smith coherence, purely off diagonal elements. Psi star psi 1 star psi 2 plus psi 2 star psi 1. That you are just that. Then comes, so in general, this is your density matrix, this object you are dealing with, then you have separated out. So only play around with that Hermitian fellow. So then, you put it, as I told you, 2 detectors to see which path it is controlled. You see here, these are imaginary detectors. Then you can actually integrate them out, because you are just having that information built in here. If it is orthogonal, you exactly know which path, so there will be no interference. If they are partially orthogonal, for example, DJ could be 1, it means with measurement. You are not observing it, partially observing it. That freedom is there because of with measurement. So that freedom is here. If it is delta Jk purely particle, if it is not delta Jk any other quantity, it is wave nature. So that you built in. This is thanks to Kurtz and this Jurek. You learn from there. So that you suitably put it here. That object up here. So there are 2 extreme scenarios. one is delta jk, purely particle, one is 1, which is purely wave. In between you can adjust. So you put that way. So then you look at your that intensity, because that's what you are looking at. All these things are hidden there. So again you do a bit of massaging, interpret it, connect it with physically observable things like visibility measure. All those things are there in the paper, don't worry about it. Now go to that path predictability. So you can see here, this flow is purely diagonal flows, suitably arranged, because which slit you are modifying will depend on the diagonal flows. So suitably if you arrange pure diagonal, go to that point, IIJJ, so that is that path predictability. So purely off diagonal is wave, pure diagonal is which path predictability. Now, if you take rho more square, other terms will be there, what are they? So that you sort of don't worry about it. Now keep on massaging it, and so that is the mathematics. I have been told not to use too much of mathematics. Go to special limits, match with others, and then in some cases there is no entanglement. You find that these things are up to 1. If there is entanglement, you find things are some fellow could be 0. So like special cases you can check. But at the end, so if you modify it, so let me get into details. So some remaining term will be there. This is the term which you have to modify. Now then it took us quite a while, and we looked at its origin. It comes from the wave function in this way, and then it has both diagonal and off diagonal. You see, IIJJ and IJ, diagonal off diagonal term. So what is it? That took us a lot of special cases to handle. So then what we found finally is that here, this flow is something which we knew earlier, and I'll show you the paper which we have done with it. One fine morning, we found it is actually exact measure of entanglement. This object is called I conference, which has been, whenever we go to more than 2 degrees of freedom, like Euclid or 3-particle system, this is what you have to deal with it, and this has a geometric meaning. It actually shows that entanglement is nothing but area between 2 vectors. So this we had found earlier, and it beautifully matched with that. It has both, you see, diagonal and off diagonal fellows, and in fact you can actually show it's an area between 2 vectors. So I will not get into that, I will only give you a reference. So when you suitably massage it, you see exactly 3 things are up to 1, and it is true even in the presence of decoherence. Okay, so that was the result, and let me give you some. Okay, so now this is just an advertisement. Recently, we found that in this neutrino oscillator also it manifests. There it is basically mode entanglement, because it is actually a field theory but with quantum mechanical wave function having 3 flavors. So in the 3 flavor space, because the mode entanglement it can manifest, and you can actually, there are 2 experimental scenarios, you can actually check it out. Then this entanglement business is very funny. You find something called monogamy behavior. If 2 fellows are maximally entangled, a 3rd fellow cannot get in. So this typical monogamy, as if particles are behaving in a monogamous way. So the same kind of behavior appears in neutrino physics. That was a very surprising thing for us, but again through this identity alone. So this is the one, this we have the government of India a program called NIUS, National Initiative for Undergraduate Students, who was sent to TIFR. And this boy came to me when he was in BSc 2nd year, and this allows you to sort of mentor them for 3 years. We did. So we found that entanglement is actually area between vectors. Very simple way you can show that. All the things which were known fit very nicely. Beside the area, because Hilbert space area, there are 2 vectors. After measurement, if somebody does a measurement, you will find some states with collapse. The collapse state area will give you the entanglement between the previous. So then, by the time we are in 4th year end, this paper got over. Then we got published. Then we are using a transition due to Lagrange. Then a mathematician from MIT pointed out it is not Lagrange, it is actually Brahmagupta. So Brahmagupta's identity fortunately manifested here. Later on we corrected it, but we have given the name Lagrange identity. So this is, and very recently, for example, general EPR state has been used, to describe it. The same identity what we have given there has been used. This is a recent work of Tavis, and I suggest that people should take a look at Tavis' work, because his works are really beautiful. Many of them could find technological applications, and I really like his work, because 2-particle interference, where entanglement comes in, And many of these things are things which Arun was talking about, particle nature, wave nature, you can separate it out, and it definitely would have lots of technical applications. So I will not prolong anymore. Basically, main point is that very simple double slit experiment which generalized to 3 slit and beyond. 3 slit is enough. You find counterintuitive things like entanglement and really changing physical quantities like visibility, and the slit width, the things which you just imagine can be quantified, and you have to do a nice mathematical formulation, and hopefully some of these things will be technically relevant. For example, two particle mobility we could use for generation of randomness, random numbers, and through measurement. So now you see this first couple of chapters of quantum mechanics is what people are dealing with. All this entanglement, this teleportation. You don't have to go beyond 2 chapters of quantum mechanics. Stern-Gerlach experiment is maximum you have to go. Still you can do remarkable things, and where the field right now is only in that direction. Okay, so linear algebra and first couple of chapters of quantum mechanics is all that you need. We stop here. I am now in Goa University. Most of these people are free workers with the students who have finished their MSc or BTech, or doing some 6 months, 1 year kind of project in NIT Rourkela and Hyderabad Central University, and 2 PhD students are here, and these are all 6 months, 1 year kind of project students, and through which you can do quite a few interesting things. So I'll stop here. Thank you.
Thank you, sir. Sir finished about 10 minutes earlier. We have time for at least 2 quick questions because we are running out of time.
Very good article, what I feel. But here you are thinking of multiple slit and the stream of photons. Suppose nowadays for quantum information, single photon is very useful for cryptography. Suppose we will, even though we will pass a single photon, either it has to go slit 1, slit 2, slit 3, still then you are getting interference. That is what I say in one equation, wave function adds, but probability do not add. So this is a paradoxical. A single photon goes in multiple paths. Multiple photon goes in multiple paths is classical. And since you are in one of your paper, this is one question. In another question, in your one of the paper, when you talk about entangled state, it is always a mixed state. That is why density of the matrix comes to the picture. But you have a pure state entanglement. How it is possible?
See, 2 particle entangled state, for example, singlet or triplet. Consider singlet state, up down minus down down. That is a pure state.
Pure state.
Now, if you are looking at one particle, that let's say Alice and Bob, one flow is Alice. You are looking at Alice end, it looks like a mixed state.
Mixed state.
In the 2 particle state, it is a nicely entangled, state represented by the wave function up down minus down by this. Only when you want to see how entangled they are, you look at the first particle or the second particle, ignoring the other one. Then you find it looks like, because of the entanglement, it's a mixed state. It is not a pure state. If they are separable, they are completely pure.
Good afternoon, sir. Yes, sir.
Yeah.
So my question is, you said that under multiple beam Ramsey interference, the decoherence decreases the visibility. But generally, we are aware that the visibility decoherence increases the visibility in case of Ramsey interference. But we know that the decoherence generally decreases the visibility. How is it possible that in multiple beam the decoherence increases the visibility? Is it under specific conditions or it's generally the case?
Actually, what you asked, that I exactly had the same question in IIT Jodhpur, where Kabir gave a talk. So I think I was really, and that is really motivating to look at it. So we see that 2001 PRL paper. It is possible. What happens is that there are 3 terms which add up to 1. If you want to increase visibility, if you can decrease that entanglement, each term is positive. Slit square plus visibility square plus that entanglement square is equal to 1. Each term is positive. Slit you cannot do much; it's already fixed. Now that entanglement you can access, change. The entanglement you see, it is between 1, 2, 2, 3, 1, 3. There are terms involving 1, 2, 1, 2, 3, 3. here, this 3 fellow is there in 1, 3 and 2, 3. So when we are doing that, putting some obstacle here, the entanglement is getting reduced.
Means we have to decrease the area between two vectors.
To entanglement, you have to reduce between the two vectors, then the visibility will increase.
So then in normal interference, why decoherence?
No, because there are 3 things. No? Normal interference is basically 2. Normal interference is psi 1, psi 2. Here psi 1, psi 2, psi 3. So third flow is like a switch kind of thing, control. So third flow you use, by putting this decoherence, we are actually reducing entanglement. In the 2001 theory paper, they don't understand it. But now we understand. You see mathematically, 3 terms are positive. What will you do? If only just neglect, suppose there is no entanglement. Then obviously that positive term will decrease. So because the whole thing is 1. So what will happen here? Slit is not going to change, visibility will increase. Roughly you can do that.
So is it always mandatory to have control?
We are running out of time.
Beyond 2, unless you go beyond 2, it will not possible. You can talk to us.
Sir will be available in the afternoon during lunch break. You can have a long discussion with him. Let us thank Professor Panigrahi for his wonderful talk. On behalf of the organizing committee, it is my pleasure to hand over a small memento to Professor. Let us move on to the next speaker. There is a slight rearrangement in the order. Next speaker is Dr. Richo Goya. He has done your BTech and MTech in Electronics and Communication Engineering at IIT Bombay, and in collaboration with the TFR Mumbai in condensed matter physics with a specialization in photonics and plasmonics. She did her postdoctoral research work at IIT Delhi, dedicating her research in the development of ultra-sensitive sensors for biodiagnostic. Currently, she is working with IBM Quantum as a technical quantum engineer, committed towards exploring various aspects of quantum computing. Madam, 20 minutes. Thank you very much.
Sorry for this delay, and hello all. I'm Rishwa Goyal. I did my PhD, as everybody said, in quantum photonics, but now I've migrated towards quantum computing. Quantum computing is a very interesting field. Honestly, all sitting here, I would I would recommend to please come in this field. So we talk about quantum revolutions, right? Quantum revolution first and quantum revolution two. First quantum revolution is what we see the technology today. It's about lasers, it's about LEDs, it's about photoelectric effect and stuff like that. What is quantum revolution 2? Quantum revolution second began around 1990s, right? This was the time when we were talking about using the same agents. When I mean agents, I mean atoms, neutrons, protons, electrons, photons. But the difference between the first revolution and the second revolution is the way we are maneuvering or manipulating our agents. When we were in quantum revolution 1, we were talking about all of that ensemble collectively being manipulated in a certain path. But in quantum revolution 2, what is currently the buzzword is in which we talk about individual particles being manipulated and maneuvered. So that makes quantum revolution 2 a step ahead of quantum revolution 1. And this is where we begin and we talk about the power, or rather the magic of quantum computing, because now here we're talking about individual entities rather than just an ensemble of particles. So, okay, how does this work? I'm sorry, it's not working. Should I, wait, I'll do it from here itself. I think it's not connected. Yeah, thank you. So IBM, of all the companies, have come up with this IBM quantum computer. The beauty of IBM quantum computer is that it is available over the cloud. That means everyone sitting in this room can access IBM quantum computer. You can run your own small experiments using IBM quantum computer for free. Literally free, 10 minutes. 10 minutes of quantum computer time is available to everyone after you open your quantum account there, right? Companies like Google also have their quantum computer. They're also working on superconducting qubits. Besides, what makes it different from the existing semiconductor technology is that in semiconductor technology, everything is benchmarked. You know how a chip has to be made, how you create the IC. But in case of quantum computer, you have at the moment so many technologies, so you don't benchmark. You have different companies giving you different errors, different processing, or what you call a cycle speed, or maybe how fast your system is running. So you've heard of neutral atoms, you've heard of photonic qubits, you've heard of Majorana qubits, and then there are superconducting qubits. At the moment, we see that superconducting qubits is somehow leading the way. So if I have to compare the state of art of technology in case of quantum computer with the existing semiconductor technology, I'll say quantum computer is where semiconductor began. It's a room full of electronics, and where you have so many limitations when we talk about processing. When you want how that system should be, you talk about very, very, very low temperatures as low as maybe just few millikelvins. So you can imagine you are talking about maintaining temperatures 100 times colder than the outer space. So in one of the conversations, a very interesting question came out from an audience. He said, if you need low temperature, why don't you move your system to moon? And of course, it's a beautiful idea. I'm talking about getting a temperature. I want that my system should be here and, have such low temperature. Why don't I just move and put a system on moon where there's already very low temperature and I would need just few more kelvins to go down, right? So yeah, I mean, people are talking about that also. So imagine your system is on moon and you're operating it here. So that's where technology, that's what technology can do to you, and that's what the beauty of any technology is. So, coffee. I'm sorry, the coffee came from Bangalore, but I forgot that I'm here in eastern part of India where tea is the preferred choice of beverage. So anyways, so your early morning cup of tea, you know, that nicotine element. Yeah. So you all want to know what's happening inside that molecule, right? Nicotine is a huge molecule. If classical was so perfect, why could not I have done that simulation till now? We have so many molecules around and so much to play with. We can't do. We cannot do exactly. Why? Because there's so many interactions. There's so much of environment. Just playing with a single molecule is, you know, it's a task. So if I have to see, I mean, this is a caffeine molecule. Please excuse me for that. And if you need to compute caffeine, actually, you would need approximately 10 raised to power 48 bits. And that is what? 1 to 10% of the total number of atoms. Imagine, can you do it? Of course you cannot do it. And you know, here lies the power and the magic of quantum computer. You need just 160 logical qubits to simulate it. And that's the power of quantum computing that we talk about. And which is why you are sitting in this room full of people. And I'm addressing you to say, okay, quantum computing is the next step. Please come and have fun. So now what we talk about quantum particles, what we talk about quantum problems are, which we want to address are, there's a set of problems you all know called the hard problems, the NP-hard problems, and there's a problems which are called quantum easy problems, and then there's a small set of polynomial problems which at the moment can be addressed using the current state of art. So if I have to take you further to what is the state of art, here you go. Sorry, before that, I'm sorry. So what kind of problems we can solve? We can solve using quantum computers, right from ground state estimation to calculating how your molecule is going to behave, whether it's ground state, whether it's excited state, using different algorithms. At the moment, there's something called SQD, diagonalization problem, which is being extensively used and studied by different scientists to for various calculations, whether it is optimization problem or whether it is a calculation of ground state energy estimation. All that is being extensively explored by researchers all across the group. These are some very basic problems that that can be considered as researchers. This includes problems like you know, developing lighter, long-lasting batteries. We all talking about EVs, and we know how difficult it is to get those rare earth metals when only a few countries have monopoly over them. So why not have a battery, or why don't develop a material from the existing set of materials, which is easier and lighter and easy, you know, can be done without spending much cost and you know, focusing on rare earth metals. When we talk about materials for building up aeroplanes, which are again stronger and which are lighter, we talk about discovering a new class of antibiotics. Of course, we all saw what COVID did to us, right? If you had quantum computer, you know, a fault-tolerant quantum computer, we could have come up with a good solution, maybe within weeks or maybe within a month or so. Then we talk about superconductor. We talk about medical diagnostics, where again quantum computers can play a major role. Besides that, we also talk about problems like problems which we can solve which cannot be easily done using classically are the optimization problem. So in this set of problems, we usually consider problems like anomaly detection, or maybe patient, if you're studying any patient, or when you're talking about risk management, whether it is quantum time series or whether we talk about finance, and optimization is deeply focused on logistic kind of problems. So these are the various set of problems. I'm giving you problems and not solutions. Say thanks to me, because this is the solution that this is what you were looking at. And now we come out to be, of course, these are the basic principles. Professors have already spoken about it. So I'm definitely going to speak about it. And yeah, now if we talk about the state of art, how much time do I have it? Another 6 minutes? Okay, I'll be rushing up, I'm sorry. So state of the technology. Now, when we talk about the state of technology, we talk about where we stand today. So at the moment, we talk about something called NISQ, near-term intermediate scale quantum. At this moment, you are able to get a result. But there is definitely a certain amount of error in it, because the qubits are not yet error corrected. What you get is error mitigated. So why is that so? Because there is a lot of limitation with respect to hardware. At the moment, IBM has 156 qubit systems, while Google is at its best is 108 qubit system. Beyond that, we don't have more than those qubits. If I want a logical qubit, a logical qubit for that matter, I can explain. There's a certain there's something called a physical qubit, and there's something called a logical qubit, which probably all of you must have encountered till now. A physical qubit is what a qubit is available to you, but a logical qubit is a qubit which is already error corrected. So a couple of logical qubits, physical qubits will join together and form one logical qubit. So at the moment, we don't have a logical qubit, which means we don't have an error corrected qubit. And that is where we stand here. We talk about error mitigation, and we are moving towards something called as error correction. And this is some kind of time scale where we think, and most companies, including IBM, is saying by 2029 we will have logically correct qubits. Quantum advantage, there's a lot of talk about quantum utility and quantum advantage. These are two terms which are often spoken and used by people in this domain. So quantum utility is basically saying, okay, this is what a classical computer can do, maybe in a 100 hours, but a quantum computer can do the same thing within maybe minutes or maybe hours, right? So that is what you're talking about quantum utility. You do an experiment and then you test it on a quantum computer, and corresponding to that, you do a similar computation on a classical system, irrespective of the time it takes, irrespective of the purity of the result. You get it as you have something which you can compare currently with the classical system, and that is how you define a quantum utility. But quantum advantage is a step ahead. So this is how it's basically defined as performing an information processing task more efficiently. And remember, Google has just showed another paper in which it stated that the quantum computer there can do their processing in 13,000x times faster than what a classical computer can do. So here it comes. It tasks more efficiently, cost effectively, because of course classical systems would with that kind of supercomputers, even if you take a cluster of supercomputers and make them do that hardcore task, they will take infinite, not just infinite time, but infinite amount of energy to operate them. Or using quantum computers than is known to be possible with classical computers alone. So in quantum advantage, we say, okay, here is a problem, and this problem cannot be solved using the current classical system, right? So what you do, you put that problem into your quantum computer, do some, play around with the gates, play around with the algorithm, and now you have a solution to it. And if you are able to do that using the existing systems, something which cannot be done classically, you say, I have achieved quantum advantage. And this one quantum advantage is, I personally hope that we should get a quantum advantage out of India, out of people sitting here, and it will be my absolute pleasure if we are able to get that. So, okay, here is the problems that we talk about. There are timely problems, there are some interesting problems, and there are the solvable problems. Here is the hierarchy of problems that can be solved using quantum computers. And yes, what we can do with quantum computers right now is this. There are some easy problems which definitely does not need any quantum computing, and you do these problems using classical computers. Then there are very hard problems which need fault-tolerant quantum computers. Of course, you cannot do them too because you don't have enough quantum hardware for that. But then there's a small sweet spot. Okay, and these are the set of problems which are being currently addressed using the quantum computers available today. So what makes quantum computers beautiful is that they should be performant, and those quantum systems should be easy to use. People like me and you should be able to access them on our laptops, should be able to program them, and then we should be able to execute those experiments, right? Just like people here were talking about Heisenberg's model, and we're talking about Schrodinger equation. So you should have those equations ready, convert them, produce an Hamiltonian out of it, and then you execute, and then you change them into quantum gates. You manipulate those, you use those gates put them into your system, transform them into proper circuits, and then you execute it. That is what quantum computers is all about. And here is how a IBM quantum platform looks like. So we begin with something called a Qiskit runtime in a quantum processing unit, and then it is working in tandem with high performance classical compute. And then we have different orchestration layers like serverless, and where we have integration with the HPCs, high performing computing. Then you have different SDKs, you have transpilers, you have a Qiskit code assistant along. And Qiskit code assistance perhaps is very useful for all the beginners. It's a Python, Qiskit is a SDK which uses Python. And anybody who has a bit of knowledge in Qiskit on Python can easily use this and write your own experiments and test them on quantum computers available. There are also simulators also available on the easily. So you just have to download Qiskit SDK and you can start doing at least the simulation part of it. And then there's the Qiskit function catalog. This is a basic hierarchy of how your system works. So as an IBMer, I would say that if you want to do quantum, what you need is to know Qiskit, right? You need to know how the gate structure works. You need to know how those Hamiltonians can be converted into to different kind of gates and different kind of functions, and then you can manipulate them. So what you need is a quantum software. You need a Qiskit. You need quantum processing units, and then you can do what you can, what is capable, what you are capable of doing, what your system is capable of doing. Some useful work. But this useful work can be a utility kind of scale, or it can be an advantage kind of scale, right? So on the IBM platform, there's this quantum learning platform where you can easily learn all the basics of quantum computers easily. I mean, they're very short courses and very, very comprehensible. And anybody who has even a little interest or understanding, you don't need to know quantum mechanics at the very core. Let me tell you, you need to have a bit of understanding, a bit of analytical skill to get a deep dive into this. And then, this is the quantum learning platform. And then there's the IBM quantum community where we talk about quantum learning. Then there's a Qiskit advocate program. We talk about the global summer school, Qiskit YouTube channel, and the developer certification. All these are very useful when you want to be hired in this domain. Then there are summer internship programs. If you follow the IBM career page, you will find out there are internship applications. Currently also they are out. So these are summer internship programs. And then we have a certain set of interviews, etc. We run through them to look through all the CVs, and based on the most suitable person for the job, we have a 3-month program. This is around May, June, or July, and it's a very good time because you get to know the corporate side of quantum computing. You get to interact with very good mentors who have very good knowledge in different domains, depending upon your skill set and depending upon your interest. You can diversify here. And then there is this developer certification program, which is a very useful certificate program. It's essentially checking Qiskit, your Qiskit skills, and other quantum mechanics skills. And that's it from me. Thank you so much.
Yeah.
I hope I can.
Thank you, ma'am, for finishing our time. It is our time to move from quantum computing cloud to quantum computing move. Let us hear from madam. One or two quick questions.
Thank you, madam, for this nice talk. I was just wondering if you can quote or just give an example of the simplest program belonging to that sweet spot. You talked about the very hard, very easy, and the sweet spot.
So, of course, I was talking to Professor Tapan Mishra. We just got a paper, just got accepted in Nature. So in this particular paper, we actually did a quantum time series experiment. So predictive model. You have a lot of prediction models, right? LSTM, transformer models, AI, ARIMA, whatever, right? So in this particular work, we actually showed how quantum entanglement can be used for prediction. So it's a quantum time series. Now this time series can be very useful whether it is whether we talk about prediction in terms of finance, or whether we talk about, in this particular paper we took geospatial data. So we took a geospatial data and we showed how quantum, how our algorithm can be easily used for predicting, right? This is a low scale problem. If we talk about high scale problem, this can be easily scaled up for any kind of prediction, whether it is related to environment, whether it is related to geodata, or whether it is related to even satellite data. So
how many qubits do you need typically for this type of?
see, of course, since it would need to be published in Nature, we had to go above 100 qubits. But having said that, a simple experiment like simply showing Bell state, right? Bell state is a simple 2-qubit experiment. It can be easily conducted. It's like flick of a finger. And besides that, there are many other experiments, tiny experiments, which you can do as a starter. But for real experiments, like there's another optimization problem that me and my collaborator are actually working on. So in those kind of problems, of course, like in the beginning, I showed you that ferrum sulfide problem, right? It took around 65 qubits. So see, 156 qubits are anyways available to you. So around 100 qubits can be easily done. And right now we are focusing on sample-based diagonalization technique. So the initial, the NIST kind of problems you basically talked about variational quantum eigensolvers, right? So they were very heavy on the system. So they need to be run for hours and hours, which requires a lot of quantum computer hardware time. Now we talk about sample-based diagonalization. It's a shot-based diagonalization technique. So, yeah.
Dr. Richa, a quick answer.
Yes.
Where is the hardware now?
Superconducting qubits.
And how who is ahead of this particular area? US, China, India, and is there a role? But yeah, that's what you know. That's a practical answer I want.
It's a difficult question for me. You're putting me in a tight spot.
No, it's a practical answer.
See, China, I will not like to say. China is currently a friend of India, so I would not like to comment.
No, I'm not trying to be political. I'm only trying to be where we stand.
See, if I really talk about in terms of hardware supremacy, at the moment I see US is leading because of course as I said, IBM has put their system on the cloud. So you can use it, you can test it for yourself, and there are so many clients, right from Mercedes-Benz to Cleveland Clinics. I mean, every banks, you can think about so many universities who are currently exploring and exploiting the resources. Besides, Google is every now and then coming up with different kind of hardware problems, and they're trying to solve them out. So.
Just one question. Thank you for the nice talk, because here you have added software with hardware.
Yes.
Actually, what we are with a common reader, we are understanding that so far as quantum information is considered, information processing, cryptography, quantum computing acts as a double-edged sword. Sometimes it cryptographically damages.
I have a little disagreement with this. Quantum information science is different from quantum computing, sir.
Yeah, no?
Quantum computing and quantum information science are different. They are different pillars together. So we talk about as 4 pillars. We talk about quantum sensing. We talk about quantum information science. We talk about Alice and Bob all the
So
time.
far as quantum information is considered,
yes.
Thinking of the secure communication, we need quantum key distribution, something like
Quantum key distribution is different from quantum computing. That's what I'm trying to say.
But I just have a quick comment.
Yeah.
Logical qubits actually exist. I mean, error-corrected logical qubits do
But
exist.
not on the cloud. I mean, not available to you as
that's
a user.
That's a different matter. But people in Quantinuum very recently,
Yeah.
the Helios, it has 98 physical qubits and 48 logical qubits.
I completely agree.
Yeah, and they've done
Because there are many error correcting codes already there. Software
no,
codes.
it's not code. It's just hardware. Actual logical qubits. They
Majorana qubits.
Sorry.
Majorana fermions.
No,
You're
not
talking
my
about Microsoft?
No, trapped ion. No.
Acha, trapped ion.
Yeah,
Okay, okay.
this-
Trapped ions.
Yeah, Quantinuum. I mean, they are the leaders
Yeah.
now.
Yeah.
I mean,
Quantinuum.
For example, H2 molecule, it had been actually performed, quantum computations have been performed using logical qubits too.
Yes.
But more recently, the Fermi Hubbard, it's a condensed matter problem.
I know.
It has been achieved by 48 logical qubits.
I know, sir. But when we actually talk about logical qubits and physical qubits, we talk about 2 logical qubits, so it's not going to take me anywhere, sir.
No. But now they have 48 logical qubits. The Fermi Hubbard
Yeah,
was
Fermi on
done
the
using
model.
48 logical qubits.
Okay.
So the first computation was using 2
The
logical
problem
qubits.
with trapped ions is their scalability. Trapped ions is not easily scalable.
It may not be easy.
So yeah. So 48 qubits. If I talk about 48 logical
Yeah.
qubits, right?
Yeah.
And if I talk to you, okay, today is 48 qubits. What next? Can you give me 1,000 logical qubits?
No, that's a different matter.
Yeah.
That only time can tell.
Yes.
Say, for example, neutral atom quantum computers are scalable.
Yeah.
Okay. I mean, even more scalable than superconducting quantum
Absolutely.
computers. So,
to my understanding, the best
but-
best would be photonic qubits. I would see photonic qubits
I don't
to be
know,
scalable.
but the best quantum volume, a concept that was introduced by IBM,
Yes, quantum volume.
that comes from Quantinuum at the moment.
Yeah.
Thank you.
Thank you so much. Any questions?
One last quick question from the student.
Yeah, everybody is waiting for the lunch. The lunch is waiting for them.
The question is more on the hardware side of the quantum computing.
Yeah. Go
So
ahead.
we know many physical systems can be realized as qubits. So
Yes.
I wanted to know your opinion, which among this is the best candidate to...
I should not comment there because we are all at a very experimental stage there. Just like Sir said, there's trapped ions, there are neutral atoms, there are photonic qubits, there's NV centers, and there's superconducting qubits. At the moment, exactly. So when we talk about photonic qubits, yeah, photonic qubits are very good for information sciences. Yes. There's so many, and besides what we have realized over a period of time, the different qubits are good for different work. Like photonic qubits are said to be very good for information science. Superconducting qubits is doing good in quantum computing. So I think eventually, the technology will digress in such a way that for a particular application, one would be good. Maybe the other one not be. Right.
Stop it here. And we have one or a small number to the next session will start at 2:30. We will have a lunch break now, and we will also, before having the lunch, we will have the photo session. The lunch is arranged in the library foyer. So we will assemble for the photo session, then followed by lunch, and we will reassemble here at 2:30. Yeah, thank you. So when you go for the lunch venue, you have to cross this road, and before you cross the road, you have a photo session. Okay. Open, sir. Those who received the lunch coupon, you kindly give it to the volunteer. Those who received the lunch coupon, kindly give it to the volunteer.
Good afternoon, everyone. So we'll start the afternoon session now. So I request everybody to settle down. My name is Subhankar Vedant. I'm a faculty in the School of Physics here. I work on condensed matter experiment, so in particular spintronics. We'll talk that someday later. But today we have really three wonderful speakers in this session. And let's begin with Professor Bhanu Das. He is currently the director of the CREST Center in Kolkata. I mean, if I would actually read his CV, probably it would need half an hour. So I can only say he's a very nice human being, a great physicist, and most importantly, he's the PhD guide of the convener of this conference. So Talia ho jaye isliye. Yes. So I would request probably with that, just to tell that he has done his PhD from city New York, and he has been visiting professors at many reputed institutes like Stanford, MIT, Caltech, and so Oxford, and so on. And he has been working long time in Bangalore, and he can give actually very nice talks which can cater to young students like you. So I'm really looking forward to your lecture. Your lecture will be for 25 minutes. I will give you an alarm at 20 minutes. Thank you.
Okay, thank you very much, Professor Vedanta, for a very, very kind introduction. I would like to thank all the organizers for this excellent symposium, and in particular, I would like to thank Professor Tapan Mishra for inviting me to give this talk. You've heard talks on various aspects of quantum. You've also heard a talk on quantum computing. So, I mean, the general aspects of quantum computing that was introduced by Professor Arun Pati, and then you've heard Dr. Risha Goel. And what I'm going to be talking about is how to use a quantum computer to get results. So the title of my talk is Finding Properties of Atoms and Molecules by Quantum Computers. Now, many of you have taken a course on quantum mechanics, and in that course, you must have studied about atoms, perhaps even molecules, and even considered properties of atoms and molecules. And a lot of researchers in the world calculate properties of atoms and molecules using regular computers. You know, the only atom for which you do not need a computer is the hydrogen atom. But if you go beyond the hydrogen atom, you need a computer. So I'm going to be talking about atoms that are larger than hydrogen atoms, so we need a computer. So this is the outline of my talk. Yeah. So there are basically 4 parts to my talk. In the first part, I'll talk about the basic ideas of what I've called classical computation. Classical computation means regular computation. It does not mean computation of classical physics, but rather the computers that you use are called classical computers, because we have a new kind of computers, as you've heard, which are called quantum computers. So anytime I talk about classical computation, it means computation of anything by classical, that is regular computers. So I want to say a few things about that first, because to understand quantum computers, you need to understand regular computers, classical computers. And then I'm going to talk, say, something that you already know about quantum mechanics, because quantum mechanics is a combination of, quantum computation is a combination of quantum mechanics and classical computation. So to get to quantum computation, one needs to know about quantum classical computation and quantum mechanics. Now, quantum computing combines the above two things. And specifically, I'm going to talk about qubits, quantum gates, and quantum circuits. These are the three things that make up quantum computing. And of course, you need hardware, an actual computer to which you can feed the input. So I will talk about qubits, quantum gates, and quantum circuits. And my task has been made fairly easy by Professor Arun Patti. He has talked about qubits. And so I'll just quickly go through that. Now, after having talked about these things, I want to say briefly about how we can apply a quantum computer to calculate properties of atoms and molecules. Okay, so just to remind you, in classical computing, the basic unit of information is a bit. So when we give input to a computer, say you want to add 5.5 plus 2.2, so 5.5 and 2.2 are expressed in terms of 0 and 1. So you have to convert to bits. So decimal numbers will have to be converted to bits for doing any kind of computation on a regular computer. So the basic unit is a bit and 0 or 1. So if you like, there are two states in a regular computer, the 0 state and the 1 state. So that's what I've written here. So, and bits are made up of transistors, and it corresponds to off and on. And so, we talk in terms of bytes. How much memory does a computer have? So 8 bits is a byte. Now, this is just a picture to show a bit. Bits are the inputs. Now, you have to use bits to do various operations inside a computer. You can add numbers, you can multiply numbers, and so on, or you can do other complex operations. And for that, you need gates. So this is something that you may have studied in electronics. You give an input, you get an output. And then a computer that you use, a regular computer, is a combination of bits and gates. So you give the input in the form of bits, then there are various operations, and you get an output. Now, this is called, the output is deterministic because it is determined by the input. Okay, so that's all that I want to say about classical computing. And now, since quantum computing is a combination of regular classical computing that I talked about and quantum mechanics, let me just say a few things about quantum mechanics, and my apologies to the experts here. Those of you who are experts in quantum mechanics will have to excuse me for saying something very simple, but if you're a BSc student, I think you probably need to be reminded that quantum mechanics, as was discussed by Professor Lambodhar Singh in the morning, deals with matter at an atomic or a subatomic level. Okay. So, and then we've heard about the Schrodinger equation. So this is the Hamiltonian, and it can have many different states. The lowest energy state is called the ground state. The other states are the excited state. So this is the Schrodinger equation. And this is what we want to solve. And so psi is the wave function. Hamiltonian is just the kinetic energy plus the potential energy for any system. Now, if you have an atom or a molecule, then this is the Hamiltonian of the atom or the molecule. T is the kinetic energy, V is the potential energy of the electrons due to the nucleus and other electrons. And then you have the time-dependent Schrodinger equation, which is this. And of course, the The way we interpret the wave function is that psi star psi is the probability. So the total probability over the entire volume is 1. Okay. So this is about the wave function, and the wave function represents system. So, so sometimes I'll say wave function, sometimes state. They both mean the same thing here. Now, another important thing to know here is an operator. So if you have a wave function, now the Hamiltonian is an operator, of course. So A can act on a wave function psi to give you another wave function psi prime. So when an operator acts on a wave function, you get another wave function. Okay. And also, let me remind you that for every observable, by that I mean a quantity that can be measured, like position, momentum, energy, and so on, they can be measured. They are called observables. And corresponding to that, we have an operator, which I call as O. Now, what you're doing is you're actually measuring this quantity. And if you want to calculate that quantity, it's simply the expectation value of the operator O star psi this. So this, of course, you're all familiar with. And this is the average value of this quantity O when you measure it many times. So when you do a measurement, you measure it many times, and then you get a quantity. And so the measured value is the expectation value, which is, if you want to calculate it, you have to calculate like this. So this is all that I want to say about quantum mechanics. Now, thanks to Professor Arun Pati, now all of you are experts on superposition and entanglement. So I'll go through it very quickly because he made an excellent presentation of these ideas without using any mathematics. But I will use a little bit of mathematics so that my talk is a little different from his. So if psi 0 and psi 1 are two states of a quantum system, then C0 psi 1 plus C1 psi 1 is also a state of the system. That is a feature of quantum mechanics. This is not true of classical mechanics. In classical physics, you don't have this, but we do have it in quantum mechanics. So this is the superposition principle, which is, Professor Pati gave an excellent explanation of this. And then, of course, entanglement, which is a little more difficult to understand. So here, what it means is that I have two systems, A and B, and psi A and psi B. Okay, so I have two particles, 1 and 2, and particle 1 can be either in psi A or psi B, and particle 2 can also be either in psi A or psi B. So if you have a combined wave function, psi A B, for both 1 and 2 together, then if you write the wave function like this, then this is called an entangled state. So you see A is in 1, B is in 2, B is in 1, and A is in 2. So you can't separate them. So if you can separate them, then they would be separable states, and they would not be entangled. But this is a feature of entanglement, you see. It's a feature of quantum mechanics. So these two concepts, these two actually not concepts, but features, are very, very important in quantum computing. It is because of these ideas that people could propose a real quantum computer. So, so you see, this is like the 0 state. In a classical computer, this is like 1 state. In a classical computer, it's either 0 or 1, psi 0, psi 1, but now it is a combination of the two, okay, and entangled. So the thing is that many systems, if you take an atom or a molecule or a condensed matter system, the wave function is entangled, and there a quantum computer can do much better than a classical computer because it can easily calculate this quantity, the quantum computer. A classical computer can also do it, but it will calculate the wave functions separately, multiply them, add them up. But a quantum computer can handle this right away. Okay. So a quantum computer actually is based on these rules. Now, again, this will remind you of Professor Popi's presentation, that the idea of quantum computation first came from Feynman in a conference in 1981, and then he published it in 1982 in a journal. Okay. So his idea was that if you want to calculate properties of atoms and molecules, you're using a classical computer. There you're using bits, and bits are transistors. So you're using transistors to calculate atoms and molecules. Why not use atoms and molecules to calculate atoms and molecules? That will be more efficient. That was Feynman's intuitive idea, and he explained this qualitatively very nicely in a paper in 1982, and before that in a conference in 1981. So that's what, and you will find this in his Feynman lecture, in this book here. And again, as Professor Pati mentioned, that this idea was actually given substance by David Deutsch, who worked out the theory of universal quantum computer. He actually worked out the details of Feynman's ideas. And in a very important paper in 1985, he explained how a quantum computer might be possible. Okay, now again, Professor Pati has talked about many of these things. So you have a system can be in state 0 or state 1. So here I'm using a different notation, what's called a ket. So this is a vertical line, a number, and a greater than sign. So instead of writing psi 0, I'm going to write it as ket 0, and instead of psi 1, I'm going to write as ket 1. You see? So then a general state can be written like this, okay? A combination of 0 and 1. Now, this is the basic unit of information in a quantum computer. So quantum computers do not use bits, but rather qubits. That is, 2 bits combined together. So if you have 2 qubits, if you have 1 qubit, you have two states, 0 and 1. So if you have 2 qubits, you have 4 states, 2 squared. And 3, you have 2 to the power 3. And if you have n qubits, you have, if you have n bits, then you have 2 to the power n qubits. So you see, and this again was explained by Professor Pati, that, so, if you have 1 bit, it's like having, if you have 1 qubit, it's like having 2 bits, you see. So if you have n qubits, it's like having 2 to the power n bits. So you can do much more computation. If the computation is very large and it needs a lot of bits, it's difficult to do that on a classical computer, but you can do it on a quantum computer rather easily. Okay. So the advantage of a quantum computer is that you're doing your operations in qubits. Okay, now how do you measure a qubit? So a qubit, as you saw, is a linear combination of 0 and 1. Now, so this is a quantum state. Now, when you measure it, when you measure a qubit, the result is not this. It's either 0 or 1. Okay, and it's 0 with a probability of alpha square and 1 with a probability of beta square. And when you add them up, that will be 1. You see. So that is important to realize, that though the qubit is a linear combination of 2 bits, when you actually do a measurement, you get only 1 with a certain probability. So the outcome of the measurement is probabilistic, unlike a regular computer which is deterministic. So the input completely determines the output in a classical computer. Here, the input only partially determines. So this may be your input, but that's not your output. The output could be either this or that. Okay. Now, the next thing to come to is quantum gates. You remember, in a classical computer, we had bits and gates. So the counterpart here are quantum gates. Now, what are quantum gates? So you've seen in quantum mechanics, we had wave functions of states. And in quantum computing, you had qubits. Now, the gates that you have actually, I've written it, it's mixed up. So the operator in quantum mechanics is gate in quantum computing. So this should be interchanged actually. So this is the connection. So state in quantum mechanics is qubit in quantum computing, and gate in quantum computing is like an operator. Remember, we talked about states and operators. In quantum computing, you have to talk about qubits and gates. So here in state, an operator gives you a state, qubit, a gate gives you another qubit. And so remember that an operator A acting on state phi gives you psi. The state can change, but the probability of finding the system will not change. So therefore, the probability whether the system is in state psi or phi is always 1. Okay. Now that's the conservation of probability. Now, if you use this property, then you can easily see that A has to be unitary. You know, we can work out the mathematics. So unitary means inverse is equal to dagger. So in a quantum computer, the gate is always a unitary operator. Okay. It can't be anything else. If it's anything else, it will not work because it will not satisfy conservation of probability. Now we know what are qubits, now we know what are gates, and so let's move on. So let me give you some examples of gates. So you can take one qubit, which I call, say, 0, and you can apply a gate. It's called a Hadamard gate, and this will give you a linear superposition. So superposition states are they are there in quantum mechanics. So this operator or this gate will give you this state, and if you have one, you'll get this state. You see. So this is a single qubit. But if you have 2 qubits, you can still have gates. Say what are called C0 gates. So that means you have 2 qubits. So you can have 0 and 0. And if you apply a gate called C0, you will get again 0 and 0. If it is 0 and 1, again you get 0 and 1. But if it is 1 and 0 and you apply this gate, you get 1 and 1. Or if you have 1 and 1, you get 1 and 0. So this 2 qubit gate, actually, what it does is, it sees what the first gate is. If it's 0, it doesn't change the second gate. So the gate sees what the first qubit is. If it is 0, it doesn't change it. But if it's 1, it changes the second qubit. So here 1, 0 becomes 1, 1, and so on. So these are the two, single qubit gates and double qubit gates are really important because using these gates and qubits, you can form a quantum circuit, and that's effectively a quantum computer. So a quantum computer needs qubits, it needs quantum gates, and then when you put them together, you have a circuit. So an example is this. You can see that I have 2 qubits, Q0, Q1. So the first qubit is 0, the second qubit is 0. So I apply a Hadamard gate. What it does is, it changes the first to 0 plus 1. The second is unchanged. Okay. Then I apply what's called a 2 qubit gate, and that, what it does is, the first one is 0, so it doesn't do anything. The second one is 1, so it changes that to 1, 1. So as a result of these 2 gates, the 0, 0 state becomes 0, 0 plus 1, 1 divided by square root of 2. Okay. Now then you can, so now that this is the output, you measure it. Now you can measure the first qubit or the second qubit. So you see the first qubit here is 0, the second is, first qubit here is 1, the first qubit there is also, 0 and 1. So if you do a measurement, the outcome is 0 or 1. Now, if you again measure the second qubit, it's 0 or 1. Again, you get 0 or 1. So you see you have 4 possibilities. You can have 0, 0, 0, 1, 1, 0, and 1, 1. So these are all possible. Okay. So each of them has a certain probability. Okay. Now, let's do it. Okay. So let's do an experiment. So we take 0, 0 plus 1, 1. And now you would expect to get only 0, 0 and 1, 1. But in reality, what happens is you not only get 0, 0 and 1, 1, but you also get 0, 1, and 0, 0. Now, that should not be there, but it happens because of errors. See, the good thing about a quantum computer is that it's powerful because of the qubits, but the bad thing is that it has errors. Now, the errors can come from the qubits. When you're doing the experiment, the qubit can flip. The 0 can become a 1. Okay? Or, when it's in an excited state, it can decay to the ground state, you see. So the current computers are called the noisy intermediate scale computers, and one can correct for these errors, up to a certain point. Now, but in the ideal case, you have what's called fault-tolerant quantum computing, where you take many regular qubits to form one logical qubit. So the error averages out, and the error is gone, more or less. So right now, as the IBM speaker, Dr. Goel said, that we have currently we have the noisy intermediate scale, so you're using error mitigation right now. But the point here that I'm trying to tell you is that though we should get only 0, 0, and 1, 1, the actual measurement tells 0, 1, and 1, 0. So that's proof that there is errors when you do measurements in quantum computing. So well, people have, we know about trap time quantum computing. This is already discussed. And we have already talked about superconducting quantum computers. Dr. Goel talked about that, and I think Professor Davis was going to talk about it. I'm just going to skip it. So now some of the applications are in factoring large numbers and carrying out searching lists. And then, okay, I'll talk about some actual applications. Now, how do we calculate properties of atoms and molecules using a quantum computer? Remember, I told you that when you calculate a quantity, what you're, which was the integral of psi star, and the operator and psi. Okay, that's the thing that you want to calculate, you see. So now we want to calculate the energy of an atom or a molecule or any other property. And so the system is in some general state, and we all know about the variational principle. Those of you who may not know, let me tell you that if you have a wave function, general wave function psi, then the energy is this integral psi star psi, and this is greater than or less than the ground state energy. Now, we take the wave function and we allow it to depend on some parameters. So the parameters are theta. So the energy becomes a function of theta. So you have the same integral. Now this should be greater than or. So the minimum value of this quantity should be the ground state energy. So what we do is we vary theta till the energy becomes a minimum, and that is the ground state energy, you see. Now, how do we do it on a quantum computer? See, in a quantum computer, it is, yeah, so the important, this is the key thing. The key step is we write psi as a unitary operator which depends on some parameters, and it acts on a known wave function. Okay. So this is the most important thing here, this step. Then once we do this energy integral that we have here becomes integral phi 0 u h u phi naught, and the theta dependence comes from the operator u. So now the phi naught is a known wave function. So you've seen the connection between qubits and wave functions. So phi naught here is they contain electrons, so which are qubits. So this can be expressed in terms of qubits. Now you've seen that unitary operators are needed for quantum gates. So here this is a quantum gate. Now the Hamiltonian, fortunately, can also be transformed in terms of unitary operators. So everything that you have here is in terms of qubits and quantum gates, and that can be calculated on a quantum computer. Okay, so let's see what we get. So the first results were carried out by a group at Harvard University and then at IBM. Now I'm going to talk about our results, which is in collaboration with we used the quantum computer RIKEN, a national lab in Japan, and we calculated the energy of lithium and lithium-like ions, and we compared our results with best classical computers, and we had to do a lot of error mitigation. I'll just finish up. So we got a result of 99% accuracy, and then this was on a superconducting computer, the trapped ion. We calculated the dipole moment of strontium hydride because molecules can have dipole moments. There we got an accuracy of about 95%, 99% for different cases. Now that we can calculate the energies of atoms and molecules, these are simple atoms and molecules. This is the first step to calculate the energies of large molecules. A drug, when you want to make a drug, so that's a molecule. So you have to see how well it binds to the protein in the body. So there we'd be calculating much larger energies. But this is the first step in that direction. Okay, I'll just skip that. So quantum advantage, again, I'll skip that because briefly, we have some examples of quantum advantage where, very few, where a quantum computer is faster than a classical computer, but there are very few such cases. Mostly in some simple mathematical problems, and more recently in sort of, in some physics problems. So the conclusion and outlook, I'm sorry for the delay. So this is an emerging area of science, and it's based on quantum mechanics. That's the first thing to realize. So quantum computing is a combination of quantum mechanics and computation. And of course, again, I'll repeat that we need superposition and entanglement, and this is what makes a quantum computer possible. And the speed up has been predicted in many cases, but not actually realized in practice. Okay, so there are a few examples of quantum advantage of mathematical problems, and for physics, only two so far. Mostly in condensed matter systems. But the methods of calculation, that is the algorithms, they're improving. And more importantly, the hardware is improving. Very recently, that was just a few days back, a company called Quantinuum announced that it has 98 physical qubits and 48 qubits that can correct for errors. Okay. Now, of course, in the future, quantum computations of atoms and molecules will find extremely important applications for drug discovery, for designing new materials, and many other things. Thank you very much, and sorry for having taken some extra time.
Thank you so much, Professor Das, for this excellent talk and explaining really beautifully to the young kids. So we have some time for taking some questions. Please raise hands if you want to ask some questions. Okay, maybe I can begin.
Okay.
So when you talk about these errors, that is, can we use this error for something, or it is really a problem? So-called quantum errors.
Yeah.
So yeah, this one.
Yeah.
So these errors, whatever coming, the 0110, as I understand. So can we also use it for something, or really the error in a bad sense?
Well, I mean, as far as my understanding goes, and it's errors in a sort of a bad sense.
Right.
But I do know of some people who have proposed that errors and noise can also be used in a good sense.
Yeah.
But I am not really sure. Perhaps Professor Potti might know. I mean, whether one can use errors to one's advantage.
Yeah. I mean, why I ask, because in condensed matter physics, many times noise can be also taken as a signal, the short noise and many other things.
I see.
So I thought maybe these are quantum errors, so we can also think of using them for some applications. I don't know, just.
Yeah.
So, hello.
Yeah, please.
Yeah. So in this context, you cannot use errors for something useful. But having said that, it is true that if you have noise in uh, different kind of noise, that can be exploited to do something better in quantum computing and say quantum communication. So for example, it has been shown that if you are sending, say, like teleportation, through entangled channel, if some noise is acting on one part of this, entangled pair, then by suitably modifying this noise, you can enhance the fidelity of teleportation compared to what it would have been otherwise. So there are cases where you can exploit, but here no.
Yeah, so you see, for example, we have a state which is a linear combination of 0, 0, and 1, 1. So we want to actually give it to a quantum computer, and we should expect 0, 0, and 1, 1. Okay, that is the probability of this being half and the probability of that being half. But that is not what we get from a quantum computer. So it's a known input, so the output should match that, but it doesn't. It doesn't. So these two states should not be there. But when you do the actual computation, that is computation in a real quantum computer, this is what you found. This is what we found using a IBM quantum computer. And this is because there are errors which should not be there. So, if you have a qubit which is 0, it should remain 0 throughout the experiment. But sometimes, because of the environmental noise or perturbations, the 0 can become 1. Like a spin up can become a spin down. And that is not what we want.
Yes.
Yeah. Yeah. Or just an electric field, for example, any kind of perturbation will. Okay. See, it's basically a question of decoherence and external perturbations.
Yes. Okay. Thank you. Any questions from? Okay, you have a question. Please go ahead.
Yeah, I was just wondering about that calculation of strontium hydride. So, do you use the shell structure there? For example, for strontium, you take 2 electrons and hydrogen 1 electron, or you take 4 in the n equal to 4. With the cell 4 also, it is not fully occupied. So, how many electrons are there in that calculation?
Yeah.
In the strontium hydride.
Right. So you see, strontium has 38 electrons and hydrogen has 1 electron. So it has a total of 39 electrons. But in the actual calculation, we consider 12 electrons. We consider 12 to be active. Okay. So we've actually considered both 6 and 12. So when we take 6 qubits, we get 95% accuracy. And for 12, we get 99. But this is after a lot of error mitigation. So, if you had not done error mitigation, the accuracy would have been like 40% or something like that. So we've also combined machine learning to remove the errors. So this error mitigation that someone talked about earlier is very necessary. So you have to do some analysis. You have to understand what could have gone wrong. Maybe the bit has flipped, or the phase of the bit has changed, and so on. Yeah, the other error is the error due to the gates. So you have qubits and gates. The gates cause a lot of errors. Those also have to be corrected. So after all these corrections, we got this accuracy. Now, I should say that this is sort of a world record. No one has done more than 12 qubits, for a molecule. We have done for a dipole moment. Pan's group in China, they have also used 12 qubits for a much lighter molecule and for the energy, not for dipole moment. So, but I'm expecting other groups like Quantinuum to do much better.
Okay, so I think time is running up. Yes. We have some memento. All right, so let's thank Professor Bhanudas again. Please clap.
Thank you. Thank you. Thank you.
Okay, so let's thank Professor Bhanudas and let's move to the next talk, which will be given by Professor Vedang Das Mohanty, our very own senior professor from School of Physics, NISA. Now we will go to high energy physics, and he gives excellent talks. And I think, yes. He has just presented his iPhone to me in lieu of 2-3 minutes extra time. It's a good deal. So I think everybody knows Professor Vedang Das Mohanty, but just for the young kids, I just want to say he's one of the superstar of Indian science, and he works really on very interesting things. And he has been awarded the Bhatnagar Award, the Infosys Award,
Thank you,
and
Subhankar.
many other things. But
Thank
I would
you very
request
much.
him for
Give
for
me
a
that
talk.
2 more minutes. So, very good afternoon to all of you, and thanks to Tapan for giving this opportunity to speak here. It was a little bit difficult because this is on quantum theme, and of course, in our field, as Professor Singh told in the beginning, we need quantum field theory to explain or understand our data. But I have brought to you 2 examples where some principles of quantum mechanics helps us to understand what we make measurements. The title has Quarks, Spins, and Perfect Fluid, a quantum story from the early universe. He suggested a catchy title, so that's why I put it like this. But I'm going to interact with you all. If you do not interact with me, then there is no point. The lights will be off, don't sleep. So let's, I was last week in a conference in Mumbai, and the conference organizers took us to Elephanta Caves. It has beautiful statues of Lord Shiva. And then when I was roaming around, a security guard told me, can I take some photo for you? I said, okay. And then when later on I looked at the photo, I found this. The red one is myself. How can I be at 2 positions at the same time? Now, who can answer? You see, I mean, the other things are all, I mean, there is no change, right? I have not added 2 photos, by the way. Huh? No answer? I thought you all are, yeah. So that I'm technologically challenged, so I didn't know that. But then I learned. But if I were an electron instead of a person, then maybe nature itself, not the camera, would truly allow me to exist in 2 places at once. I'll be described by a single wave function unless someone looks or makes a measurement. And then the wave function collapses, and then you have. So then I started, when I'm preparing this talk, I have a habit of trying to put things down and see what are the contrasts. I made this table. What does camera world tell me, and what does quantum world tell me? So quantum world, as you heard from all the experienced speakers, the wave function describes one particle spread across 2 positions. The particle is really in a superposed state until the measurement makes it to choose one. The measurement collapses the wave function into a definite state. That is, I think, what we all learned since the morning. Now let me go back to my own area. How many of you know who is this person? In the photo. You have to, somebody told, speak loudly. Dalton, yes. And what is he known for? Atomic theory. And what does atom mean? Something which cannot be divided further. Okay. And then this gentleman came. Who is he? Don't know? Thomson. And what did he discover? No, plum pudding model. So first he has to discover something to make the model. So he found electrons, right? And then who is he? Rutherford. And what did he find? How did he find? Did he do the experiment? And who were the two students who did? One of them was a UG student, Geiger and Marsden. And then he interpreted the data and told us that an atom is made up of a positively charged nucleus and electron. And he found it from scattering of alpha particle over a gold foil. He also found out proton. And who is this? Somebody said the correct answer. So he is Chadwick, who discovered the neutron. So at that point, all of us were made up of proton, neutron, and electron. Okay? Then in between, you heard today morning a very nice talk about this person. Okay? And he gave this expression, right? He has a connection to Orissa. He was the first one to win the UNESCO Kalinga Lecture Award, which is given for popularization of science. And this was his PhD thesis work. But it, it didn't come about just like that. There were two very important principles in physics existing that time. One is related to optics, called as the Fermat principle. You heard about it? What does it say? Okay, very good. And there was a principle of least action. Are you aware of it? And he was able to connect the two to give this. Of course, his thesis is in French, but if you read it, you will see how profound he was able to connect these two distinct ideas to bring it together to give this expression. And why I show it, I'll tell you. Now, this is something which has unit of length. This has something which has sort of energy, connected with energy. So what you see, you can probe small distance scales if you hit the object with high energy. Okay? This can be used, so if you use a particle, higher the energy, it will probe, smaller the length scales. And that's how you found out that protons and neutrons are actually made up of still smaller objects called quarks and gluons. What was done is you take proton, which is an ionized hydrogen, and you impinge it with an electron. Okay? And then you look at the scattering pattern, exactly like alpha particles scatter of gold foil. And this scattering pattern told us that protons and neutrons are made up of still smaller objects called quarks and gluons. Okay? This principle high energy physics uses to find out how smaller and smaller particles. So as of now, what are we all made up of? Quarks. Atoms to ho chala gaya. It is made up of quarks, gluons, and particles like electrons, right? So that is what we are the basic building blocks of matter: electrons, particles like electrons, quarks, and gluons. And there are four fundamental forces in nature. Strong interaction. This is the force which holds quark and gluons inside protons and neutrons, or protons and neutrons inside the nucleus. That's strong force. And then electrons and the positively charged nucleus to form atoms, or atoms to form molecules, electromagnetic force. And then there is those force which helps us understand phenomena called as radioactivity, the weak force. And then there is gravitational force, which allows us to walk, Earth move around sun, moon moves around Earth, and so on. This taken together, we can build our universe. But we don't see free quarks and gluons. There is no free quark and gluons in this seen in this current nature. Okay, then how can we study its properties? Why should we study its properties? Because each one of us is made up of it. We should know what is the material that we are made of. What is its viscosity? What is its conductivity? What is its diffusion? Right? So how can we study its properties if it is not free? Then you can ask why it needs to be free. Okay, so let's see. Suppose I give you water. All of you know water? Huh? So water is made up of hydrogen and oxygen. So hydrogen is a fuel, right? Hydrogen burns. Oxygen supports burning. Water extinguishes fire. So if I give you water, and again this is at a popular level, if I give you water and tell you to extract properties of constituents like hydrogen and oxygen, it's difficult. But if you have a free system of hydrogen or oxygen, then you subject it to external conditions and you can get its properties. Similarly, to understand the properties of the visible, what the visible universe is made up of, the building blocks, you need them in a free state. Now, where do we get, were they ever free? So today morning, Professor Singh said there is a model which describes the evolution of universe. It's a Big Bang model. And as per that model, when the universe was a microsecond old, that is 10 to the power minus 6 seconds, temperatures were 10 to the power 12 Kelvin, million times higher than score of sun. There was a free system of quark and gluons. We call it as quark-gluon plasma. Current universe is 14 billion years since that time. Temperature is 2.7 Kelvin. Quarks are always confined inside particles such as protons and neutrons. So how do I get to that matter? So perhaps I have to heat the matter to temperatures of 10 to the power 12 Kelvin so that the matter melts into its fundamental constituents, and then I can try and study its properties. So that is the basic idea that we do, and the machine which allows us to do is a collider. The largest particle accelerator in the world is the Large Hadron Collider. It has a circumference of 27 kilometers. It collides two heavy ions at relativistic speed. So what happens is a large amount of energy is deposited in a small volume. So the energy density is large. Can you recall a formula which connects energy density to temperature? Have you heard about Stefan Boltzmann law? Energy density goes as T to the power. Okay, so if you have large enough energy density, you may reach large enough temperatures. And if the temperatures are of the order of 10 to the power 12 Kelvin, you may form a free system of quark and gluons. And then you can study its properties. Now, in this experiment, this system stays for femtosecond. And the size is femtometer. Okay, that makes it extremely challenging to do these experiments. But ironically, to detect these femtoscale systems, we need meter scale detector. Here is a human being, and you see the scale of the detector and the complexity involved. So we have to really pull together the best of the brains and minds from 40 countries, 170 institutes to build this experiment. And that experiment is called ALICE, and here are the people coming and working from those countries. Okay, so I will tell you that I'm not because I have to connect to quantum mechanics, so I'll not show you the results, but you have to believe me that we have reached temperatures of 10 to the power 12 Kelvin. Just to give you the perspective of how large a temperature has been reached, so the lowest temperatures are something of the order of 10 to the power minus 10 Kelvin. Then comes 10 to the power minus 6 Kelvin trapped ions. If you want, you can discuss with Professor Ashok Mahapatra, who is going to give a talk on cold atoms. That's his expertise. He can tell you more about the temperatures here. The universe has a temperature of 3 Kelvin or 2.7 Kelvin. The temperature in this room is 300 Kelvin. Temperature on the surface of the sun is 6,000 Kelvin. Core of sun is million Kelvin. A thermonuclear explosion can give you 10 to the power 9 Kelvin, and the temperatures which are reached in this nucleus-nucleus collisions are a staggering 10 to the power 12 Kelvin. That's the matter which we produced. And if you still don't believe me, we have entered Guinness Book. Huh? You can see, right? To create the highest artificial temperature. Okay. Now that we have created a free system of quark and gluons, we can study its properties. One of the property I will discuss today is viscosity. How many of you know viscosity? What is viscosity? Oh, you start saying. You have to tell loudly. You cannot take that much time. I have limited time. Viscosity is resistance to flow. Okay, very good. Now I will, before I tell you more about viscosity, this is something which you all have studied in quantum mechanics. Today, all the talks you have seen, that is the uncertainty principle. Okay, I'll tell you why I'm discussing this. Uncertainty in position, momentum has this, this form. Now, what it tells us that more precisely we know a particle position, less precisely we know the momentum, and vice versa. It's not a limitation of the measurement, but it's actually a fundamental property of nature. Now, you must have read examples of where application of uncertainty principle. For example, you take an electron in a box, and if the width of the box is L, you can find its momentum, and then you can use uncertainty principle to see what will be the minimum kinetic energy. The concept of 0-point energy, the underlying principle is uncertainty principle. Okay? Now, this same uncertainty principle tells us that if there is a quantum fluid, then it will this viscosity, kinematic viscosity, will have a lower bound. And that's what I wanted to tell you. So before that, let us go through what we know of viscosity. It is, as you have read in textbook, force is proportional to velocity gradient. The proportionality constant is called as coefficient of viscosity. And when you compare viscosity across fluids, you take kinematic viscosity, viscosity divided by the density of the fluid. You take out the density effect. You know water flows more smoothly, less viscous than, for example, honey. Before I show the results on viscosity of what we are made up of at high temperature, let me show this thing. This is an experiment. You can look up Google and you can find. This has pitch. Pitch is something which is used to make roads. It is put in this funnel. Here is a beaker and shielded from external environment. And you know, only 8 drops have fallen since 1927. And nobody has seen exactly when this drop fell into the beaker. But nowadays we have CCTV cameras, we can of course record and see. So this tells us it's highly viscous. It's about 230 billion times more viscous than water. So keep these in mind, water, honey, pitch. What do you expect is viscosity of matter we are made up of? What's your expectation? Anybody? Close to water. Okay, let's see. So before that, let me tell you, viscosity is of course resistance to flow. Maxwell in 1860s actually calculated the viscosity for a dilute gas. It's 1/3 times number density, momentum transfer, mean free path. And I want kinematic viscosity. I will divide eta by entropy density. Entropy density goes as number density times Boltzmann constant. And I will use uncertainty principle, and immediately you see there is a lower bound to viscosity just from uncertainty principle, the basic principle in quantum mechanics, to what eta by S values a fluid can have. A more sophisticated string theoretical calculation which connects to in a particular limit to calculations in gravity tells us that it would be 1/4 pi. So what I'm trying to tell you in a simple way, that some natural principles tell us that there would be a lower bound for viscosity. You saw highly viscous fluid pitch, but you can have the smallest values of about 1/4 pi. Let's see what did we get. So we have an observable which calculates flow, and it's obtained for different kind of particles that we measure. So it's momentum of the particle. This is the data point. How do we extract the kinematic viscosity from data? We solve energy momentum conservation equation. This is just energy momentum conservation equation with eta by S as a parameter. If I take eta by s as 0, this is where I should expect the measurements to be. If I dial up the eta by s, I will increase the viscosity. Flow has to decrease. So the y-axis has to decrease. And that's what you see, 1 by 4 pi. This is already 1/20th of that of water. And then you can go on. And what do you see? You see that the viscosity of quark and gluons at those high temperatures are very close to the 1 by 4 pi limit. Okay. Now, when we get this result, we were surprised. We didn't know what it means. Some thoughts I put together here. In a classical particles, they are distinguishable, random, and colliding. They follow Maxwell-Boltzmann statistics. Motions are usually chaotic, no collective, no coherence. But if you have a quantum fluid, it's characterized by indistinguishable, collective, coherent, a perfect flow, following specific kind of statistics. It seems at these extreme temperatures and density, quantum rules the shape how matter flows. Somehow, we think it's a bunch of quark and gluons. It's not. It's flowing. It's flowing with the smallest eta by s values known so far. Now you can put together the eta by s and x-axis. I have to normalize by a critical temperature to put other systems in place. And you can see compared to water or helium, this is where the eta by s of quark gluon plasma lies. This is the property. This is very close to the lower bound of 0.08, which comes from uncertainty principle. It just seems that even at trillions of degrees, quantum mechanics refuses to let the fluid flow infinitely easy. Eta by s is not 0. Okay, that's a universal nature's way of saying even perfection has a quantum price. Okay. Now the second topic, the last one I will want to discuss is spin. Now, discovered is already on the slide, but can anyone say? And what did they do? They had silver atoms placed. There were magnetic poles, and they found that there were two directions in which they were going, and that's how spin was obtained. There has been mention about spin. I will not go into all details, but I just want to tell you the spin of a particle that we are talking about is an intrinsic property, just like a charge and mass. It is not like spinning around something. It's not that. Okay. Now, fundamental particles have spin. Okay, these are the values. Spin is very useful quantity to have. It's a quantum nature, but very useful because electron spin explains magnetism, atomic structure, fine structure splitting. Nucleus spin is used. Do you know what is NMR used for? At least full form of NMR? Nuclear. So this is a nicer also. There are a set of NMRs you can find. This is used to find out the structure of molecules. Very useful to know structure of molecule, for example. And also MRI. Do you know what is MRI? Yeah. And again, it is all because of the spin which you get these societal applications. So if there is angular momentum and there are particles with spin, there will be spin orbital angular momentum interactions. Okay. Can you give me examples where spin orbital angular momentum interactions you have studied? Anyone? No? Huh? Okay, any other? Okay, we'll come to that. So we have these quarks and gluons and hadrons, they all have spin. And if we have angular momentum, then can we see spin orbital angular momentum interaction? Remember, in femtoscale systems, okay? And systems which finally comes down to no free quark and gluons are seen, confined systems which hadronize. Can we see the spin orbital angular momentum interactions? Okay, you have seen that in atomic physics, shell model in nuclear physics, spintronics in condensed matter. Now let's see in our system. So in our system, two heavy ions are coming from opposite direction. The distance between the center of the two ions is called impact parameter. Suppose the impact parameter is non-zero, that means they don't collide head-on. Then what happens when they collide? The system imparts a torque, and you get an angular momentum of the order of 10 to the power 4 h bar. The largest ones which are measured in laboratory are of the order of 70 to 100 h bar. In this system, you can have large angular momentum. Large angular momentum, and you have particles with spin. There could be spin orbital angular momentum interaction, and that could lead to polarization or vorticity. Okay. Now, experimentally, how do we measure it? How do we see if the spins are aligned along the direction of the angular momentum? And you need quantum mechanics to understand that. So how do we? So this is an expression which is purely derived from quantum mechanics in 1970s. And that is what experimentalists use to figure out if spins are aligned along the angular momentum. So I will explain to this. This is particularly valid for particles with spin 1. So it can have z components, -1, +1, 0, right? Now, these are called vector mesons, spin 1 particles. They decay into daughter particles. The angle made by the daughter particle with respect to the angular momentum direction is this theta. And we can measure this quantity experimentally. Now, if you have a box where all the spin states are random, so spin 1, +1, -1, 0, so each has same probability, 1/3, 1/3, 1/3. What is rho 0, 0? It is the probability to find that a vector meson is in spin state 0. So if everything is random, it will be 1/3. And you can substitute 1/3, then this angular dependence goes away, okay? 1/3, so 0, this goes away. So experimentally, you will measure a flat distribution. If the spins are aligned, then rho 0, 0 will be different from 1/3. And then you will have an angular distribution, depending on how strongly the spins are aligned. So this is the technique which we use, and this is purely derived from quantum mechanics. And you can do the same thing for spin half particle. The expression is slightly different. And there is a coefficient sitting here which is called as polarization. And this has been measured, percentage polarization with the energy with which we collide the heavy ions. And if you try to extract the vorticity, again with the assumption that the entire thing is gives to a vorticity of the fluid, temperatures are known, this is a constant, this is what we experimentally measure, then the vorticity that you get is 10 to the power 21 rotations per second. Again, with a very, very strong assumption. Huh? So just to give you a perspective, we have vorticities. You have seen vorticity. This is, I think, Fani cyclone hitting Odisha. Okay, you see. And then you have in the coffee cup, tornadoes, river. All these have vorticities of the maximum of the order of 1,000 rotations per second. When I was going for lunch a few days back in Mysore, I saw something called dust devil. Do you know what is its Odia? Khondya Bhutta, yes. Just see. It's also having, so I immediately stopped and took that recording. So what we found is, we have perhaps found the most vertical fluid known to us in the laboratory. So with that, I will end. What I wanted to tell you is, we, through our experiment, have managed to create the temperature conditions which existed when our universe was a microsecond old. It's a free system of quark and gluons. This we achieved by colliding heavy ions at very high energies. Temperatures were 10 to the power 12 Kelvin. Matter melted into its fundamental units. This allowed us to study the properties of these quark and gluons. One property which I described to you is the kinematic viscosity. Uncertainty principle tells that the lower bound is of the order of 1/4 pi, And this fluid turns out to have kinematic viscosity of the order of 1/4 pi. Hence, it's called the perfect fluid, which is in agreement with quantum mechanics. We saw evidence of quark spins getting aligned with angular momentum. Perhaps we formed the most vertical fluid known in laboratory. And I hope I've conveyed that we have somehow managed to convey that we have found some quantum properties in the system that we have seen. Before I end, I want to put this slide for two reasons, this plot. I'll take this opportunity to tell you what are the scopes in mega science. And the second is, I was in this conference in Mumbai. People are now trying to use quantum computation to compute this evolution of universe. 14 billion, temperatures over 30 orders in magnitude, going through changes in degrees of freedom. And it's an ambitious idea, but I was shocked to see a talk being presented that how about using quantum computers and its power to understand how the universe evolved to the current state. So, you can jump into that science. But let me tell you, I was talking about scenarios of a microsecond-old universe. Both the Department of Atomic Energy and Department of Science and Technology are funding projects at every stage of evolution of this universe. If you want to know a few minutes old universe, you can join the FAIR facility at GSI Darmstadt. India participates in it. If you want to know when the first stars started forming, 100 million years old universe, you can join Square Kilometer Array project, where India participates. If you want to know about how the structure of the universe got formed, 500 million year old universe, you can join 30-meter telescope, which India participates. If you want to know how fusion process happens, you can join ITER. And if you want to know a few billion years old universe, you can join LIGO, one of the centers is happening in India. So great opportunities for young minds if you want to join these mega science projects. Thank you very much.
Thank you. Thank you for this very nice talk. It's open for questions now. Please raise hands. Yeah. Can you take the microphone?
Hello. Thank you for the talk. Professor, you mentioned about kinematic viscosity. So isn't it obvious that viscosity is the resistance to flow? So is there anything known as static viscosity as well?
No, that's a terminology which I use to remove the density effect so that we can compare viscosity for different fluids. So it's just viscosity divided by a quantity proportional to density. Here it's entropy density. You can use another quantity.
Thank you.
Students, I think everything was clear. Okay, okay, maybe here. Can you please come to the front to speak a little bit? Yes, you go ahead. Go ahead. Yeah. Only this much loudly you speak. In class we used to shout so much. Ah, they're there. Yeah. Quark, anti-quark, and gluons. They're there. Yeah. Phi operator on vacuum, well, huh? Maybe you are talking about creation operators, which, yeah. But what is your question? I mean, X, what does X represent? How do you calculate position? You take a expectation value.
How do you calculate? You have to calculate, no? Any observable, you have to calculate by calculating an expectation value. But localized where? I mean, you have to tell me the system. In a particle in a box, you can calculate expectation values of X. You can calculate momentum. Yeah. So localized where? If you are talking about free particle, then no. It's then you have to do something called box normalization to understand free particle. Yeah.
Okay,
You,
here
you,
is.
you are from Nicer? Out. Okay, then we can discuss later. Huh?
During the tea break.
Or I can go there.
Yeah. So why do you think Gluon won't be a perfect fluid? I mean, I can put the question in a different way. Whatever the deviation you got it from 1 by 4 pi, then what is the reason that it deviated from the perfect fluid?
Yeah, I mean, the reason I don't know, it is a strongly coupled system. Now, such systems also exist in, say, graphene is also a strongly coupled system, or even cold atoms are a strongly coupled system. But with this difficult experiment, it's pretty close to 1 by 4 pi. There could be many other factors which could influence it to be a little higher value. There are correct. I mean, so several factors. I don't. This itself was already a surprise. Why it should be like this?
Sir,
sorry.
sir, could you please elaborate on vector mesons? Like, what are they?
So the particles have spin. Those who have spin 1, that means the Z components can take up values +1, -1, 0 states. Those spin 1 particles are termed as vector mesons. Your first year, na? Nicer? Okay.
First year. Yes. Please be loud until microphone reaches you. Continue.
Viscosity, as I know, as you have studied, I have studied, it is force is proportional to the gradient of velocity of different layers, like fluid motion. The proportionality constant is the coefficient of viscosity. It turns out for certain systems, like Maxwell has calculated, the viscosity arises due to momentum transfer. It's related to the number density, momentum transfer, and the mean free path. And then you can invoke quantum principles to see does it have any bound. That is how I put it. But definition is what you and I studied. How to quantum mechanically define, I don't know actually how to define it out. Yeah.
Okay. So I think, you have maybe the last question. He is already running out of time.
From the you said about from the Big Bang model when universe is
Not
created.
mine. Yeah, Big Bang.
From the when universe is created, particles are created. Can you say something about what about dark matters and dark energy?
Yes, and that is left for you to discover. So, all that you see in this what I understood is if you look at the total energy matter budget of the universe, all that you see is roughly 5%. And the other part, about of the order of 25%, is dark matter. There are many experimental evidences that such a matter should exist. And the remaining of the order of 70% is dark energy. Now, dark matter has not, what dark matter is made up of has not been found yet. 90 years as studies are going on. We have not figured out what it is made up of.
Some models like we predict that this means particles or something else.
Yeah, but all models has validated by real measurement. Measurements have not seen it.
Okay, we discussed this during tea break. Thank you. So let's thank again Professor Mohanty for this excellent talk.
Phone.
Yes. So,
did what?
Okay, please welcome. The next talk of this session is given by Professor Sadiq Rangwala from Raman Research Institute in Bangalore. He is working there as a professor. He's an experimental atomic molecular optical physicist working on trapped and optical ions, cold atoms basically. He has been awarded the Bhatnagar Award, P.K. Iyengar Award by the IPA, and is a fellow of the Indian Academy of Science. So we are very much looking forward to your talk.
Can you hear me? Okay, fantastic. I'm just going to do a little thing here and hopefully it works now. No, my slide switcher is not working for whatever reason. Okay, never mind. So we'll figure it out. So I'm Sadiq Rangwala. I'm an experimental atomic physicist from the Raman Research Institute. What you're seeing in the center of this image is, in the center of the slide, is an image of two trapped ions which are in an ion trap in our lab, and they're glowing because we are shining light on them, and this light is being scattered of these particular ions, and we are able to observe them using some optics and a camera. And what I'm going to show you is a really interesting domain where we are able to image single quantum systems, and we are able to extract a lot of physics out of these systems. And that is the adventure that I want to take you on. I mean, of course, it's very difficult to follow up on the previous two talks, which were like, both of them were absolutely fascinating. But nevertheless, I shall make my attempt. So, so I want to first start by, something's the matter. My screen is frozen. Okay, perfect. It works now. So a bit of my first two slides has been covered by Dr. Goel in the morning at the IBM talk, basically, which is what is quantum technology. She introduced quantum 2.0 and so on and so forth. And so I'm going to skip through a lot of things here. And what I'm going to point to you is that if you want the modern quantum technologies, not your cell phones and other things, but the quantum computing and quantum sensing, etc., to enable these technologies, what we need is, we need to leverage quantum mechanical principle, like what Professor B.P. Das talked about, and allow for specific manipulation of quantum states to develop the technologies and devices. This is basically the idea. And what does it require? It requires systems that are quantum mechanical, which is an obvious thing. So these systems should be identical to each other. If we are going to make a large quantum system and start doing things with it, we need to be able to manipulate them. If they are not the same as each other, then every system has to be manipulated differently, which is awfully annoying if you are an experimentalist. So you need to be able to isolate these systems and combine them on demand, because your process may require any of these flexibilities in order to be able to work the thing. Then, and what makes the whole thing possible is that we have this thing. So we need precision electromagnetic fields to perform quantum operations on quantum systems, do entanglement, and so on and so forth. And in addition, we need to have sensitive and low noise detection. so that we can process the information, we can put information into the quantum arrangement and take information out of the quantum arrangement usefully. So why do we, so I work with atoms and ions and molecules. And why do I want to work with atoms and molecules? There was a question about which quantum system is favored to the IBM person. And the simple answer is all quantum systems will find their niche. Okay, it's not like there's going to be one winner. If that winner had to emerge, chances are it would have already happened. Okay, it's been around for 20 years now that people have been putting in a lot of minds and resources on these problems. So quantum ions, so all different quantum systems will flourish in their domain of advantage. And one thing that had been, I'm going to tell you about ion traps. And one thing that had been talked about ion traps is it is not scalable. So let me tell you what we are after in our lab. We are developing 2 teeny tiny ion trap quantum computers. They're going to be side by side, but they're going to be separate. And we are going to communicate from one computer to another so that we can map the entire quantum state on one computer, from one quantum computer to another quantum computer. And if we can do that, we can essentially solve the scalability problem to a large extent for ion traps. And this is one of our primary longer term goals, just so that you know. I mean, people are thinking about how to advantage their things, so their interests. So I work with atoms, molecules, and ions. And there's one absolutely key advantage of working with these systems is that they come in identical copies. Nature makes them for you. You have a rubidium atom here, you have a rubidium atom at the other end of the universe. They will show you the same physical properties. You can work with these things with the same laser system which you carry from one place to another. So this is phenomenal. So it is free of engineering costs at that level. That doesn't mean that there is no engineering required. Complicated engineering is required. And but we have a magic trick, which is lasers. Lasers are phenomenally effective at manipulating atoms and ions and molecules. So this is something that we do. And yeah, and it is in the visible and near IR that they really are lasers are really nicely available. And this is where the atomic atoms are, and we really can work with them very easily. Detection is also very simplified at these frequencies because, as human beings, we are continuously exposed to visible light and near IR light, and we have honed our detection technology over generations for taking advantage of this particular thing. So we have some really interesting materials and detectors for such things. So this is why atoms, ions are always going to be there. It's part of the puzzle. Which technology wins is a question for later, but this is a very, very relevant technology out there. And so now you want to hold so if you want to work with quantum systems, you have to learn how to hold a quantum system in space. It's an atom. Atoms are moving, molecules actually in this room are moving freely. And the question is, you want this one thing, which is you want to locate it in space. So this is a very important problem. And so if I'm working with ions, trapping ions, then there is an issue, because if I use electric fields to try and put an ion localized in space, then it does not allow me, Earnshaw's theorem does not allow it. And so what happens is that if you take a positive charge, electric field lines are moving outwards, if you look at it. And on the other hand, if this ion has to be held, then in all three directions, the force has to be inward on the ion, but then you have a contradiction because the force is proportional to the electric field and the sign is switching, so there is a contradiction. So Earnshaw's, this is the proof that of Earnshaw's theorem, which basically says that you cannot trap an ion using static electric fields. A charge cannot be trapped using static electric fields. So what do we do? Well, we start moving electric fields. So what we do is we combine a static electric field with a time varying electric field. By the way, these are all technologies which have a very strong connection with high energy physics. You will see that the technologies which are used in high energy physics and low energy, I mean, these things are at millikelvin temperatures. We were talking about 10 to the 12 Kelvin temperatures. So, 15 orders of magnitude, and we end up using similar technologies. It is quite kind of remarkable. So you can see our box of tools is basically also built on our imagination of what the thing is. So what you are seeing here is a trajectory of an ion, okay, when in a combination of oscillating and DC fields. And what you are seeing is two kinds of motion. This is the fast motion, which is synchronous with the time varying electric field, and the slow motion, which is the time average potential which it represents. And that is what is trapping the ions. Now, there are two kinds of ion traps. We have both in our labs. One is a linear Paul trap. This is the kind of trap which is often used for quantum computing. And this is an NCAP type trap. This is used for optical clocks. And this is the trap I'm going to talk about in the further part of this particular talk. But we have both these kinds of traps in our lab, and we are trapping ions in both of these. So now I have to tell you, okay, so now we have solved the problem of holding an ion in space. But now we have to lower its energy. We have to address it. So we have to cool this guy so that it has very little motion, because a little bit of motion means that a monochromatic beam of light appears to it to be shifted in frequency. That is not very good, because then you are going on and off resonance if your resonance is small. So what you want to do is not only hold it, but you want to actually cool it so that it is in the lowest possible energy state that you can put it in motion. So what you have is let's say a two-level atom. You have a ground state, you have an excited state, and you have so the black line is a laser which is on resonance, a blue line which is above which has a higher energy than the gap between these two levels. That is called blue detuned, and the red guy is the red detuned laser, which has lower energy than the so this is the atomic line, this is the resonance condition, this is so this is light scattering intensity, and this is the resonance, this is the frequency, and you can see that red detuned is to the left, blue detuned is to the right, and this is how atoms scatter light, absorb and scatter light. Okay, now when an atom which has some velocity, it is moving in counter to the direction of propagation of the red detuned light, then the red detuned light is seen to be more shifted towards the resonance. So the light which is here, for the atom, it comes shifted towards the resonance. And when it comes shifted to the resonance, the atom absorbs the photon, gets a recoil kick, okay, and it slows down just a teeny bit. And then this excited atom will decay into, by emitting the photon, some energy, it will get another recoil kick, and that is random. So that gives you the stochastic process, which allows you to cool. Laser cooling every cooling has to have a stochastic element to it. This is the stochastic process. If, on the other hand, the atom was moving away from the incoming red detuned light, then it would not absorb because it would be very far away here and it would not be sensitive to scattering the light. So this is laser cooling. This is what we do to atoms or ions which are in a trap so that we can keep them and hold them down in one place. So this is quantum engineering. This enables you to prepare your system to do all the stuff that you want to do, whether it is quantum computing, whether it is an optical clock, whatever it is. This is what an experiment looks like. And here I'm going to show you something which is how we load an ion in the ion trap. This is a movie of experiment in the lab, and you can see the dots are coming in one by one. Here what is happening is each dot represents light which is being scattered by a single ion, and you can see as time is passing, more and more ions are getting filled inside this particular potential, and this is what is happening. Now let me explain what has just happened in this particular picture. So what you will initially see is when the trap is empty, there is no atoms there. Okay, so you're shining some lasers in, so there is some residual light scattering, and that is at some level, which is a DC level. Okay, now what we'll do is, as the atom comes in, suddenly there is a scattering point which is extra for the laser light you are pumping in, and the intensity goes up. So that is a jump in this intensity, and then it plateaus. Then a next ion loads up, there's a jump in the intensity, and so on and so forth. And you're seeing that when a new ion comes in, the screen is blanking out. That blanking out is actually happening because the new ion which is coming in is very hot compared to all the other laser cooled millikelvin ions. So this is a crystal. This crystal instantaneously melts because this ion has, it gets caught into the trap. It has a Coulomb force. It interacts with all the other ions which are very cold. It comes with a few hundred Kelvin, and it bangs into this millikelvin cloud, and it completely melts it. Then a little bit of time is required to refreeze all the earlier ions plus this new one, and that's how you get, the screen is blanking out. You're seeing basically in these kind of the simple thing which we do on a daily basis in our lab is illustrative of so many things that you can, so much of the physics you actually read about, and you can see it happen, okay. So now, how do you measure with quantum physics? I don't know how much time do I have left actually. Okay, so I need to so what you need to do now is you need to have quantum jumps. I was looking at this timer, and it was not counting down, so I was comfortable with 16 minutes. Okay, so yeah, so here is what is happening. So what you want to do is, let's say you have a single trapped ion that is like this, and you want to put it in a dark state. Okay, so when you put it in a dark state by tuning some lasers, then it you can see the fluorescence suddenly vanishes. The ion is still there. It is just not in a state where the applied lasers will scatter light from it. And so you get, in our case, the dark state is this 5D the doublet D 5/2 state, and essentially the lifetime from this state to the ground state of the calcium ion is 1 second. Okay, so this is where you are seeing the stochastic nature of the decay of a prepared excited state into the ground state, because you can see that these times where the ion is in the dark state is varying. There are short intervals, there are long intervals. And what you do, and this is what a video of this thing looks like. You can see, I mean, these are, things, all the videos I'm showing you were taken 1 month after, in the first month of when the experiment became operational. Okay, so you can see the ion is blinking on and off when it goes, so it's dark, it's bright. I mean, these are your quantum signals. This is what you want to measure when you do quantum manipulation. This is with 2 ions, and so you can see 1 ion going dark, both ions going dark is down, and both ions bright is the top. So now you can see phase transitions in these kind of crystals. Okay, so what you can do, okay, I won't spend a little bit of, okay, I'm going to skip a bunch of stuff in the interest of time, and I'm going to tell you something, that lifetime, if I want to measure this lifetime, I told you it's 1 second. So we took 2 hours of data of this particular thing. I mean, this is just initially, within the first week of the experiment working, and this is what the histogram of the downtimes looks like. Okay, it's very dirty. You can fit it to a single exponential and keep your fingers crossed and then compare it with experiment. So you get a number, which is the lifetime, which was not bad. It is almost 1 second. And this was literature. Okay, this is not the right way we were doing this measurement in the wrong way. So, I mean, it was always going to be very approximate. Now, just like a week ago, we got all the tools in the lab to do this experiment right. We will do it, and we'll do it for 1 week. But you can see that if I have to measure a 1 second lifetime, I'll need a 1 week's measurement to get a nice data histogram, so that that phi sigma thing that the high energy physicists keep talking about is well met. Okay, so now I will tell you a little bit. I'm going to change to something which will connect with condensed matter physics as well as high energy physics. It's just a vignette of something that we do in the lab. So now I have trapped ions in the ion trap. So there's an external potential and there is essentially Coulomb interaction between ions. This is the two actual native forces of this system, and there is the light scattering that is happening. Okay, so this is basically the thing. So now the trap is a harmonic oscillator trap, and you can say that alpha, if I change alpha, I go from a pancake shaped trap to a oblate shaped trap. Okay, that's all that you have to remember. And now I load in my ion trap while laser cooling 4 ions, 5 ions, and 6 ions. This is what is 4 ions, what you get with 4 ions. This is what you get with 5 ions, and this is what you get with 6 ions. Okay? This is the full crystallography of these ions. These are things which, I mean, we did it, this is the first of its kind, because people have not done this kind of crystallography in 3 dimensions with ion traps. So most of these ions are not yet published. Our journal, our thing is under review. So, so now you can see that you start with high alpha, which means you start deep in the pancake. Okay, so 4 ions are in a square pattern, and you see it as a ring or a line, because actually this is stochastically rotating because of the laser cooling kicks that it is getting. Our trap is so symmetric that even a photon recoil of a single electron, of a single photon, will make it go at 50 hertz. Will make it rotate, impart enough angular momentum to make it go at 50 hertz. So you can't image. So you always image it smeared in the XY plane. So you'll see it as a line because we are looking at it side on. And you can see that this is a crystal. This is when the trap is X, Y, and Z geometries are exactly identical. So it presents itself. It will be like a trapezoid or some shape, but it will rotate freely on a sphere, which is why it looks like a sphere. Okay, now I will just show you one instance of structural transitions. And if I can get 2 more minutes, I will do it. So essentially, structural transitions break up into 2 types. One is essentially a displacive transition, and the other is a reconstructive transition. So the displacive transition is if you have a crystal structure and you move things a little bit, then you go from one point group to another related point group. Reconstructive transition is when you have to break bonds and make bonds in order to obtain the new crystal structure. So like graphite and diamond is a reconstructive transition, but this is barium titanate oxide, you go from a high symmetry to a low symmetry phase by doing this. Now, you saw all these crystals. As a function of my trap squeezing, I can break the symmetry and make the symmetry. So all these structural transitions are actually happening, both the reconstructive type as well as the displacive type. And I'm going to show you one such thing. So, okay, we can explain all our things for this is a little slightly technical from Landau theory. Okay, this is something which is used for second order phase transitions. Don't worry about it. But what I want to say is the following. When you have a crystal and it is going to change its symmetry using a displacive transition, then what is going to happen is as you approach the point where the symmetry is going to change, there is going to be a freezing of some normal mode. So the crystal is vibrating. If there are few ions in there, there are 3n of those few vibrations which are present. These are the normal modes, and one of those normal modes will freeze. And when that freezes, that pins the entire structure into changing its conformation as you change the parameter. So this is what is called. So this is something which was Cochrane and Anderson proposed in 1960, and I will show you what the great C.V. Raman did a bit later. So in a 4-ion configuration, you have these kind of crystals. One is a cross, that is when you have, then you lift the symmetry, then it goes like this, then it comes in like that, then there's a canting, and then you get these in a straight line. And what you can do is, so what we do is we go and we look at this transition in detail, okay, where you go from a square to a lifted 2 dumbbell structure. And what do we find? We find a Higgs-Goldstone mode, okay, because what is happening is that there's a bifurcation, and the bifurcation is this. This is one option, and this is the other option. So you see, whether the way the dumbbells, the way the inversion symmetry is broken is coming out, and this is the order parameter for this is breaking in the octopole moment. Okay, and so you can use the language of condensed matter to explain ab initio crystal structures, and even get a Higgs mode. Okay, I don't know. How that excites somebody. Okay, this is all details. One last thing, which is the C.V. Raman had and Nirangudi in 1940 had already seen this soft mode, and they had got the mechanism right. Okay, long before Anderson and Cochrane, etc., made their predictions. And so this is the kind of stuff that we are doing right now, because we didn't have some tools to get straight away into the quantum domain to do the superposition states. But now we have them, so we will do that. But essentially, we have all kinds of first and second order phase transitions are exhibited in just these crystals, and we have a study of these things. This is the article, which if you are interested in, you can look at. These are the heroes who have actually done the experiment, Anand and Akhil. And these are our collaborators. Shovan is a brilliant theoretical physicist in RRI, and Arun is in University of Toronto. And yeah, that's it. Thank you.
Thank you for this very nice talk. Maybe quick 2 questions so we can take. Yes, sir.
From the classroom teaching point of view, while teaching realization of qubit in quantum material,
Okay.
trapping ion comes one of the main category recently.
Yes.
Sometimes it is written trapping ion and sometimes it is written trapping atom. It is same or different?
Well, there is a trapped atom platform,
Yeah.
and there is a trapped
Different.
ion platform. They are quite different. The trapped ions, the way you do it is you have in an ion trap, you make a bunch of ions,
Yeah, yeah.
and then you couple them through the phonon mode. For trapped atoms, you take atoms in each one in a dipole trap, which is a light field, and then you entangle them using Rydbergs. That is the typical route. I'm sure there are other routes which people will come up with. So there are different technologies,
So
but
the realization of qubit is ground state and excited state, I believe.
yeah. So no. So the in the trapped ion system,
Yeah.
okay, what you do, for instance, gate operations are done via mediated via the phonon modes. Okay, it's a superposition between a phonon mode and the ground and excited state. So you
Harmonic oscillator type of.
Yes,
Is it harmonic oscillator?
it is harmonic oscillator physics.
Yeah.
All this
So-
stuff will
so
never
I
work if it's
believe-
not harmonic oscillator
I
physics.
believe if it is a harmonic oscillator type, then qubit realization is ground state is 0, excited state is 1.
Yeah, yeah.
Am I correct?
Yeah, I mean,
Yeah. Why do you
Sir,
prefer?
actually, I request because we are running out of time.
One minute. Just
Maybe we discuss during the tea break. Okay.
It's general interest of everything. Just a couple of minutes.
No, couple of minutes. Sorry. No, really, because the organizer is
Acha, acha.
proceeding.
Okay,
Okay.
thank you.
I'm really sorry
Thank
because
you.
he's asking to wrap up. Maybe a short question from a student, if there is any quick question. Okay. If not, I think then let. Okay, there is a question from a student. Yes.
Multi-qubit gates implemented in this.
okay, so for instance, for ion traps.
Yes, sir.
Okay, so what you have is you have 2 tight dimensions and 1 soft dimension. Okay, so you basically don't work in this kind of a trap for doing qubit operations, though we are exploring how to work with this. But the typical realization is in a linear Paul trap, and so you have 2 tight dimensions, one soft dimension, and what you do is you make the gate. The gating is done by applying a series of pi and pi by 2 pulses, which will make a superposition of the two ions, let's say, okay, via their internal state and the phonon mode, the common phonon mode.
The trap, the ions interact.
Yeah, the ions are interacting with the Coulomb force between them, but they have a common phonon mode, and that the state of the phonon mode is entangled with the internal state of the ion, and when 2 such ions are brought together and work with, you can make a nice gate or do stuff with it. It's very interesting, but it's actually quite simple. If I could just draw it on a board, I would just do it.
What causes the scalability issue then?
Okay, so the scalability issue is the following. You have a line, okay, which is essentially zero field, but you have to basically make it a harmonic oscillator. So when you make it a harmonic oscillator, when you bend the field, okay, along the z direction, then essentially the distance between neighboring ions starts changing, okay, And if you look at iron crystal images which are shown in the trapped ion quantum computing thing, you'll see them more crowded, okay, at one end, and it will be like spaced out in the middle or something like that. So, you know, the distances are not maintained, and then there are other issues. But having said that, trapped ions provide the best results in terms of fidelities and various other things. So, you know, I mean, they're kind of superior in a lot of ways, and they have pioneered the technology. But now the superconducting guys have come in, and they are able to scale more. They are going to get into their own set of problems, don't worry. They also have a scalability problem, so it's not like they don't have it.
Thank you, sir.
Okay. Looking at the time constraints, so thank you so much, Professor Anguilla. Yes. Thank you so much for this nice talk. Okay, thank you so much. Tapan says that looking at the interest of time, so we postpone the tea to we compensate by high tea at the end. So now I request Professor P.V. Satyam from IIT Bhubaneswar to chair the last session of this conference. Thank you.
Okay.
Okay, thank you, Shivankar.
I'm thirsty.
So indeed, it's a. I thank Tapan, Mr. Tapan Mishra, for giving me this opportunity to chair this session. The second speaker I'll speak later. The first speaker is we have Professor Ashok Mahapatra. So he did his PhD in TIFR and a couple of postdocs outside, including Germany. And from there he came on here. The important thing I would like to emphasize here is that Professor Ashok Mahapatra gave his colloquium talk recently in IIT Bhubaneswar, and then I felt that it was such a wonderful talk he gave. We would like to have a colloquium series with him. So that's what I was mentioning. I also mentioned him that teaching is an art. I felt that he has that, and I'm sure we all going to enjoy that. So it is meant for you now. Please go ahead.
Actually, I'm quite nervous. Professor Professor Satyam said I gave a wonderful talk in IIT Bhubaneswar recently. I don't know whether I'll match up to his expectation or not today, so I don't know. But thank you very much for this wonderful introduction, and also thanks Tapan and the organizer to just give me this opportunity to speak about this. I just have kept my title to be, creating powerful technologies driven by quantum principles. So I'll just speak about that. Okay. And, I was listening all the talks today, and there's some gaps which I'll fill up. Okay. So that would be a really nice thing. Okay. No, it's not working. Okay, so already Professor L.P. Singh, he gave a beautiful, wonderful history of quantum mechanics. And, he talked about this Max Planck, who explained the black body radiation of all the way to photoelectric effect. And, that's which was being done before the modern quantum mechanics, which came, which was actually developed during 1925 and 1927 by Heisenberg with matrix mechanics and Schrödinger with his wave theory. And actually, Schrödinger showed it that they are equivalent at the end. Actually, there is Professor Singh, he mentioned about this. Like you can have an operator method as well as solving the Schrödinger equation for a harmonic oscillator. You get the same answer. Okay. So, you know, because the quantum mechanics actually was formulated during 1925 to 27, then this 2025, just after 100 years, it has been declared by, declared as the International Year of Quantum Science. But I would like to highlight that also technology. Okay, so the quantum mechanics now, we cannot simply think that it's a basic science. We can simply use the quantum principle to develop the technologies. So I'll talk about that. Okay, so you know, when we talk about technologies, you cannot just get it just like that. And it takes a long time. The time taken to build a technology, like let's say the phone or a computer which we can use today, and from the conceptualization, it takes centuries. So one example is for the classical computer. If you see, it was first conceptualized in 1850 by Charles Babbage. That was a computer in 1940s. Okay, you can see the size of the computer. And then, of course, these integrated circuits, it came in 1960s. Then after that, the form factor could be reduced. And today, all of us are having the computers like this or our cell phones. Okay, and you see, you can look at the time scale from 1850 to 2025. Okay. I will just give one more example. You know, the mobile phone, the concept, it was actually started in 1922, and today is 2025, so 100 years, and we have the cell phone in hand. Okay. So, so now for quantum computer, I can say, like, you know, it was first conceptualized by Feynman in 1981 or 82. Then hopefully in our lifetime or my lifetime, let's say if I can count it to be 100 years, then maybe by 2080, we'll have a quantum computer which I can use, a quantum computer of this scale. Okay, this is what I just wanted to mention. Okay, so as I said, my talk is about using the quantum principles to build the new technologies. Let me just highlight about these quantum principles, which many students, they may know. If you don't know any of this, you please tell me. The superposition principle, already it is talked about a lot in this, in the morning. Interference, tunneling, uncertainty principle. And if you ask me, actually, these four principles, they are actually observed in some classical systems. Okay, some classical systems. And for the students, it is good, they can go back and look at those classical systems and try to understand those. But if you look at these three, the wave-particle duality, which was Professor Pati was mentioning in the morning, the quantum entanglement also, it was discussed in detail by Professor Pati, and the quantum measurement. These are specific to the quantum mechanics. Okay, so just to tell you about this superposition principle, can anybody tell me where do you observe it in a classical system? Anyone? Students? I have already mentioned there the Young double slit interference with light. Okay.
And of course, these two, you can observe it for light. Tunneling. So tunneling is for something called a frustrated internal reflection. Do you know what is frustrated internal reflection? Are you too tired or you don't want to respond? Huh? Okay, don't know. You know, the frustrated internal reflection is like, suppose if you take a prism, put just incidental light more than the critical angle, then all the light will be reflected from the prism surface. That is what we call as the internal reflection. But you know, the light actually, sorry, it has to be done from a denser medium to a rarer medium. So the prism would be like this. So the light actually, it goes a little bit to the air or the vacuum and reflects back. Now, if you bring another prism close to that, you will see some light will leak out. Okay, that is actually the tunneling. It's if you do the calculation, you will see it actually there will be higher potential, which is there is a potential barrier where the light is leaking through, and it is purely due to the wave nature of light. And the uncertainty principle, again, it is with the light. A Gaussian beam, it follows this delta kx, delta x should be greater than or equal to 1. No? Yeah. So these are the things we observe in class, some kind of classical system, but not all kind of classical systems. But these three, what I mentioned, they are actually observed in pure, it's specific to the quantum system. And already quantum entanglement is discussed. Quantum measurement is something, it is also discussed, not in detail. It's like when we make the measurement, the system actually collapses to one of the end state of the measurement basis, isn't it? That's the thing. But this wave particle duality, which actually Professor Pati was mentioning, that actually can understand very well with a very two simple experiments in quantum optics. Okay, one is just a Hanbury-Brown twist interferometer. Like, let's say you have a light source, you just split into two parts with a beam splitter and detect it. If it is a particle, let's say it is, and you say it's a particle, then I cannot split it. That's where we call it as a particle. And so if I want to look at the correlation, then if it is a single photon, then if this detector is clicking, this one won't click. If this will click, this one won't click. So there is anti-correlation. So that tells us that it has a particle nature. If I just change the experiment a little bit, like this, let's say, instead of putting the detector here, let me just reflect it by 2 mirrors and send it through another beam splitter. So I superimpose them again. And let's say I change the phase of the light there. Then what I observe, a interference signal there. If I change the phase, I'll see there is an interference signal. So that means that interference signal, I don't see if that photon has gone through both the paths. Okay, so that's a puzzle. So this one will tell you, this one we can explain if the photon is wave. Okay, it's a wave-like nature. Then I can get an interference pattern. The previous one can be explained if I say the photon is a particle. So this is where we say the quantum system has wave and particle both. So these are the things which actually you don't get it in a classical systems. So, so nevertheless, I mean, all these principles, it is must for a quantum system. Okay, all these principles, it must for a quantum system. And let's see how we can use these principles to build new technologies which will be more powerful. So that's my objective. Okay.
So now you know there is the quantum technology, which it has basically three verticals. One is the quantum computing, which you have already heard the talks. The quantum communication, where the entanglement of the photon pair is being used to make your communication to be secure. Okay, so I'm not going to talk about that, but I will just talk about the quantum sensing. So before telling you about the quantum sensors, so the one thing which is not really covered in the talks in the morning is about the decoherence. You know, the decoherence is actually the devil. Okay, that kills everything. I mean, whatever the technology I am building using these principles, if the decoherence is dominating, then my objective won't be fulfilled. So that's the reason we have to understand this decoherence well. And when I talk about decoherence, it's actually the noise. And that noise, you should not confuse with the quantum noise leading to this uncertainty relation. You should not confuse with that, because that is actually quantum. Okay, what I'm talking about, the classical noise in the system. Okay. So what is the decoherence? So this I can understand if I take the superposition of a quantum state. So let's take a simple example of a spin-up system. It has two states. Okay, spin up, spin down. So I have just depicted this one is like a spin-off state along z direction. These are spin down along z direction. These are the two states. Then any arbitrary state, any arbitrary quantum state psi can be just written as a linear superposition of these two. Okay, where these two are two complex number. But then you know, these complex number, you can say these are C1 and C2, but what I can do is like I can take the phase of one, the first complex number outside, and then I can make it to be real. And then this one, the phase, I can take it out here. So that is the relative phase between these two complex number I'm saying. So whatever the complex number I have taken out, that the phase I have taken out, that's a global phase. Actually, that doesn't play a role in the dynamics of the problem. So that's the that's why I can take it out. And then after that, I can write down just with two parameter. One is theta and phi. Okay. And you can see easily that this cos square theta by 2 plus sin square theta by 2, that will give you 1, perfectly matching with this probability to be total probability to be 1. And of course, there is a relative phase between these two complex numbers is phi. And interestingly, what you can do is, since these are just two parameters, if I write the state to be like this, you can represent that state on the surface of a sphere. Okay, you can just do this little algebra. If you take your theta to be 0, that is your spin-off state, theta to be pi, that will be your spin down, and theta can go from 0 to pi, by the way. Okay, and you can take the phi to be 0 to 2 pi. Okay, and these are like one is the azimuthal and the other one is the polar angle in your spherical polar coordinate. Okay, so you see in a two-level quantum system, any state you can simply represent on a surface of a unit sphere, and you can visualize all the rotation, everything, or whatever people are talking about the gate operation, single qubit gate operation in quantum computer, or everything, you can simply think about it's a rotation in the surface of a sphere. Okay, so now if I try to understand the decoherence, so it is the noise of this theta and phi. Any kind of noise when I introduce to theta and phi, that will basically include the decoherence in the system. Okay, so how do I understand that? This one is not working, is it? Okay. Yeah, so to understand that decoherence, what I do is like, let me put a magnetic field. Then once you put a magnetic field, of course, you can split the energy level.
And the splitting would be basically equal to h bar omega L. That's the Larmor precision. And what exactly is the Larmor precision? If the magnetic field is along z direction, and if you start the initial state to be here, then it will keep oscillating about this z axis with this frequency. Okay, the quantum state will keep oscillating about this z axis. That you can get it from this little calculation in quantum mechanics. Okay, you can do that calculation here. Like you take a state like this, okay, that is your psi 0, and the psi t would be something like e to the power I minus phi minus omega L, I times phi minus omega Lt sin theta by 2 dou. So it is kind of oscillating like this. Okay. So, so now what I can do is like I introduce any kind of noise here. Okay. How can I introduce that noise? The magnetic field noise itself. That's just an example. I can introduce a magnetic field noise. So then there will be a noise here, a noise here. That is one way to see. Or, yeah, in this case, actually, this would be the, yeah, it is the noise in the magnetic field. So basically, this energy level are not just single. It's there is a spread. Okay, there's a spread, and what you can do is now with this noise, if you try to see this one, that is basically introducing a noise. This omega L. Omega L is not just one value now, it has a noise, there is a noise, and over the time, this whole phi, which is basically this whole thing, is getting a noise added to that. Okay? So that's where basically you introduce the decoherence in the, or the noise in the phase, and the same way you can think of introducing the noise in theta. And with this we can say, suppose this is my delta omega. This delta omega which is introducing the noise to phi for the time evolved state, and it doesn't remain as a pure quantum state anymore. I cannot write a pure quantum state, and it will be basically it will go to a mixed state. It will go to a mixed state, and then you have to use the density matrix for that. But then what I can do is like my phase noise now I can calculate to be delta phi to be delta omega by t, and from there I can just calculate what is the coherence time, which would be roughly 1 over delta omega. Okay, so so this is the decoherence and the coherence time of for a quantum system. So if you are doing the quantum computing, then of course this coherence time is very crucial. Like like if you take an atomic platform, the coherence time they found to be something like of the order of 1 second. Okay, then you can calculate this delta omega is really small to at a Hertz level, less than a Hertz level, to get the coherence time to be of the order of second. Okay, so so this decoherence actually plays an important role in quantum sensing also. If the coherence time is longer, the sensor performance would be better. How many? 5 minutes. Okay. Okay. So now I'll just tell you quickly. I'll tell you about a couple of sensors. One is a magnetic field sensors, where we use the coherence in the superposition of Zeeman states. Okay, to build a magnetic field sensor, and this is what's the simple experiment. So you know, if I take a atomic state, in this case it is rubidium, and if I take the ground state to be F equal to 1, it will have 3 magnetic states. I know F equal to 1 will have MF equal to -1, 0, 1. Okay, these states I can actually couple them with a RF magnetic field. I can couple them with RF magnetic field, and this RF magnetic field generate a coherence between these states. So since I'm driving the system, it is developing a coherence between, let's say, MF equal to 0 to MF equal to -1 state. And then I can drive this state to the excited state. That will create a coherence between MF equal to -1 to MF equal to 0 state, the excited one. Then a natural coherence being developed here. So that generates a light. And by detecting that light, which has a different frequency than the whatever the pump light, what we are putting, by detecting that, we can say there is a RF magnetic field present. And that's the principle of the sensor. And this is what we did. The experiment, this is the first sensor what we had built. And then, of course, you have to do some little interferometry experiment to detect that light, because it will just interfere with this beam. So we can detect that. And in fact, these are the signals what we get. These are the signals. See, this is the pump light. This peak is because of the pump light. These peaks are because of the generated light when there is a RF magnetic field present. And just by detecting that, we can say there is a RF magnetic field present. And from here, actually, we could measure the sensitivity of this magnetic field sensor to be of the order of 70 femtotesla per square root house. So when I say 70 femtotesla, means if I average the signal for a second, I should be able to detect a change of 70 femtotesla. Okay, so that's the idea. And you see how small field we can see. Now the other one, the electric field sensor, I don't have time, so I'll skip. So that we use with Rydberg atoms. And again here this sensor is being used. We use the interference of two pathways of excitation to the Rydberg state. That is being used, which is a process. And there actually we can detect the microwave. There we can detect the microwave, which is at 15 gigahertz. And yeah, so this is where actually we could write a music to the microwave. We can write a music to the microwave, and that we could actually transfer the music, which is the electrical signal, which is written on this 15 gigahertz signal, and it was transferred to this light. Okay, that was the thing. If you allow me, I just play that video for a second. I think the yeah, so though I didn't go into the detail, I just tell you about this video. What we have done is there is a microwave source, and you can see this cable, and there is a horn antenna where the microwave is being radiated in free space. Okay, and when Tanim, she is my PhD student, she worked on this problem, and what she was doing, she was taking the music, I mean, from her cell phone, which she is doing an amplitude modulation of the microwave by connecting to her phone, cell phone. So then the amplitude modulation of the microwave was done. And then since we can detect the microwave with this Rydberg excited light, then whatever the music as an electrical signal as a written as amplitude modulation, that was transferred to the light. And then that light was detected with a photodetector, amplified with this amplifier, then which was played. And I can just play it again to start. You can see that what I just described, you can see. So this is where she is just doing amplitude modulation of the microwave. Then, yeah. You see, when she blocks, the music stops. So that means we cannot detect the microwave there when she is blocking that. Yeah. Okay, so I told you about what happened. Sorry. Okay. we are off the time. But one thing what I didn't tell you about is the last slide was about these powerful technologies. What actually you can do many things. These magnetic field sensors can be used for inertial navigation system, which doesn't need a GPS. Okay, and this inertial navigation system is now very important for defense technology. Okay, because GPS jamming can be done, and then it can be used for biomagnetic field. It can be used for geomagnetic field for mineral exploration, and also it can be used for dark matter search, say fundamental research. But what we are targeting or we are planning in our lab is key. We wanted to detect, let's say, a biomagnetic field, like your brain at the skull. It generates a field of the order of 100 femtosecond of that order, and our sensor is already sensitive to that. And if we put the magnetic field sensor, if we can miniaturize it, put many sensors, then actually we should be able to detect the brain activity. Okay, if we can use AI, machine learning, we can actually use the, you can study the brain activity, which would be useful for the disabled people. Or in other words, I should be able to read your mind at some point. Maybe after 20 years down the line, we should be able to read your mind with our cap, which will make with our magnetic field. Okay, with that, thank you very much.
Yeah, thank you, Ashok. And right now, he's not reading my mind, so I'm safe. But indeed, it's wonderful talk, and showed what the future could be. And one question from any student is welcome.
Yes.
Yes, sir. Sir, you mentioned that when we have noise in theta and phi, we get to see this. So, is it necessary that the noise in theta and phi is always classical, or any quantum noise can also happen in theta and phi?
See, the thing is that, of course, I can say what is the state. Those noise, what I get when I make the measurement into complementary observable, let's say SX and SY, isn't it? But for the given state, okay, for the given state, I can accurately prepare it. Let's say all the spins aligned along Z direction in spin off. In principle, I should be able to do that. But when I make the measurement, let's say in SX and SY, then that delta SX and delta SY would be greater than or equal to 4 times, I think, mod of SZ or something. Something like that's where I get the noise. Yeah.
So, can there be a quantum aspect to that noise in theta and phi?
No. So when I'm saying the see quantum aspect to that noise, see these are the parameters. Okay, so see the noise you associate always to the observable. I mean, it's like you choose the measurement basis.
Do you want to say is fundamental in nature?
No, I just want to know about can there be a quantum aspect in this theta and phi parameters?
Theta and no, if it can be, if I actually if I have a theta and phi, no, so when you are making the measurement, let's say SX and SY, that's where you can associate with theta and phi, no? Okay, but having the noise for theta and phi for the state, I can prepare all of them in one state actually. Well, that would be a problem. I don't think that should be a problem.
should not be a problem.
So any further questions? Okay, so otherwise, let's thank the speaker for a wonderful talk, as we expected. And the last talk is, it's indeed my great pleasure to hand over the memento to Professor Ashok Mahapatra in his own institute. And thanks for giving me this opportunity to present him. So we move on to the last talk of the wonderful day we had, 100 years of quantum mechanics. And indeed, it's my great pleasure to invite my thesis supervisor, Professor B.N. Dev. And I feel honored to be here to invite him. Of course, it's only one thing which I'm envious is he looks more younger than me. So, and of course, he does more research than me also. So that's nice of him. And the topic what he has chosen, the quantum tunneling to Nobel Prize in Physics, indeed an interesting thing, because way back in IOP Institute of Physics days, IOP days, in 2003, the first MBE STM facility was up, which was his dream to get the quantum tunneling going on, where the excitement of getting a 7x7 reconstruction silicon 111 surface was still very live in our minds. So I'm pretty sure you all enjoy. He's one of the, the very good teacher. Actually, he's inspired a lot of us to do basic research as well. So, an experimentalist. He's a great experimentalist in such a way that he teaches students without coming to the lab. So that is an interesting thing which we will see. But you can imagine many things without. You can tell, okay, here is the problem. So this is an opportunity to invite me, Bhupen, and indeed I feel thankful to the NISR to give me this opportunity to invite him here on this special occasion. Thank you. Still, it is 20 minutes, so he is my boss. So you don't get any extra time, Bhupen.
Okay. You promised me to give extra time.
He gives, but not me. I'm the chairperson.
So I can ignore you. Hello.
Yes, I thank Professor Mishra for inviting me here. And I also thank Professor Satyam for giving this kind introduction. But of course, he's a student, so he has a tendency of overdoing things, of course. Anyway, so this is the pointer. So I start with the picture that Professor Vedang Mohanty showed, existing at two places at the same time. So his wish could be fulfilled because the Nobel Prize for this year is about quantum mechanics of macroscopic system. So far we have heard all these things, the quantum mechanics explains the behavior of atomic, subatomic particles, but this Nobel Prize for this year is not just for subatomic or atomic particles, it's for macroscopic systems. It's something I can even hold in my hand, and that obeys quantum mechanics. That's the message. So the theme is the tunneling, quantum tunneling. And the tunneling has undergone different kinds of tunneling, so I have to give an introduction to those also. But I have to keep in mind about the students, because it's for undergraduate students mainly. So if I am too simplistic somewhere, I apologize to the experts for that. Well, that's the outline. Quantum tunneling, there's three types of tunneling I have talked about: electron tunneling, Cooper pair tunneling, and finally the macroscopic quantum tunneling. That's the topic of the Nobel Prize this year. And these aspects will show the macroscopic quantum tunneling and the energy quantization for a macroscopic system. So you have already seen that these three people got the Nobel Prize this year: John Clark, Michel Devore, and John Martinez, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit, and which is macroscopic, basically. So this is only fair that this year of international quantum science and technology, the Nobel Prize has gone to the quantum science. So this work is not just a fundamental. It's a superconducting circuits and superconducting quantum bits, superconducting quantum computers. All these things that come from here. So quantum tunneling. So for the students, I have a copper wires connected with a battery. So there will be a current flow through that, right? What is your answer? Yes, okay. So if I have a break in this wire, will there be a current flow? What is the answer? But what is written here? The quantum mechanics tells us that it is possible to have a current flow through a gap. So this is, you have all studied quantum tunneling. The algebra you have done already, but now try to see if you can connect your ideas with that. Let's see how it happens. So this is the picture that cartoon says, if you throw a ball which is macroscopic and to a wall which is like a potential barrier, then this comes back. It cannot go through. But if it is a quantum particle, say throw an atom to that, if you throw it 1,000 times, maybe 5 times it will penetrate through that barrier. So that means that in this case, you can provide, you can actually have current flow through that barrier, through that break. So this you have studied already. The quantum, if you have a potential barrier and a particle arrives from this side, this is the incident particle. The major part will be just reflected, but a part will just transmit. This will undergo exponential decay. Right? You have studied all this. So let's see that if this barrier didn't extend all the way here, it has extended only up to that, and then the potential has gone to 0. So that means I have a potential barrier of this type, right? So I put this potential barrier here. Now I can see on the other side of the barrier, I have some amplitude of my incident particle wave function there. That means they have penetrated. So that means this, if there is a gap between these two pieces of copper, through the gap now electrons can tunnel. That's the quantum tunneling of electrons here. So this was the discovery, and a Nobel Prize was also given not for that discovery because it's just quantum mechanics principles, but using that to develop a very powerful quantum technology. For that there was a Nobel Prize also. But before that, even for fundamental quantum tunneling, there were Nobel Prizes. I'll just mention those. So this is what you have studied in your book, right? This wave comes from here. This is the exit wave function. The mod square of that is like mod square of the incident, exponential minus 2 kappa d. So now you see that if d is large, it is 0 almost, right? The amplitude of the transmitted wave function. If d is small, it is non-zero. So the first Nobel Prize was given on tunneling. It's two people, Leo Esaki, for showing in a diode, semiconductor diode, tunneling behavior. And then in superconductor also it was shown by Ivar Giaever. So these two persons got Nobel Prize, but simultaneously together with them, Josephson, who actually predicted tunneling of Cooper pair. In a superconductor, the carriers are not electrons, it's the pair of electrons, the Cooper pair. So now, Brian Josephson's theoretical predictions were essential also for the Physics Nobel Prize of this year. As we go along, we'll see all these things. But then, using quantum tunneling, these two people, Gerd Binig and Heinrich Rohner, they developed the most powerful microscope. It's called the scanning tunneling microscope. What is this? If you have a piece of material, these are atoms on the surface of a material, and you take a metallic wire, you cut it, and you can make something like it, and bring it close. Then there will be tunneling of electrons, depending on the voltage. If it is a minus here, electrons will tunnel from here to here. If the minus is on the other side, electrons will tunnel from here to here. Now you notice something, it says the 1 decade per angstrom. That means if you change the distance by 1 angstrom, the current will change by a factor of 10. Extremely sensitive. And that's why this microscope could be developed where you can see individual atoms on the surface. So this microscope has enormous capability, like microscope with the highest spatial resolution, and equipment to explore electronic energies of quantum states, and equipment to explore atomic scale, nanoscale structure, and equipment to move atoms around. With a, as I say, I can move this one holding from here to here. I can hold an atom from here and take it there using a tunneling microscope. So this is this quantum tunneling experiments had been going on in Bhubaneswar since 2001. This was our equipment. It's a molecular beam epitaxy. We can deposit atoms, and I can draw many structures. And here, this is the variable temperature scanning tunneling microscope. And everything within this chamber is ultra high vacuum. It's something like vacuum at the interstellar space. So it's the cleanest possible system. And then I'll give you some examples from the first measurements of results from here. This one shows that scanning tunneling microscope image of a clean silicon 111 surface. There, each dot is a single silicon atom. And you can get the detailed structure of the surface, and you can also see the periodicity of the structures. So this early as 2003, these were published. We can grow nanostructures, like this is a germanium island on silicon. You can see the size is 10 nanometers, this scale bar. You can, this shape is like a trapezoidal here, but you can also grow almost spherical quantum dots. In this picture, it is scanning tunneling microscope can see from the top, so you cannot see the full shape. You can see it circular, but you can cut it somewhere here. And from the side, you can look with a transmission electron microscope. Then you can see that these are nearly spherical island. With a high resolution image, you can see atomic strings, all these things within the germanium island, and also their extension into the silicon. This is the epitaxial nano island. And the dimension of this is about 10 nanometer, and this has quantized energy levels. In the morning, Professor Ghosh talked about the quantum dots. So this is the quantum dots, and they have quantized energy levels in them. This is something interesting. This is these lines that you see. These are silicon wires. The width of that has only 3 atoms and enormously long. So you could do the spectroscopy, electronic density of states measurements for both sides, the valence band and the conduction band. And then you could actually drop a few atoms there. Every 10 silicon atoms you drop on silver. Depending on their bonding position, the electronic structure gets changed. You see the band gap has changed, many other different features. All these features we observed. And then also we explained it with a theoretical paper. The first one is the experimental, second one is the theory. It's just so many different kinds you can do. That was done in Bhubaneswar IOP. I just given a few examples. But here it's called that Leo Esaki got Nobel Prize showing the quantum tunneling in a diode, and that diode showed negative differential resistance. What is it? If you increase the voltage, current increases. That's normal. It gives you resistance, right? But after this point, you see that the current is going down. That means that's a negative resistance. So negative differential resistance that is being used in lots of electronic components. So this was his discovery, Leo Esaki, tunnel diodes, 1958, and his Nobel lecture, Long Journey to Tunneling, 1973. But so this is macroscopic. But we have actually demonstrated it from Bhubaneswar, atomic scale negative differential resistance. What we did here is on silicon, we deposit 1 atomic layer silver. Do the measurement of this IV curve. See, from 3 atomic layers, you have this turning of this resistance. So this at the atomic scale, 3 atomic layer film, and we see already the negative differential resistance. So this is to show you different possibilities. That was done right here in Bhubaneswar. Now, what I show here now, another interesting thing, atom manipulation. You can deposit a few atoms on the surface of something, and then, but with the scanning tunneling microscope, you can hold it from one place, drop it another place. By doing that, this was written IBM with 35 xenon atoms. So each dot is an atom. So with 35 xenon atoms, whole IBM was written over there. This is another structure where 48 atoms had been arranged in a circular array. And on the surface of this material, there are surface electrons which move on the surface. And what you see here, these are the electron standing waves, because the electron originates, gets scattered and comes back. It's like a particle in a box. This box provides the potential, and you have the standing wave patterns within that. If you make it, instead of circular, it's elliptical, and you place one atom here, then you image it, you can actually see that there is like another atom there. But actually there is nothing there. That's why it is called quantum mirage. It doesn't exist there. And also this talks about the quantum teleportation in a nanoscale system. So there is nothing actually here, but actually you have transported the wave function of that there. Right? So now I come out of this single electron tunneling. So we are going to get into another regime. It's the Cooper pair tunneling. That happens in this called the Josephson junction. In this case, this is a superconductor instead of a simple metal. You have an insulator, which could be an air gap or some other insulating material, another superconductor. So through this circuit, even if you do not connect any battery and just connect it like this, you can get a current flow through that. So this will not happen for normal metals. Only for superconductor and Josephson junctions, this can happen. Now, how do you describe these two superconductors? This is like the whole superconductor is a macroscopic quantum system. So you represent it by a wave function. The magnitude, amplitude of that is mod psi L, and this is the phase of that. On the right side, this superconductor, again, you represent by another wave function. Now there can be phase difference between the left side and right side. So you define this phase difference phi. So basically, we are going to show that phi behaves quantum mechanically. That means the junction behaves quantum mechanically, a macroscopic system. But before going into that, let us understand the Josephson junction a little bit more. So what is showing, the Nobel Prize has shown that the junction has quantized energy levels. So that's a quantum phenomenon, and the phase phi shows quantum mechanical tunneling. So that means this big piece of we can hold something like Josephson junction in our hand, and that is going to behave quantum mechanically. So now this is the Josephson equations that is described for the Josephson junction. What is it? I, just forget the t now, I equal to IC sine phi. So that means if I have a phase difference between these two phi is non-zero, I see that IT is also non-zero. That's the supercurrent that passes through the Josephson junction. What is IC is the critical current. That's the maximum supercurrent that can pass through. If you send more current in that, then superconductivity will be gone. It has gone above the critical current. So it doesn't apply anymore. So this is the second Josephson junction. If you have a constant phi, you can get in current already. This is DC current. But if you have a variation of phi with time, then that actually generates a voltage there. Or on the other hand, if you apply a voltage to the circuit, then it will change a phi that changes with time. These are the behaviors that doesn't happen for a normal junction without a superconductor there. Okay. So now let's look at these two Josephson equations. You do simple algebra here, and then you find a relationship like that. Can you connect it to something in electronic circuit? V equal to L di over dt. That represents an inductor, right? It's across an inductor, that's the voltage that generates if you change current di over dt. Now what we find here, this L is not a constant. This is a function of that phase. So this is, as you see here, so that means it is nonlinear L. If you, want to construct an LC circuit, you take an L, which is like a coil, that provides you a linear L. But here you get a nonlinear L. And that is very, very important for all the things that I'm going to describe later. So reception junction is an LC circuit, but where L is a nonlinear inductor. That's the difference. So let's explore the properties of a simple LC circuit. You have done it in your undergraduate classes. You have studied simple harmonic oscillators, right? And if you have an LC circuit, there also the charge, the capacitor charges and discharges, you have oscillatory values for the charge. And that's represented by this equation. So it's an oscillator, and that has a frequency of oscillation. This is the angular frequency. Linear frequency is 2 pi f equal to omega. So that depends on value of L and C, right? So now let's proceed. If I construct a LC circuit, right, I can calculate its frequency. From the electronics laboratory, if I pick up a capacitor and an inductor, that their value would be typically say 10 microfarad, 1 millihenry. So if I put that in the equation, what I get omega, and of course the 2 pi nu is the omega. So nu is this frequency. If I know the frequency, I can calculate the energy h nu, right? And that h nu value comes to be like 10 to the power minus 12 eV. How small it is? What's the difference between hydrogen n equal to 1 and n equal to 2 level? That's the energy difference. It's about 10 eV, right? And this separation is 10 to the power minus 12 eV. So the states should be so close that I cannot consider it as a quantum oscillator. It's a classical oscillator, right? But if we take slightly different values of this L and C, say instead of microfarad, femtofarad, and instead of millihenry, nanohenry, I put those values, then I get these energy differences like 10 to the power minus 5 eV. Now we can call it as a quantized energy levels in there because we have microwave frequencies. With that, we can actually excite from one state to another. 5 gigahertz frequency we have in microwave. So this is now the energy levels could be quantized this way. So this we have already studied. Quantum harmonic oscillator, I suppose, wave function, and this is the energy levels, probabilities. So now we talk, if I call it this lowest level ground state, a zero state, like a quantum zero state, this is quantum one state that we have been listening for all the lectures. So let's move ahead. So this was my LC circuit. So the LC circuit gives me a harmonic oscillator, right? Simple harmonic oscillator. And the energy levels separations. How much are these separations? It's all of them are same, right? It's equal separation between the energy levels. Now there's a problem. If I want to do anything quantum with that, and if I want to interact with a photon, microwave photon, and if I can excite the system from this state to this state, accidentally I can also excite from here to here, right? Because it's the same energy difference. So that's not good for going into the quantum. So what is done, if you replace this linear L by a Josephson junction, then you get a nonlinear L there. And that modifies the potential. It's not a simple harmonic anymore. It's an anharmonic potential. In this case, the energy separation between 0 and 1 is larger than that of 1 and 2, and like that. So now if I work with an incident photon, which frequency is just this difference, then I cannot accidentally excite the other ones. That's very important for that. So the reception junction acts as a nonlinear inductor, and this is the value of that. And these are the three papers based on which Nobel Prize was given for this year. And in every case, you see that it's in a current bias reception junction, of a current bias reception junction, of a current bias reception junction. So that's what I'm going to tell about right now. What is a current bias reception junction? Basically, you just connect it and give a current source, you pass a current through that. So after doing that, what we are going to drive at is what the Nobel laureates have shown, quantum mechanics of a macroscopic variable. That is the phase difference of a Josephson junction. 5 minutes. Okay, 5 minutes, I probably cannot do a justice to this, but if you insist on that, then of course I. Okay, so this is okay. So this is the current bias junction. That means I send a current through this circuit. So this is the total current. But as I said, this is a Josephson junction behave like L. But these are two superconductors, so the metal and the insulator in between. What is it? It's a capacitor, right? Two pieces of metal plates, and in between I have an insulating film. It makes a capacitor. So it's not only a Josephson junction, in parallel I have a capacitor, but also in many cases these Cooper pairs can break, it can form electrons, and that actually acts as a resistor there. So there is a parallel resistor here. So if I write the equation for this total current, that would be the current flowing through all three branches, right? So current through the Josephson junction is this, current through the resistor is this, current through the capacitor is this. V dot means dV over dt, and V is this. So now so this is written, the same thing is written here in terms of phi double dot, because this is V dot, V is phi dot, so it's the second derivative there. Okay. So this is the equation that we get. So can you identify this equation? What does it look like? All of the undergraduate students have learned it in the first year BSc, I think. Can anyone tell? Okay, let's see. It's a damped driven oscillator, right? If this term is 0, this term is 0, this is nothing but a simple harmonic oscillator. If you have this term 0 and nothing else is 0, then it is damped harmonic oscillator. If this side there is some driving force, it's a damped driven oscillator, right? So that's exactly what it is. This is a damped driven oscillator that we are dealing with. So in this case, we know what you do. X t equal to what? That's the dynamics of this system. Here, phi t equal to 1. That defines the dynamics of this system, right? So let's look at this same equation written in this form in terms of a potential. So this potential is this. As you can see, the derivative of the potential that appears here. So this potential, if this IB is the driving current here, the bias current, if this is 0, so this is basically a cosine potential, just defined by this, right? And if you have this term, this provides a negative slope if IB is not equal to 0. Depending on the value of IB, this slope would be different. So your potential looks like a washboard potential. Why is it called washboard? It's a Dobbies use a board like that, and when they do this, the water rolls out there, right? That's called washboard potential. So now, look at this equation. So what is this term? It is the mass term, right? With phi double dot. Comparing your damped oscillator that I talked about. So this is like a phase particle. The phase oscillates with a frequency. That particle has this mass. So that is called the phase particle. The phase oscillates in this potential well there. And that, if you increase the bias current, VI by 2, this tilts. If you increase it to the critical current, then it just rolls out, the particle. So now just look at this one. You have a potential barrier here. You see that this potential barrier here is larger, here is smaller, here it doesn't exist anymore. So you can tune the potential barrier also by applying your current bias. So Josephson plasma oscillations is the phase undergoes damped oscillations in the washboard minima. Now say we have a situation like this. This is my potential barrier here. Now if I want to prove that really this phase particle behaves like a quantum particle, two things we can show: that they have discrete energy levels, and second thing also we can show that they can tunnel through this barrier. If we can show these two properties, we can say it is behaving like it's a macroscopic size, the variable is macroscopic, and that is behaving like quantum. Now look at this picture. That it shows if I have the system, that means phase particle at this ground state, it can tunnel through this or it can jump over this. These two possibilities for coming out, escaping, right? And for both, this probability would be small because it has to overcome a big barrier. And in this case, it has to face a big, thick barrier, right? In both cases, its tunneling probability is going to be smaller, right? So this rate would be the minimum, smallest. If the phase particle is here, this escape rate would be higher. If it is here, the escape rate would be even higher. So just by measuring the escape rate, we can get information about the quantum states. And also what we can do, say we have this system is here. Now we can excite by sending a microwave pulse from here to here. Then it is here. See, what will happen now? It will have a higher escape rate, right? So by exciting with a resonant microwave frequency, I can enhance the escape rate. And thereby also I verify that they have really quantized energy level. So these are the things that I show. This is the picture that I retained here so that you understand it better. So now this is a situation where a small current IB has been given. So the barrier is still quite high. And if I increase this current, this axis is the current, this barrier becomes smaller and smaller. So the potential gets distorted like that, right? So this is the deep potential. That means the energy separation here between 0 and 1 is going to be large. Here it's going to be smaller. It's going to be, again, more small, right? So now, if I expose this with a microwave signal, which has a frequency of 2 gigahertz, then whenever I get a excitation, that means a resonance, which is equal to 2 gigahertz, something like this here. In this case, this level and this level, this is equal to 2 gigahertz. So in this case, I get an excitation from this level to this level. Then immediately, what happens? The escape rate becomes larger, right? In this potential, these two is now smaller. So 2 gigahertz will face here, will coincide with this. Even when I actually excite from here to here, then I get enhanced tunneling rate, escape rate. So these are the different escape rates for these different currents. That is shown. So this clearly tells us there are quantized energy levels within this potential. So one quantum aspect has been shown now, the quantized energy levels. Now, let's go to this figure. This picture shows about the possibility of tunneling, right? Now, what happens if it is classically, it would go over. If it is a classical particle, it will go over the barrier. So if we are studying the escape rate there, the probability of tunneling as well as the probability of jumping over the barrier, they are there. We don't know, we can identify what is what. So this is the escape rate, the temperature dependence of that, given this delta U, same, we could vary at the potential. So if we do that, and you see here that whatever classically predicted over the barrier, that agrees with the experiment. But as you go to lower and lower temperature, then it starts deviating from here. And then we enter into a region which is temperature independent, but this escape rate. And this is the region where it is fully quantum behavior, is tunneling fully. There is no over the barrier jump. But this region is completely over the barrier. This region is a both processes take place. And at what temperature? It takes about 40, from the experiment they found about 40 millikelvin, where this sort of flattening starts. And there was a theory by Anthony Leggett working on the same thing. And Anthony Leggett, by the way, is also another Nobel laureate. He got Nobel Prize in 2003 for work on superfluidity and superconductivity. So he actually theoretically envisaged this phase, this quantum phase. So this was the theory, the two main papers over there. So what we have seen now, it's like Josephson junction is, it's a big system, it's behaving like a quantum system. So this is similar to a macroscopic nucleus which emits a particle via quantum tunneling. So a nucleus, alpha decay, is an alpha particle gets out with tunneling. But you have quantized, it's a quantum system, of course. But this whole Josephson junction is behaving like a quantum system and that emits this, this so-called particle. This phase is defined by a particle, the B. So the particle is initially a metastable bound state and tunnels out into the continuum states. That's what happens in alpha decay, right? And this similar things are happening here in that low, very low temperature range. So just to picturize these three different tunneling, quantum tunneling domain I just described, the first one is the metal, where electrons are the carriers. So if I have a gap here somewhere, the electrons tunnel across the gap. That's the first example I had given. What is the second? It is like superconductors, insulators, superconductors. Here insulator could be a tunneling gap like that. So here the Cooper pairs tunnel across the junctions. Not just single electron like the one before. It's a Cooper pairs tunnel. But the third regime, where I saw the macroscopic quantum behavior, that's where even this whole Cooper pairs, they condense into a single entity here. The Cooper pairs behave as if they were a single particle that fills the entire electrical circuit, and quantum mechanics describes this collective state using a shared wave function. So it's a single wave function that describes the whole thing. So this is, you can imagine something like a river flowing without any friction. This is similar to that. So these are three distinct quantum tunneling regime. And this Nobel Prize is for this regime, 2025. Now, I just briefly go over how these things actually go into technology. So I just flash a few slides to show what is the development in our institute. So basically, we have transmon qubits, which are something like that. And to ensure that the system stays in the ground state, we have to cool it down to very low temperature. How low? It's about 10 millikelvin, which is 0.01 degree above absolute zero. So we cool it down and equip our Josephson junction at that temperature. And that's when we ensure that the system is at zero state. Now I can apply a microwave signal whose frequency is equal to this frequency. Then I can excite to 1. And now I can work with two states, which defines a qubit, quantum bit. So we can now generate a superposition of these two states, 0 and 1, experimentally, just using the microwave signal on this system. And all sorts of, Professor Bhanudas described many single qubit gates. We can implement all those single qubit gates on this qubit. So this is the this is the difference in energy. The corresponding to that, there's a frequency, and we shine microwave photons of that frequency for manipulating the quantum bits or controlling the qubits. The dilution refrigerator, which is the bottom plate, is about 10 millikelvin. Gradually, how we built it. These are the electronics that works at very low temperature. We integrated those in. Then this is the qubit is inside this cylinder. This is the shielding. As I said, the quantum systems are very sensitive to the environment. So the magnetic field, Earth's magnetic field also can be destructive. So to shield from all magnetic fields, we have this shield around the qubit. So this is the qubit is inside. So this thing is inside this. And this qubit is this little piece here. And this cavity is the microwave resonator. So microwave photon standing waves are produced within that. And that cavity photon and qubit interaction, that's what you utilize to read the state of the qubit. So that's the qubit. And as you have seen that this is the Josephson junction here. It has its own capacitance, but we add another capacitance. It's called transmon. The capacitance value is very high. That becomes less charge noise sensitive, to reduce the noise sensitivity to that. And then we feed in microwave into this cavity. Then we can study the interaction between the cavity photons, and so this is the equivalent structure of that. This is the Josephson junction and its own. This is capacitor, and this resonator is described by another LC oscillator. Then the microwave signal we feed through this. So the whole thing, when it is complete, this is open. It has 4 layers of jacket. When you put them together, they look like this. So these are inside the electronics and the measurement system. We set up how we made it. And with that, what you see here is called the Rabi oscillation. By applying microwave pulses, we can actually tune. As I said, I can control the superposition. So at some point, it is the full occupation of state 1, full occupation of state 0. So this oscillates, this probability. That's the plot. But if you notice here that the amplitude is gradually going down because we can totally avoid the interaction with the environment. That's why it loses this amplitude. So if you make it measurements over a longer time, this is 1.6 microsecond, this is 100 microsecond. Then you see that this amplitude has gone down to almost 0. So from here, with the fitting, we can find out T1 relaxation time. That's the decoherence time that we find out. And by doing other measurements like Ramsey interferometry and Hahn echo measurements, we get the dephasing decoherence time, all these measurements. And then we use that interaction between the photon in the resonator and the qubit. What is qubit is behaving like an atom, right? You have quantized energy states, just like atoms. So and photons, photon-qubit interaction, photon-atom interaction, what is it? What theory describes it? Quantum electrodynamics, right? So you can use the quantum electrodynamics formulation and the Hamiltonian corresponding to that, and then you can show that if an empty resonator has a resonance frequency at the middle, say this blue position, but if it interacts with the qubit, depending on the state of the qubit, whether it's at 0 state or 1 state, the resonance shifts because of this interaction. And this shift, if it is at 0 state, we see that this has shifted to higher frequency. If the qubit is in 1 state, it has shifted to lower frequency. So by measuring this shift, we can actually determine what is the coupling energy between the qubit and the photon. So quantum electrodynamics experiment you can carry out here. But in addition, what we have done here, we have identified the state of the qubit without destroying it. You have heard that once you measure it, the system collapses into one of these 2 states, right? In this case, this is quantum non-demolition measurement. That means without demolishing the qubit state, we could still get a measurement, what state the qubit is. Anyway, so that's with 1 qubit, but we are soon going to work with a 5-qubit quantum processor. You see this central 5-qubit, qubit 0 to qubit 4, and we are going to start working with the 5-qubit system pretty soon. And as Professor Das has carried out meaningful calculation and published that already with 4-qubit with his collaborator in Japan, Professor Nakamura, who is the inventor of the superconducting qubit. So we hopefully, even with a 5-qubit system, we'll be able to do some meaningful quantum computation. So this is the year of science and technology. So just I want to mention briefly, flash over, what sort of technologies have already been available from 3 quantum tunneling regimes that I mentioned. First one, top one, the scanning tunneling microscope, I have already seen. That's the big technology that came from quantum tunneling. And various possibilities I have shown what you can do with that. Now, SQUID, superconducting quantum interference device. This is actually a loop, and where you have 2 Josephson junctions. That's a SQUID. It's a very powerful magnetometer. And you can map magnetic field. What is you see here? It's a dollar bill of the US dollar bill, right? This is George Washington's picture. And that has been mapped with a squid. And you see this. So this is the way it is printed, the dollar bill, is the ink. That ink has magnetic particles, which has very low magnetic field, something like of the order of nanotesla. So you just map the magnetic field with a squid, and then you can get image all these things with the microscopy. But this is just a demonstration there, but it's not of much use. But where it is very meaningfully used is the magnetoencephalography, uses squids to detect the weak magnetic field produced by neural electronic activity in brain. Very high field sensitivity of the order of femtotesla is obtained with that squid. So you have a helmet with thousands of squid within that and connected. So it images the brain activity. If there is a little brain activity, there is a signal, weak electrical signal, that produces a magnetism. And that magnetic field is mapped by doing that. So this technology came from the second type of quantum tunneling, which is Josephson junctions, the tunneling, Cooper pair tunneling. But the third one, of course, is that superconducting quantum computer, quantum cryptography, quantum sensors, all these things are coming out from the third kind. Well, with that, I thank you.
It's a wonderful talk, but what I missed was that I didn't introduce him. But I don't think now I need to introduce him. But just for the sake of completeness, he did masters from Bangladesh in 1977. After that, PhD in Sunny Albany, then followed by guest scientist at Haslab, and then Marie Curie Fellowship at different part of the Germany. And then it was a major time he spent in the Institute of Physics. Many of us did PhD there. After that, he moved to IACS and then IIT Kharagpur, and later recently at CCG Crest. Interesting is that now he is doing a wonderful experimentalist. We see now that one. So it's indeed a very nice thing to end with his talk on this 100 years of quantum mechanics, both theory and experiment. Any questions, of course, welcome, if time permits. Yes. So Professor Durga Mahapatra knows much more than me. So he also got the President Award from United States. There.
That's in the US.
In the US. Yeah. Several of them, I missed it. He's also fellow of several society, fellows of several academies. So but that's not to say, but he's very good teacher. Yeah, please.
I want questions from the students because it's important to understand physics, not just doing the algebra.
You can go ahead, Professor Panigiri.
Okay, very briefly. Then have you thought about some experiments with your single qubit?
With single qubit?
Single qubit.
Yeah, we are already doing something like we have recently done the noise spectroscopy of that. So Fourier transform noise spectroscopy. On superconducting qubit, nobody has done that yet. We have done it. We haven't published it yet. But we presented in August in an international conference on superconducting qubits and algorithms in Netherlands. And it was very appreciated very much.
I have in mind something like, Legge-Dorg inequality, which you can check with a single qubit, temporal evolution. Which, for example, if you see Mohes paper in MR, a single qubit is what you need, temporal evolution. You can actually use and test it on Legge-Dorg inequality.
I would like to tell something that you can do a lot of interesting physics with single qubit. Say if I put a small magnetic ball and I can control its magnon frequency by applying a magnetic field. I can study the interaction, quantum interaction between the magnons and the qubit. And in that case, I can do magnons and photons. I can put some small vibrating small piece of material. I can say the phonon spectrum. I can study the interaction between phonon, quantum. Everything is quantum. So it's all quantum mechanics you are doing in your laboratory then.
We move on to students' questions.
Sir,
Yeah, please.
I have a question relating to the slide. You showed figures of electron tunneling, Cooper pair tunneling. Please, can you show the figure? Yes, yes. In the Cooper pair tunneling, as I can see that all the Cooper pairs are aligned both sections. All the Cooper pairs are aligned in the same way, but in the second section, the fast Cooper pair, the fast component is aligned in different way. How
You mean
this
this
is
one?
this one, this one.
This one also is aligned the same way. This thing's on the right side. This thing's on the right side.
But the leftmost is to left side.
This one.
No, no, no. See, on the right side, the leftmost.
This one.
Yes, yes.
Yeah, this is also exactly identical to this one. You see that this and this on the right side. So these are all in phase.
All in phase. Then my question is, how in they are not connected? There is a gap in both sections.
Yeah.
Then how the Cooper pairs in both the sections identify they are in the same phase? My question is that without any connection, how the Cooper pair of
No,
another
in this case, I mean, when you the way the Josephson junction is made, you don't have air gap. You have an insulating material. Everything is solid, right?
Yes.
So even if you start with the same material, you cannot ensure that they are at the same phase, but you can get in the same phase. In that case, they would be in the same phase. But if there is an initial phase mismatch, like phi equal to phi L minus phi, that is non-zero initially to start with, then there will be phase difference on the left side and right side. But you can prepare it if you are very careful with a phi equal to 0 at the initial state. Then both sides will have the same thing.
I think we move on to the other questions if there are any.
Sure, sure.
The last figure.
Last figure.
Yes. You have one wave function, so a single particle basically. You have
Yeah.
written also that.
Yeah, yeah.
So can that single particle be a quantum?
Oh, sorry.
Can it have quantized the energies like atoms?
You are asking the question on the same picture, right?
Yes.
Yeah, this one. Yes. Yeah, this is like a single atom.
Single atom.
Yeah. As I said, this whole thing behaves like a single thing. So it's represented by now.
It's a Bose condensation kind of
It
thing.
is a condensation, yes. And you
And
see that
behaving like a single
it happens at very low temperature, below something like 30 millikelvin. So Leggett's theory calculated T equal to 0 theory, that is close to T equal to 0.
Okay, so
And that's why I said it is like a big nucleus.
One question there.
Is Bose condensation always behave like this? Do they behave always like this, or this is a special case?
The Bose condensation also happens the similar way. Yeah, you get a single wave function.
That single wave function.
Yeah.
Is like any Bose condensation.
I think in all Bose condensation it should happen a single state. Right?
So it has quantized energy.
Even if when you do the with atoms.
No, no.
Right?
What we say is that condenses to the lowest energy.
Right.
So does it have also quantized energy levels?
Quantized energy levels, no.
No.
If anything has to be quantum, you know that there's an uncertainty there. The uncertainty, because of uncertainty principles, energy can never be zero. In a simple pendulum, its energy can be zero, but when you have a hydrogen molecule, which is like a harmonic oscillator, its energy can never be zero.
Okay, I think the last question.
Sir, I
There.
have a question.
Just wait a minute.
How exactly you transfer the gigahertz frequency to a qubit? What is the role of the cavity there? Is there any size of the cavity that matters?
Okay, yeah, size of the cavity matters because you have to design your cavity in such a way, and you have to simulate what is the resonance frequency for that particular structure. So you have to design the cavity that way.
So you have to know first the energy state of the qubit. Accordingly, you have to
No,
design the
it's
cavity.
independent of the qubit. Here, the resonance frequency of the qubit is about 5 gigahertz. Resonance frequency of the cavity is 7 gigahertz. So you have to design that cavity in such a way. Say I want 7 or 8 gigahertz. I want. So I have to design the sizes of the cavity. That has to be right. That I have to simulate these properties and find out that yes, I get a resonance at 8 gigahertz.
And the other one question is, you mentioned that about any charge noise that is effective for the qubits. And is there any other options for avoid the thermal noise and getting little bit higher temperature the qubit should work?
Then of course you get more errors because coherence time goes down, and if you
there
raise the
is no
temperature,
possibility to mitigate
yeah,
this.
so a simple thing is that if you design this energy spectrum, right, for your qubit, and now we can calculate from the Boltzmann distribution of the probability of occupation in state. Now, if I keep this one and leave it at 300 degree Kelvin, you can find that n equal to 1 to n equal to 100, the probabilities are almost the same, probability of occupation. So it is not a two-level system. So it's a junk. So if you now go it to 10 millikelvin, you can show that the probability ratio of occupation of at n equal to 0. If you calculate that ratio, you'll find that this probability is about 10 to the power minus 10 compared to this one. That means now we are ensured that the system is at the 0 state, ground state. And for any quantum computer, the first condition is that you have to initialize. So you should be able to initialize the system to the lowest energy level.
Okay, I think the last question from him.
Thank you, sir, for the nice talk. I have a you have a condensation of the Cooper pair, and there is an insulating material in them.
Yes.
Then my question is, if you don't prepare this quantum state of the condensate in the same phase, how that makes the current to flow in a single direction? Are you applying any?
No. In this particular case, yeah, condensation of Cooper pair. Yeah. Before condensation of Cooper pair, you go to that one, right? Yeah. So there, if you cannot make it at the same phase, phi L and phi R equal, then phi is non-zero. So we have done the quantum mechanics of phi. If it is zero initial, is fine, no problem. So what you found that the phase particle oscillates at the minimum wherever the minimum comes. If initially you start with a non-zero, then the minima will shift. So at the minimum of this potential, the phase particle oscillates. So even in the presence of your insulating material there. So even here, that doesn't matter. Insulating material is here. It doesn't matter. It will form this condensed state. Because it can tunnel anyway. Reception junction, you have seen that, right? It can tunnel anyway. Well, when it goes to that, we are dealing with a particle in that potential well, it oscillates. So it goes both ways. Current oscillation you can also find. That's what I shown, that current peaks that correspond to excitation from one quantum state to the another state.
Okay, I think so. We stop here and let's thank the speaker, Professor B.N. Dev. Thank you very much for your talk.
Oh,
is the right take from you?
Sure.
Thank you.
Good evening. I truly value your patience level, but kindly allow me two of your times, a little bit more, to just do the concluding formalities. We are incredibly delighted to see the overwhelming response to our event. On behalf of the convener and the organizing committee, I would like to thank several people for their unprecedented support to make this event a grand success. First, we are most grateful to our director, Professor H.N. Ghosh, for kindly agreeing to host the program. We are indebted to all the distinguished speakers for kindly sparing their valuable time and taking all of us through this exciting quantum journey of 100 years. Our heartfelt thanks are due to all the participants who have taken the pain of coming from various places such as Bhubaneswar, Khurda, Cuttack, Puri, Jagatsinghpur, Kendrapada, Berhampur, Rourkela, and also I see some of the OPS, Odisha Physical Society members gracing the event. And all of them have made this event extremely special for us. We are truly overjoyed. We are equally thankful for the financial support provided by Chairperson, School of Physical Sciences, and Anusandhan National Research Foundation ANRF funding through Dean R&D NICER. Last but not the least, we owe our gratitude towards all the faculty, staff, especially the auditorium staff, Mr. Prasanna, Mr. Vidyut, staff from administration, photographer, student volunteers for extending their support to execute the program smoothly. We are also thankful to Pacific Parampara for the catering services and Jena Travels for the transport support. So with this, the program concludes. I welcome you all to enjoy the high tea outside and have a great evening. Thank you.
High tea is arranged outside.